organized it. So with that, I would request Professor Suhas if to say a few words, and then Professor Chandra as the coordinator.
Good morning, all. I am Suhash Ranjan Dey. So basically, the advanced materials workshop. So I guess that you all work in this area, okay, and and research, doing research in this area. So the one idea that I want to share, because I was earlier the TechCube coordinator also from IIT Hyderabad. So one other reason is of bringing you all is not to teach you. Basically, it is like train the trainers program. So you are already a trainer in your respective institutes, and whatever you will learn during this interaction of these 2 days, okay, and that you should go and go back and you will be teaching it to your own students also for in teaching purpose as well as doing research purpose also. So anyway, I will be taking the first session on advanced materials on high entropy materials. So I will be interacting more. I will be talking more on that topic. So I request Professor Chandrasekhar Sharma to come and say a few words.
In terms of metal characterization or in terms of understanding the various aspects of advanced materials, as Professor Suvash was mentioning, that it is having wide area like energy materials, healthcare, also biomedical materials. But then some of the common threads under these materials will be discussed, and more importantly, there will be hands-on sessions. So I'm sure that you will enjoy the hands-on sessions more tomorrow. And my request to all of you again, as I visited your institution and I made this last time as well, that please use this opportunity to interact with the faculty members, not just only the resource person for this workshop, but also the potential host faculty for IIT Hyderabad, so that you can plan your visit if you have not planned so far in the coming months. So take this opportunity to meet, interact with the faculty, and possibly fix the dates for your visit. So we are very keen to host you as well as your students. And in fact, when I visited your institution, I made it even little more flexible that in some institutions where we do not have enough PhD students, we are even open to the MSc or MTech students also, right, for their projects. So please try to take this opportunity as a point where you can interact with the faculty, fix the dates to IIT Hyderabad. Again, to repeat that for for faculty it is for 15 days visit, and for the PhD scholars they can stay up to 2 months. And for their stay, they will be given some kind of a stipend or some kind of financial support, so that they need not to put anything from their own pocket. So once again, welcome, and I'm sure that these 2 days will be quite enriching, and not only interact among your team, but also interact with the other spoke institutions, because this collaboration under the pair is not just between the hub and the spoke, but also among the spoke institutions. So again, take this opportunity when you're visiting in person for this workshop. In fact, we are just going to have another workshop now in healthcare, and two more workshops will be planned in the subsequent month on energy as well as AI. Last but not the least, I would again reiterate that as we discussed earlier, that we are now also going to start the workshop at your places, especially the generic workshop like on scientific proposal writing or science communication. So already we have started communicating with the RIPO team. In the next 15 days, we'll be having workshop there, and we are now quite open to have workshop at other spoke institutions where our team, our resource person will be visiting you and conducting the workshop. So I think we are now left with 6 months, I would say, effectively. So please take this opportunity to utilize these 6 months, and we have the financial support available. That how much we can collaborate, and we can start working together in the next 6 months. So once again, wish you all the best for the next 2 days, and I congratulate the organizers, coordinators for this workshop, especially Dr. Shuda, Suhas, and Dr. Sakit, who has put a lot of efforts, and their team members who will be assisting in conducting the lab sessions. So thank you, Shorya.
So thank you, Chandra and Suhas. I will now just add one small thing to what Chandra said. He put it very eloquently that this is an opportunity for us to collaborate not only between the spokes and the hub, but also between the amongst the spokes, right? I will also add one more thing. We are limited by time, that we only have 2 days to basically have the theory plus the hands-on, and of course we cannot cover everything. It's practically impossible. But having said that, in case you have something very specific that you want to visit, want to see, want to discuss, we are happy to facilitate that, right? Like for example, he mentioned Sati. Even within Sati, we have a set of 11 microscopes, but most likely you'll be spending time on 3, right? So in case some of the others are useful, we will do a facility tour. You are most welcome to come and use it. I think there are a few people from AI. We have a lot of data that you can potentially work with for doing all sorts of analysis, right? So there are various avenues that we can think of exploring. It only is a matter of discussing, and we are all open for it. Thank you. With that, let's start the first session. I would now request Professor Suhas, who is an expert of high entropy materials, and subsequently he'll also be chairing the session, and I will see you for the afternoon session starting after lunch. Just for an administrative logistic thing, the lunch is hosted at ITH, I think 4th floor, and please come back on time so that we can start the next session on time. Thank you.
Thank you, Dr. Shaurya. Maybe I can keep the mic over here. So since the title or the program name itself is pair, that means we are equals. Don't think that you are students and I am a teacher over here. So it's kind of finding the right synergy, okay, among ourselves, among yourselves also, as Professor Chandrasekhar Sharma said, and among ourselves, that means with us also, so that we can progress together further. Just let me remove and let me bring to the slide. So the today's the first topic is on high entropy materials, and the way I have made the presentation slides is that you can, if you want, I can give it to you after this session. I can share it with you, and you can you can take these slides and teach it or show it to your students also, research scholars as well as students also. So no need to take note down. Maybe if you have any specific questions, you can ask me, stop me in between, and ask me also. Otherwise, there is no need to take pictures or this, pictures or notes. I think you just try to understand. Okay. Of course, most of you know already. But if you are from different stream, then it will be nice. But before doing that, may I very quickly have the quick introduction from from all of you. Just your name, your department, that's it. Okay. Okay. That's true.
Good morning, everyone. Myself, Dr. Susan Clark, I'm an assistant professor BSc department in IIT Hyderabad.
Yeah, good morning all. Myself, Dr. Prabhu. I am from CSC department in Delhi.
CSC degree.
Good morning, everyone. Myself, Manivandan from NIT Hyderabad Chemical Engineering Department.
My name is Dr. Vinod Kumar Raja, Chemical Engineering Department from NIT Andhra Pradesh. I work on advanced ceramic membrane materials.
You already know. Please.
Yeah. Professor Nagaprasad Naidu, Professor of Mechanical Engineering, JNT University, Anantapur, Andhra Pradesh.
Wow.
Thank you.
Welcome, sir.
I am Professor Prashanti, a Senior Professor for Mechanical Department, JNT Hyderabad.
Thanks.
Professor Shesh Maheshwari, JNT College of Engineering.
Thanks, sir.
Viren Kumar, Mechanical Engineering Department from NIT. Dr. Rajesh Reddy, Technology Department in NIT.
I'm Dr. Santosh Kumar Daya, Department of Mechanical Engineering from NIT Andhra Pradesh.
You are also participating? No. Okay.
Dr. Mohan Satnam, Chemistry Department, Pandit Ravisankar University.
Nice.
Dr. Ishwar Kumar, School of Engineering, Chemistry, Pandit Ravisankar University. Dr. Y.K. Kumar, Department of Physics, Pandit Ravisankar University.
Dr. Kamesh Kumar Srivas, School of Studies in Chemistry,
Right. Very nice. Yes, ma'am. Yes.
Myself, Dr. Sarita, I'm from JNU College of Engineering, Turkey.
JNU, Anantapur.
Anantapur campus.
Thank you. Nice. Thank you, madam and sirs, for joining this session, coming to IIT Hyderabad and joining this session or this workshop. So, the first we are going to start with high entropy materials. So, and we will be discussing about the concepts behind it and the properties that one can harness from high entropy materials, and what are the processes of making high entropy materials and its respective applications. So, so if you start with the materials, we know that our human civilization is associated with materials, as we know, and if we see, sorry, okay. Okay, it's a little slow, just 1 second. Let me again please start it. I think now it will be okay. It's a little slow. But, so as we know that human civilization itself is associated with materials. So we are no different than materials in the sense that we require materials in our day-to-day, to sustain in our day-to-day life. So over the period of time, we could discover several materials, and we have made a table out of those materials or those elements, and this is the modern day periodic table. So as more the numbers of elements you see, more are the possibilities of its application. So this is, if we use single, so total if you see, there are more than 100 elements we can see over here, right? And they have been made into a table format, used and named them, as per their properties, okay, or as per their number of electrons present in their valence band. So this way modern periodic table is constructed over here. So if we use each one of these elements itself, so there are more than 100 applications we can get out of them, right? 100 elements means 100 type of usages one can have. What if we mix them together? That means we take one element and mix it with another element. So we will create an alloy, okay? And the combinations that are possible is immense, right? You can do the permutation and combinations. So as we increase the number of elements, mixing of number of elements, we can have more number. It will be crossing. If we take 5, for example, it will be crossing billions. So billions of opportunities are available of usage of elements if we increase its mixing. Okay, mixing of these elements. If we increase that number of mixing. So that way, this high entropy materials have come, where we try to increase the number of elements, okay, in the alloy making or in the compound making. Okay, so that's why it's called high entropy. Why high entropy is there? So that we will come to know soon. So basically, the whole idea is that we increase the usage of number of elements given in the periodic table, so that we can increase the opportunities of its utilization. That's the basic concept behind mixing of elements. Now, what will happen if we mix the elements? In what scientific way we will gain? That's what we will see now. So, the today's talk is basically, it will be on high entropy materials. So we will be introducing the high entropy materials and different types of high entropy materials. So we know that basically material science and material engineering, if you see, so it's basically divided into three major parts, right? So we deal with solids. Generally, material science and metallurgical or mechanical or civil, we generally deal with solids. So under these solids, there are different categories based on their applications and properties and applications. So we divide them into metals, polymers, and ceramics, right? These are the basic, more or less, three classifications or three divisions of solid materials. Under this division, also we can mix two of these segments, let's say metal with ceramics, and we can create a composite, right? So, and that composite will have with different properties and for different applications. So we can tailor mix these materials among themselves also, and we can create more possibilities of its usages. So same way, if you mix, you can mix metal with ceramics or metal with polymers and create composites. Also, you can mix metal with metals and we can create alloys. So that's the difference if you see, between mixing of metals and mixing of metals with others. So if you mix metal with another metal, you create an alloy. If you mix metal with a non-metal, for example, element, then you can create a compound. So that's the basic difference between, let's say, the material science and the metallurgy also. In metallurgy, basically, people, they use deal with metals or multiple elements of metals, that is alloys. And in material science, basically they deal with compounds, okay, or semiconducting materials. So that's the basic difference between material science and material engineering, if you want to know it in deep. So as I said that you can, so in periodic table, if you see, just I go back, okay. In periodic table, as I told you that these are the columns are groups, okay, given as group numbers, and the rows are, okay, given as per there. So if you see that these groups are basically group 1, group 2 are basically signifying or telling us about the number of electrons present in the valence band. Okay, number of electrons that are present in the valence band. For example, hydrogen and group 1 is having 1 electron present in their valence band. Okay, valence band, yes. So the last cell, the outermost shell, and the outermost band in that orbital in that outermost shell. So if you see, then you will find that all these elements are having 1 electron, okay, in their outermost band. Same way, it is having 2 electrons, okay, and like this you can go on, keep on doing. And if you see how they are arranged in a row manner, can anybody tell how they are arranged in the row? Row number 1, row number 2, row number 3, what does it signify? Anybody? Any idea? So basically these rows are the shells. It represents the shells. So the first row, hydrogen and helium, it represents the K shell, right? Then next is the L, then M. Okay, so K, L, M, and O, P, like this the shells goes. So that way the elements are arranged row wise, and they are arranged vertically, okay, as per based on their electrons present in the valence band. This we understand, right? So in this way, we have got several number of electrons, elements, okay, and and we can see also that these rows, the groupings also done like this is the S orbital. We know about, right, shells, orbitals. We know, right, all this basic quantum detailing of an element. So this is a L, this is S, then this is D block elements, all these are D block elements, then this is P block elements, right? And the F block elements comes under this lanthanide and actinide series. So these are the F block elements. Okay, 4F and 5F series are being given over there. So F can have 14 electrons, so 14 elements are possible. So you can see that each of this 4F is having 14 elements, and same way actinide series, 5F series is also having 14 elements. Now, based on this presence of electrons, number of electrons, and presence and their orbitals, we can devise or we can understand their properties of those elements. So based on the placements of this element in a particular group, we can understand its properties. Basically, that's what I want to tell you. Okay, we can understand the chemical property as well as we can understand the physical property. The chemical property is basically associated with the number of electrons present in the outermost shell. So these are all arranged as per their chemical properties. That means these group elements will have similar chemical properties, right? Okay, and the physical property basically is associated with the nucleus, number of protons and number of neutrons present in the nucleus of that atom. So by knowing the number, the atomic weight, let's say, okay, by knowing the atomic weight, we can predict its physical properties. So, for example, specific density, okay, this kind of values we can predict. So this is from periodic table itself. We can understand the physical and chemical properties of individual elements. Okay, so we can also mix these elements among each other, and we can further multiply or further augment the properties, right? Okay, and fine tune those properties and tailor made those compounds or alloys for our specific application purpose. So here, if you see the periodic table, can you tell me how many metals are there? So if we distinguish them as metals and non-metals, so how many metals do you see in a periodic table? Maximum are metals. So maximum are metals. Around, if I take 100, first 100, if I take, count up to 100 elements only, if you see that 85 among them are metals. Okay, and the remaining are non-metals or semiconducting metals or materials. Okay, so that's the reason that whenever our human civilization, we started with metals, finding because metals are much more possibility of finding metals are higher than non-metals, and we started using metals, started getting metals from the Mother Earth. Okay, and we started using it. So that's why the metallurgy word came, and where the extraction, finding of ores and mining them, and then using those ores for metal making. Okay, so metallurgy field came into the picture from there, and then the finding on usage of silicon daily, which is used as semiconductor. A new stream has been evolved from that is called material science. The semiconducting usage of semiconducting property of a material, okay, has initiated a new stream or new field in materials. Is called material science maybe. And the overall usage of all the elements basically comes under materials engineering for a technological purpose. Okay, so one can use these, let's say, metals and can make an alloy with another metal, then we will be calling it alloy, right? But if we mix them with non-metal, for example, if I mix some metal with oxygen, then it will become a compound. Okay, so what high entropy materials basically means is that we will try to mix. Okay, so anyway, we will come to the high entropy materials soon. What we can is that we can mix it with metals and create alloys. We can mix it with non-metals and we can create ceramics and oxides. If we mix it with oxygen, then we will call it as oxides. Otherwise, if we mix it with some other elements, for example, carbon or nitrogen, okay, then we can create carbides, we can create nitrides. So the traditional carbides are single metal carbide. Okay, any single metal, you can take iron carbide, okay, for example, or iron nitride. Okay, and same way we can make iron oxides also are present, right, in the mother as ores. So, but what is the high entropy meaning? Why it is called high entropy? That we will come into the picture. But first we need to understand is that, forget about the high entropy part. we understood the materials. Materials we have divided into several segments: metals, ceramics, plastics, okay, polymers. I mean, and then we can mix the metal with metal. Then we will create alloys. We will mix it with, if we mix it with other elements, non-metals, we can create ceramics. And if we mix it with oxygen, then we call it as oxides. Okay, and then we can see the properties and applications based on those compounds, okay, that we create, or alloys that we create. Now we are adding one more term, that is called high entropy. Now we will understand what is high entropy and how is it different from the traditional conventional materials. So what is high entropy materials? So basically these are compositionally complex materials. So it's also called CCM, compositionally complex materials. So it is basically mixing of elements which will ultimately increase its entropy. So so we call this mixing of element if the delta S, that is the entropy of mixture, if it falls between 1.5 R to 2 R, okay, if it falls between 1.5 R to 2 R, then we call it as high entropy alloys. And basically, and below that, this comes under medium entropy alloys or conventional alloys. So in conventional alloys, the entropy of mixture is less than 1 R. Okay, if you increase the number of elements in the mixture, then it will be called medium entropy alloy. If you make the mixture so that the ratio becomes 1.5 R to 2 R, then it will be called high entropy alloy. And higher than 2, it will be called ultra high entropy alloys. So basically, to come under this bracket of 1.5 R to 2 R, okay, we basically these are the characteristics how we can come into this range. So basically, under this range, these are the following parameters that will be automatically be followed, okay, or observed. So each of these elements, their atomic weight percentage will fall between 5 to 35 atomic percentage of mixing. Okay, so each of these elements will be having 5 to 35% atomic weight percentage. And high entropy alloys basically should have nearly minimum 5 elements. Okay, that is minimum 5 elements. It should constitute with 5 elements, 5 or more number of elements. And it will show the 4 core effects. The 4 core effects we will be detailing it further, but these 4 core effects will be sluggish diffusion. It will have sluggish diffusion. It will have high entropy effect. It will have lattice distortion, and it will have cocktail effect. So just remember these words. We will be explaining it or learning it in more detail. Okay, in the next few slides. Yes, please. R is gas constant. Is gas constant?
Gas constant value.
Yes, gas constant value. Okay. So basically, R is gas constant value, and if chemist can understand it maybe much more better. Okay, but anyway, we will be coming to this thing. Okay, how R is related to entropy. Okay, how these numbers are related, that we will be coming into we will explain it a little bit. Yes, ma'am.
Have 5 or more elements, so homogeneous materials or different elements also?
These are 5 or more different elements only.
Different elements.
Yes. So we have seen the periodic table.
Metals and non-metals.
Anything. If it is metals, as we understood, if they are metals, then it will be called alloy. If it is a non-metal, then it will be called a compound. So high entropy compound, high entropy. If it is oxygen, then high entropy oxides. Like this, it will be called high entropy carbides. So we will be seeing some examples of them. So basically, the basic idea is clear, right, for among all of us. So many of you or most of you know about high entropy materials, but those who does not know, please feel free to stop me and ask me. No problem. Yes, sir.
It has anything to do with the homogeneity rules?
It has to do with homogeneity rules. Yeah.
It has to.
Yeah, everything is follows that rule. That is a basic fundamental rule. Okay. But anyway, we will come to all these things. Okay, little later. Let us first begin, and then we come back to everything. Okay. So basically what sir is saying is Hume-Rothery rule. So that Hume-Rothery rule is alloy making, is used in alloy making, where the numbers are very few, maybe 2 or 3, not more than 2 and 3. There those rules are followed. But this is an outlier. When you increase the number of elements, it increases the entropy of the system. Okay. When it increases the entropy of the system, it stabilizes the system more. The enthalpy, the energy of formation, the Gibbs free energy of formation gets increased, it becomes more negative, right? It becomes more stabilized. So that's the whole idea is behind increasing the number of elements, is to stabilize the system. Okay. So basically, if you see that, anyway, we will come as and when we will. Okay.
That I-35 atomic weight percentage, the first question.
Yes.
I-35.
So if you take five elements, for example, if you take 5 elements, and if you in equal atomic percentage, if you introduce in your alloy, then the weight percentage will come. Atomic weight percentage will come is 20%, right? All 5 are in equal amount is present. Okay, equal numbers they are present. Then it will be called 20%. So what we are saying is that among all these 5 elements, each one can be present between 5 to 35%. Okay, if there are 100 atoms, in their 100 atoms, if 5 elements are there used, then each atom will be present, let's say 20 each. Then the atomic percentage will become 20, right? What I am saying is that among all the 5 elements, each element should present at least 5 in number, and it should not go more than 35. That's what is the basic fundamental. Okay, so if you have 5 elements under this atomic weight percentage, generally we will get a solid solution. Okay, phase. So metallurgy people, they understand it better. Non-metallurgists, there is no need to go more. What we were saying is that it will give a more stable phase. Okay, that's the ultimate meaning of it. And if you have 5 elements or more than 5 elements, more elements increases its configurational entropy, which basically stabilizes the phase. Okay, stabilizes the crystal phase. If you increase the configurational entropy, that basically stabilizes a single phase. Okay, it omits the intermetallic phases, for example. As we introduce more number of elements, it omits the chances of having intermetallic phases. So, do you understand intermetallic phase, right? Many of you. So,
it does not come under the. It doesn't satisfy the solid solution rules.
No, it's not that. Yes, but what are intermetallic phases? It's just like compounds. These are metal compounds, let's say, which are ordered structure, having ordered structure. Okay, and normal crystal structures are disordered. Ordered structures means this, we know where the specific elements are placed in that crystal structure. Right? You understand crystal structure. All of us understands the crystal structures, right? So we deal with crystal structures mainly in metallurgy, but it can, if they are non-crystalline, then it's called metallic materials, okay, or amorphous materials, which are non-ordered or disordered. So in normal alloys, they are basically disordered. That means all these 5 elements, the placement of these elements in the crystals, each element in the crystals, we don't know. Then we call them disordered structure. So basically, increasing the number of elements, okay, will increase the disorderness in the, not disorderness in the crystal structure. That means it will not let us know where the placement of this system is. Okay, if they are placed in the exact position, then we call them as ordered structure, and it will have different properties. Okay, disordered crystal structure is having different properties, and ordered structure is having different properties. That's what it is.
Sir, for this making this material, we can take any element from the periodic table and mix together?
We will see. I mean, as in we are just starting with the concept first. We understand the concept, then we will see the utilization, how to mix it and how to do it. So tomorrow in my lab, we will be making one high entropy alloy also. Okay, or high entropy material, oxide maybe. Okay, we will see. So this variety of usage of different elements and making of high entropy materials, it opens up the doors for various applications and modern day applications like energy, sensors, thermal applications. So these high entropy materials comes under advanced materials. Why this comes under advanced materials? Why not conventional? Because with the conventional, whatever usages it required, we have already achieved. Okay. Now with the new age, we require new applications, and for that we really require to tailor-make the properties, those properties which can cater to those applications. So for that we need to find different materials. So one way of finding different materials is increasing the mixing different elements. Another way of getting, can anybody explain or tell me what is the other way of getting new properties, let's say, out of the same material? One way I am telling you is that by increase the number of mixing elements of mixing, we can increase the number of properties, possible properties. What is the other way we can, with the same element, we can change its properties? What is the other way? Exactly, by changing the dimension, size, length scale, right? So bulk is having different property. Okay, two-dimensional materials is having different property. One-dimensional materials will have different property. Zero-dimensional, like quantum dots, will have different properties. So this is so by dimension-wise and by composition-wise, we can change and play around with the properties, and we can get new materials for advanced applications.
Even you can do retreatment also.
Yes, by processing also. By processing is conventional mainly, but yes, conventionally we with same material composition, by changing the processing we can have different properties. That is conventional. But now for advanced applications, we have to think out of the box. So one of the way of thinking out of the box is by changing its composition, either by changing its composition or changing its dimensions of usage. Okay, these are the mainly two versions. So I am dealing with the composition. I think somebody will discuss about the size also, dimension also. I think nanomaterials, somebody will be talking about nanomaterials also. Okay. Yes. So if you see the historical background, it starts at 1996. Okay, but as an Indian, we know that in India we already were working with several element alloys. For example, Panchaloha, Panchadhatu, you might have heard, right? And Ashtadhatu. So we were already knowing the importance of mixing of more number of elements. So Panchadhatu, that is mixing of 5 elements, okay, and mixing of 8 elements is called Ashtadhatu. People were already in ancient Indian metallurgists, they were already using them, and using these different compositions for bell making, or the bell and the gong, as well as the sculptures, right? So mainly for structural applications, these were utilized, okay, and we know what is the importance of using Ashtadhatu sculptures. They are still present in their pristine form, even if they were, under the earth for so many years, so many centuries. They were under the earth. So, but the modern day high entropy alloy was basically started in the year 1996 by Wang and Ye, okay, from Taipei, Chinese Taipei. They first reported the high entropy alloy. Then in 2004, Ye and Cantor, they published independent works on high entropy alloys. So it basically started with alloys, okay, mixing of different 5 or more number of elements in alloy form, and they called it as high entropy alloys, okay, in 2004. Then in 2006, the reason behind those wonderful properties, they try to start explaining those properties via 4 core effects. The sluggish diffusion, all those 4 effects that we have seen just now, we will be understanding them in the later slides. So that those effects, understanding of those effects, okay, they started appearing in 2006 onwards. Then phase formation rules was enumerated in 2008. Then the first application of high entropy alloy, okay, in sub-zero region came up in 2014, and 2015 onwards, not only alloys, it expanded from alloys to other domains. For example, high entropy carbides, high entropy nitrides from 2015 onwards. So now, sky is the limit, as I said. you have got more than 100 elements in a periodic table, you can mix 5 of them, and then create your own alloy. And you can study its you can characterize them, and you can study their properties and find its application, the spectral applications. Yes, so we understood already. So basically, the high entropy comes in this range where the entropy of configuration entropy is between 1.5 R, more than 1.5 R to 2 R. Okay, if it is between 1 to 1.5 R, then it is called medium entropy, and lower than 1 R is called low entropy or simple alloy. Okay. Basically, if you increase so if you see this in this graph, you can see that the ideal configuration entropy. So configuration entropy, you understand, right? Compositional entropy and composition and configurational entropy. What is configuration entropy is that the placement of atoms in the crystal structure. So if you take a simple cubic structure, right? Simple cubic means it's a cube, okay, having elements present in the corners of the cube. So there are around how many? 8 elements are present. So in these 8 elements, so that is a simple cubic structure. If it is a BCC, then at the center of the cube also there will be one placement of one element. Same way FCC means faces. On each face, okay, each face will have a element into it or atom present in it. So the configurational means, for example, in FCC, how many placements of atoms are possible? One at the corner, another one at the faces. Okay, 2 different, all the phases of the cube will have also the atom. So the placement of the atoms, where either they are present in the corner, okay, or at the center face of the center face position. So all these will create possibilities. So those placement possibilities are called configurations. So there are different possibilities of configurations or placement of atoms in the crystal structures that creates entropy. That is also one kind of entropy, right? Placement, different number of placements means different number of entropy. Higher the possibilities, higher will be the entropy. So same way, as you increase the number of elements, okay, so as you increase the number of elements from 1 to 2 to 8, 6, I think this is 8 or 6, 8, then 15 number of elements. So as we keep on increasing, the configuration entropy also keeps on getting increased. And the formula that is there, the formula that is given over here, delta S is equal to minus R x ln x. Okay, so xi, that means I is the number of elements. So I, if it is 5, n is 5, that means with there are 5 number of elements. Now each element is present in what atomic number value? Okay, it's present 20%, then 0.2 ln 0.2, like this you can get. Okay, so you can change the entropy by the number and also by the value of xi. So this way you can change the entropy, and if it falls between 1.5 to 2, then it is called high entropy alloys. If it is more than that, then it is called ultra high entropy alloys.
Could you explain the X?
X is the atomic percentage. Yes. X is the atomic percentage. Let's say out of 100, 20 elements are present in A, 20 present in B, like this. So 20, 0.2, 0.2 is total number, fraction is fraction. So 0.2 is the value for Xi for element number 1. Element number 2 is also 0.2. So like this you can do 0.2, 1, and then 0.2, 0.2, and then 0. Like this you can add all of them, and you can see that R will be falling between 1.5 to not less than 1, 1.5 to 2. Then only it's called high entropy alloy. If it is less, if it is 1, then it is simple alloy. If it is 1 to 1.5, it is called medium entropy, and if it's 1.5 to 2, it is called high entropy. Higher than 2, it's called ultra high entropy. Okay, so these are the differences between traditional alloys, okay, and the high entropy alloys. Traditional alloys generally consist of alloys. Remember, I'm talking about alloys, okay, not oxides or any other materials. So traditional alloys contains 2 or 3 metallic elements, whereas high entropy should contain at least 5, right? Then the traditional element, there will be one base element. In traditional alloy, there will be one base element, and then you mix another element into it. Whereas there is no base element in high entropy alloy, there is nothing called base element. Okay, all can be present equally also, but all should be present between the range between 5 to 35 RNA%. And there is nothing called base element in that. Okay, there is nothing like nickel-based superalloys, for example. Or many of you might have heard about superalloys. Okay, so it's called nickel-based superalloys. That means nickel is having present in higher amount or higher fraction of nickel is higher or highest. Okay, and remaining others are added as alloying elements. So that's the difference between traditional alloy and high entropy alloys.
So when you mean that maximum alloys will be 20 into 500.
No, maximum is 5 to 35, madam.
No, we said no, 5%, that way you take 100% means 20 different alloys will be there. 555.
No, madam.
I'm just asking.
No, it's absolutely
it's nothing
not.
like that.
Not absolutely not. There is no blackboard or whiteboard. That is the problem of this. You should arrange actually at least for the later sessions.
No, you said no 5%, minimum 5%. Like that I calculated. Minimum 5% means how many different elements we can mix as a single.
You can have as many number of elements. That's true, madam. That's
as many means that is fixed now 20.
Yes, maximum is 20. If you have 5, then it is called 20. Yes, maximum elements that can have is 20 elements. Correct, madam. But there are several challenges, in making 5-element alloy itself. It's a challenge because mixing all of them to synthesis method. That's why. So synthesizing and fabricating a mixture of 5 elements itself is a challenging task. Now, if you want to make a 20-element alloy, it's it's very, very challenging.
Hypothetical alloy.
People have achieved it. It's not that. That's will fetch you science paper or nature paper. If you can make 20 elements alloy, then you find a way out and then you make it. You will definitely get a nature paper for sure. But yes, you are right. If 5% is the minimum, then 20 possible elements are possible in an alloy. That's correct.
Sir, generally that metals or elements are present in the from the company we are buying in the form of compound. Then how we can get the pure form?
No, we purchase. We get elements in pure form also. Yeah, we can get element in pure form also. Iron, you can get iron rod, iron powder, or whatever form you want, you can get.
We have to grind.
That synthesis, you are talking about synthesis method, that we will see little later. There are synthesizing 5-element alloy, we will see what are the methods available. We are still continuing with the concept. Let us finish the concept because we don't have much time, okay? Anyway, it's okay. You can stop me in between also and we can continue later on during our lunch session also, it's okay. Okay. So there is a base metal. There is nothing like called base metal in high entropy alloys. It has a well-defined microstructure. Okay, it may have dendritic based on the synthesis method. It may have dendritic structure or eutectic, microstructure. Whereas high entropy alloys are basically disordered or homogeneous microstructures. It exhibits this kind of microstructures. And it exhibits a range of properties, okay, based on their composition and microstructure, traditional alloys, whereas it shows superior combination of properties. So there is a little difference, fine difference between this statement and this statement. See, we make an alloy to have a higher property. But what the property we are talking about is one single property. For example, we can increase the ductility of a product by alloying it with another element. Whereas high entropy materials can show superior combination of properties. That means more than one properties. We can target more than one property and make a high entropy alloy. Okay, same material will be having superior property, 2 properties, let's say, superior 2 properties. Whereas here in traditional alloy making, we just target one property, one single property. Okay, we want to increase the value of one single property, whereas it can be 2 properties. Okay, increment in 2 properties. And the synthesis methods in traditional alloys are casting, extrusion, forging, whereas there are several synthesis methods that are being used in high entropy alloy making. For example, arc melting, induction melting, solid state processing. Okay, mechanical alloy. Somebody was telling that we can mix powders, also take different element powders, we can grind them together and can get a high entropy material out of it also. So the examples are like iron cobalt, iron cobalt nickel. Okay, traditional alloys. Whereas this is vanadium, niobium, molybdenum, tantalum, tungsten high entropy alloy. So there are different, more than five or more than 5 element high entropy alloys have been given over here. Yes. So these 4 effects we will, I think one by one we will take now. So first effect is high entropy effect. Second effect is lattice distortion. Third is the sluggish diffusion, and fourth is the cocktail effect. So these are the 4 effects which people try to explain the superior properties that is achieved through high entropy materials. So through these 4 effects, they basically try to understand and explain the reason behind achieving superior properties. And in these 4, mainly high entropy and sluggish diffusion, and to some extent lattice distortion, are for structural application purpose, and the functional application, that is the material science part, they basically explain their superior properties, achieving superior properties through cocktail effect or lattice distortion effects. So these are the combination of properties, right? Combination of superior properties that can be seen as a cocktail effect. Okay. So, but anyway, we will now come in detail. We'll understand them in detail. First core effect is high entropy effect, right? So what does it mean, high entropy? High entropy means increased mixing entropy. So as we increase the number of elements, okay, this increase the possibility of atomic arrangements, enhancing its configurational entropy. So you can increase basically by increasing the number of elements involved, you increase its configuration, number of possibilities of configuration, which actually increases its entropy. Okay, so this is the reason of increment in entropy, basically through configuration. Increasing configurational possibilities in configuration. Now, if you increase the entropy, the Gibbs free energy of mixing is also gets increased. We understand, right? If delta S is increased, value of delta S mix is high. If you increase this value, then automatically delta G also becomes more increased. So we know, right? Gibbs energy rule, okay, of formation, let's say, okay, formation of a compound or of an alloy. We can increase the Gibbs free energy and we can make it more negative by making either the reaction of formation. For example, here we are talking about formation. Either we can make the reaction exothermic, that means we increase during the formation of that particular compound, the delta becomes more negative. Okay, that means more releasing of energy. So that formation releases the energy. Either by releasing energy during the formation, we can increase its Gibbs free energy, or by increasing the entropy more positive. That means that minus, it's a minus sign, right, before the entropy. So we can either make the delta G more negative, either by increasing the temperature, releasing of temperature, or by increasing the entropy term. Okay. So this is the reason that it lowers the free energy value of the particular alloy or the compound, and by increasing the number of elements. So that's why it lowers the free energy. The other thing is that as I told you already, that if you have more number of elements, it's as per the conventional phase rule, it reduces the complexity. That means it reduces the phase formation, more number of phase formation, and it gives us single phase with BCC or FCC, body center cubic or phase center cubic or hexagonal cubic plan. Okay, HCB crystal phases it gives us, because it tends to, all these terms, it tends to form simple single phase solid solution. As we increase the number of elements also, it tends to give us more single phase solid solution.
increase the solid solution solubility. Okay, and it because of that solid solution formation tendency to have high possibility of solid solution formation, it gives us single phase. Okay, so more number of single phase formation is it happens. Okay, with increase in number of elements, and because of that, because of all the overall effect, it gives us enhanced properties. For example, higher strength, higher hardness, higher thermal stability, more corrosion resistant. So all these properties we get in because of all effects, all these effects coming from the high entropy. So increasing entropy. So first is the high entropy effect. Second is the lattice distortion effect. What is lattice distortion means? There is a, if it's a single element crystal structure, then it will have uniform lattice parameters. For example, lattice parameters means the length, okay, and the angles, okay, in that cubic, let's say cubic structure we are talking about, okay. But if you introduce different size elements into it, okay, then it will create distortion in your crystal structure. So that distortion in crystal structure also can be used for our applications. Okay, so why this distortion happens? Because of atomic size mismatch. Okay, and this atomic size mismatch can create one-dimensional defects like dislocations, or it can create zero-dimensional defects like point defects. Like that means vacancies. It can create dislocations, or it can create vacancies. Okay. So what is the effect of these distortions, lattice distortions? Because of these lattice distortions, it can affect the mechanical property, it can affect the thermal property, it can affect the electrical properties, right? We understand all these things, right? Mechanical properties, how it affects the mechanical property maybe one of you can tell how can you correlate mechanical property, for example, the elastic strength, let's say, with the crystal structure. Can anybody tell me how can I correlate elastic strength with the crystal structure? Okay, but anyway, so these kind of questions also you can ask your students, so that when you teach this high, little advanced level courses also, you can always ask this kind of basic fundamental questions to your students, so that they can rethink back in their first year. They have been taught all these basics fundamentals, right? The atoms and the effects of bonding between two atoms. Okay, how does it translate into mechanical strength, let's say, okay, or the elastic modulus values. Okay, so all these things you always have to keep on doing, because these are high level courses, so they may be learning it in their third year or fourth year, but they tend to forget their basic this thing. So it will be really nice if you can correlate always and try to correlate each of these high level courses with the basic fundamental understandings, so that they can retain, or they can try to retain their basic fundamentals, what they have understood or studied in their first year or second year of their coursework. Yeah. So second effect is the lattice distortion. Because of this mismatch, atomic mismatch, it creates distortions in the lattice, and which can change the properties, mechanical as well as the thermal and electrical, and we can tailor this kind of, so we can choose the elements with different atomic size. Okay, we can particularly choose certain atomic size elements, so that we can fine tune our required properties. Okay, so that is the way of design of an alloy, or design of a compound, 5-element compound or 5-element alloy, is that what exactly actually you are looking out for, and based on understanding the individual element atomic properties, we can take them together, and we can design such a compound or high entropy compound or high entropy alloy in such a way that it caters to our needs. Okay, that way we design an alloy or design a high entropy material. The third one is sluggish diffusion. Okay, so the random mixing of several atoms creates various types of atomic surroundings, which basically means that the energy required for an atom to jump from one side to another side gets increased. Okay, so it varies very greatly. So the atomic diffusion becomes slow. That means it becomes sluggish. Okay, so this atomic, and if you increase the number of elements, that means if you make a multi-component alloy, for example, it will also create, it will increase the diffusion activation barrier also. Barrier means for one element atom to jump over the another element, that barrier also it will get increased by introducing different elements of different atomic sizes. Okay. And the same way, the energy required for this such jumping over a different atoms also gets increased, and this can be reflected from this Q by Tm value. Okay, Q by Tm value, if you see Tm is the temperature, right, melting temperature, right, and what is the Q? Q is the activation energy of the jump, activation energy of the atomic jump. So the activation energy as increases, so Q by Tn values also gets increased, and this increment of these values shows sluggish diffusion. And this movement of atoms, that means the movement of atoms gets restricted by introduction of more number of elements, and that creates a sluggish diffusion. And what is the use of this sluggish diffusion means? It is, let's say for example, corrosion. It is more corrosion resistant, right? Because how corrosion happens? The movement of atoms from bottom to the top, and then it reacts with the air or whichever environment it is. Okay, and it creates a different compound, for example. Okay, so that way the removal of elements atom by atom starts happening, and corrosion takes place, and it corrodes, it destroys your material. So one way of stopping this is stopping the movement or hindering the movement. How can we introduce the hindrance? By introducing more number of elements, which will create a different environment. We will provide a different environment to the atom which intends to move, okay, from its position. So that stops its movement and slows down the movement, and it's called sluggish diffusion effect. And because of this, we can have more stable material, let's say. It will provide us more stability. This you can see the cube. Oh, sure. This you can see the values, as you increase the number of pure iron, pure cobalt, pure nickel, as you start mixing them together, you can see that their Q by Tn values gets increased, largely. The last effect is the cocktail effect. So this effect was basically explained by our own Indian scientist, okay, Professor Ranganathan. You might have heard, many of you heard Professor Ranganathan from IIT Bangalore in Metallurgy Department, Materials Engineering Department. He retired by now. And he is the PhD supervisor of our director, P.S. Murthy, Professor P.S. Murthy also. Okay, so basically this effect still is that if you take more number of elements, it will change or it will alter its, not only the other effects that we have seen, jumping and all these things, it will also alter its electronic properties, electronic structure. Okay, not only the mechanical configuration structure it changes, it also changes the electronic structure of the whole material as well. Okay, and this changing of electronic structure, if we can optimize it, okay, and we can get a synergistic effect out of it. Synergistic effect will enhance the structural severity that we have already understood. Because of the lattice distortion, it will change its or affect its structural properties as well. And another effect of cocktail is that, as this is understood, is that anyway, through examples we will be seeing, where superior combination of properties can be is mostly explained via cocktail effect. Okay, what is cocktail means? It's a mixture of different, let's say here in liquid form, but that mixture can give us a new flavor, as well as we can get their individual flavors also. Whatever. So that's the meaning of cocktail, where we can get individual flavors as well as flavors in terms of properties here, if we talk about high entropy materials. So individual material property also we can achieve from them, as well as the combined properties also we can get out of that. So high entropy materials, classification of high entropy materials. So we understood that they can be alloys if they mix with metals. They can be carbides, they can be diborides, nitrides, oxides. Okay, so basically based on their different types of elements that are being used, we can call them or classify them under that category, basically. And if they are non-crystalline, if they are amorphous, then they called metallic glasses. So high entropy metallic glasses also is one of the area that is coming up. Bulk metallic glass basically is high entropy. You can call them high entropy. Earlier, before high entropy alloys, it was the stream or the field that was very much, a la mode. A la mode means fashionable in year 2000 at that time was bulk metallic glasses, where having different number, introducing different number of elements of different size. If you don't follow the Hume-Rothery rule, then you end up in bulk metallic glass, getting bulk metallic glass basically. Okay. And by following Hume-Rothery rule, but by introducing more number of elements, you will end up with high entropy materials. So that's the difference between bulk metallic glass and high entropy alloy. Is not only being crystalline or being non-crystalline, but also following rules. If you follow the Hume-Rothery rules and increase the number of elements, then you will end up with high entropy materials. Okay. If you don't follow the Hume-Rothery rules and still increase the number of elements, then you end up with bulk metallic glasses, basically. Yeah. So we have understood already the high entropy alloys. So now we will classifications, right? So classifications, we will start with high entropy alloys, and then we will start with high entropy alloy. Then we will come to high entropy oxides. Okay. These two examples we will take most probably, and then we will finish today's class. How much time is remaining still? Till what time? I have to. 10? No, 9:15 to 10. Only 1 hour. This is not 1.5 hours. Oh, yo, it's already 10:15. So maybe I can quickly. Go to. Okay, so I will just quickly go through the slides. Okay. So I have got 35 slides and I am still 14. So maybe we can stop after some time. Just give me 2-4 points more. Okay. So high entropy alloy we understood. Okay, already that is mixture of alloys, and basically the structural materials is mainly having structural applications. Okay, and because it gives higher superior mechanical properties, enhanced stability, and we can use it because of the possibilities of so many number of availability of so many number of elements. There is a vast compositional area that is open to us for new design. So basically it creates a new design space for us for future research, and we have seen already on this. So this is one example where one of the Cantor alloy. You remember Cantor? EA and Cantor, they first reported high entropy alloys. So based on his composition, Cantor's composition, it is now called Cantor alloy. So Cantor alloy is having better superior yield stress value than the conventional alloys. You can see conventional elements and alloys, steel for example. And it also shows, high entropy alloys also shows not only good mechanical properties but also good thermal properties and corrosion properties. This we already understood, right? So for example, if you have elements like chromium and aluminium, they will come up, okay, on the surface, and they will be there on the surface. They will react with oxygen and will create a protective coating, alumina, An2O3 and Cr2O3. So this will also do these elements in your alloy. If you add these elements, then there is a possibility that they will also cover your material and protect it. Okay, so here the cocktail effect comes. Not only the strength, okay, mechanical increment in mechanical strength is happening by introduction of elements, but also it is giving you a protective layer coating. Okay, so this is multiple superior combination of superior properties. Okay. High entropy ceramics, you can have ceramics. You can have ceramics with carbides, diborides, nitrides, and it can have structures like rock salt structure, fluoride structures, other types of perovskite kind of structures. Different structures are also possible with high entropy ceramics. And their main property is they have high melting point. Mainly, if you see this ceramics, that means mixing of metals with a non-metal. Generally, these are ionic in nature. These are ionic salts. So ionic salts have got different types of structures, you know, right? Basic is rock salt, fluoride, anti-fluoride. Different types of structures are possible from them, in them, and because of being ionic nature, automatically their melting points are very high. We know ionic bonding, right? Metallic bonding and ionic bonding. So ionic bonding gives us high melting point compounds. Okay, so because of that ionic nature, they have high melting point, and because of this, because they have got ionic bonding, that is directional bonding, right? Because of this directionality, they have got extreme hardness, gives extreme hardness and wear resistance. Okay, because of this ionic bonding, basically. Now, high entropy oxide. So this is the area. How much? What time? You said tea break, right? After this.
10:50. No, it's my class.
I skipped my class. I come here to teach them. Okay, so then maybe I stop. Okay, I will stop. Maybe just give me 2 minutes. I was not when you were here already. So one more, other than high entropy alloy, as I told you that we will talk about high entropy oxide also. So oxygen here is the element that is added. So basically, whenever you are having high entropy material, if it is oxide or if it is carbide, the main other element that present is, okay, that should be separately be written, and the mixing should be happening with the remaining one. So here the metal cation is there and anion is oxygen. Okay, and it will be called high entropy oxide when you have 5 elements over here on the other side. Okay, that way, and the same formula will be followed, 5 to 35 of each one of them. Okay, and then remaining is oxygen. So that then it will be called high entropy oxide. Same way, high entropy carbide, high entropy nitride you can generate. Okay, and you can use it for different applications. So high entropy oxides can be used for catalysis, sensor storage, all these applications they can be used for. So I think I will stop here. I will, there are synthesis methods. Maybe tomorrow I will be leaving this slide with my students also. Tomorrow when there is a practical session, they can again show this slide in my lab. Okay, and then they will use one of the techniques, for example, electrochemicals, using electricity also we can do chemical reactions, right? We can fabricate or synthesize materials. So using electricity, we will try to see how to make high entropy alloys or high entropy oxide. Okay, and one application also they may show. So I think with this I stop over here, and you can take the slides, okay, and use it for your future purpose also. So I am again telling you is that I am not teaching you, I am interacting with you. Please feel free to ask or discuss anything, and hopefully in these 2 days of our possible interaction, we may have possible future collaborations also in this section. So through student exchange or through any other possibilities. Joint program.
So one thing I would like to ask you. So till now we have discussed all the advantages of high entropy alloys are outside. What are all the disadvantages of them?
Disadvantage is that was the starting. That's why it was if you see its growth also is very slow because of having more disadvantages. The one disadvantage is that if you use so many elements, what happens is that the cost of finding those elements also now in this present scenario, finding different elements is also very difficult. It's better to use only one element and work with that one element. But one advantage I can tell you is that if you use only one element for magnetic purpose, so you use mainly cobalt and nickel. Okay, both are expensive. What if I mix it with other possible elements also, and the jointly that usability or usage of that particular single element will be reduced. In that way, I can cost down. Okay, I can cut down on its cost. Same way, platinum is used in catalysis. Okay, hydrogen evolution reaction also. Why don't we use other transition metals? Okay, frequently found transition elements, mixture of them, so that we can fine tune its electric property.
Cost of it may be compensated by the complex synthesis.
No, cost is always be beneficial if you increase the number of elements which are easily found in then you will drastically reduce the cost. Okay.
And we have discussed the complex, like synthesis complex and this high entropy material. That cost may shoot up when we cut down these base material costs.
Synthesis, maybe because of the synthesis complexity in synthesis, the cost may shoot up. So that's the research there it is. That is one of the reasons that it's not being used very much in use. So in structural purpose, but it's very much in use nowadays in catalysis, okay, and all this.
Because I got this question, I worked on batteries. So when you mentioned slug is diffusion, so in batteries we need diffusion.
Yes.
So but we have generalized it in 4 segments.
Yes. So sluggish diffusion in bulk, but you can increase the diffusion by making it porous. Okay, you have the substrate, porous substrate, and you can use this material, coat this material, okay, in nano size. Then you will have enhanced effect. There you can use the lattice distortion phenomena effect. So that's why I'm telling you is that by introducing more number of elements, you can fine tune the effect also. There are 4 possible effects. It's up to you which effect you want to use for your application. So that comes under a design problem. Very nice question.
Yeah, that's right.
Okay. So thank you for your kind attention, and we will continue our discussions, okay, tomorrow also. Thank you. Please. So now it's my pleasure to welcome Professor Vishwanath Chintapenta. He is from Mechanical and Aerospace Engineering Department, and yeah, your talk is on the additive manufacturing. So that is another very advanced level processing or manufacturing that is coming up in this scientific world. So I finished my Karma Yogi 2 days ago.
It is parallel running.
Okay.
Otherwise, I would have.
No. Sorry. Stolen. Not possible. Maybe you can introduce yourself.
Yeah.
So there are mechanical engineers also.
Okay. Good morning, everyone. So, myself Vishwanath, I'm from Mechanical and Aerospace Department, and in fact, I should say that I work closely with the material science people than my own colleagues. That's what they say. So, this area of additive manufacturing is such a kind of a thing where it falls under manufacturing, it falls under design, and it also falls under metallurgy, right? And today what I'm talking about is mostly on the metal part of additive manufacturing. There are other parts of additive manufacturing such as polymers or tissues and other kind of stuff. However, my focus is on metal additive, so I'll be showcasing that. Just give me a minute, my charger is totally down, so they have to help me with respect to that. I don't mind. keep it one there.
Check. Check my test. Check. 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 Check.
Because then you get opinionated. So this metal additive manufacturing is not a new one. It's a kind of a manufacturing process which is additive in nature, right? It dates back to 1926, and any kind of a manufacturing, additive manufacturing can be coined as joining layer by layer. It is joining, I think this would not work on the, it is joining by layer by layer. So further, based on the constituents, there are three important things. One is type of feedstock. Your feedstock can be a wire, your feedstock can be a powder, right? Based on that, there are different types of additive manufacturing are there. Depending upon your heat source, your heat source can be a welding arc, your heat source can be a laser, your heat source can be a kind of some heating furnace. Heat source can also be some form of electron beam. Depending on that, there are different types of additive manufacturing are there, and depending upon the type of manipulator, you can use it as CNC or XYZ kind of a thing, and based on that it will be there. And then it also requires your final CAD model. So the importance of additive manufacturing is gaining because in conventional manufacturing, you have to make several parts and join them, right? And when you are making a component, the component requirements are based on metallurgical, operational, as well as structural in nature. Because of this, if you make it in a conventional manner, for example, if you want to make a kind of any aerospace high ratio is very high, and further there are a lot of other machines. Additive manufacturing will not totally remove it, but what it does is it tries to minimize those as little as possible by creating a component almost near net shape, right? So that is the reason this is quite most important, and that is also one thing. And if you want to do it for R&D, most of us do it for R&D, and you want to know about new alloy designs and other kind of things, that can also be done using the AM in a sizable manner. So with this, let us go into the classification. So as I said, metal additive manufacturing is characterized into several different things. One is powder based, another is energy deposition based and solid state. So in our group, we started with direct energy deposition wire arc. Somewhere around 10 years back, we used to work that. So I will show initial efforts of our that, but currently we mostly work on powder bed methods, both on electron beam and selective laser. That is the second part of this talk. But let me start with the direct energy deposition wire arc, because that is close to welding. It looks like almost like a welding process. So I just want to connect you with that, because all of you must be aware of it. And then we don't work on solid state much. There are friction stir welding, cold spray, and other kind of a thing. We used to do modeling of friction stir, but that efforts are very limited in our group. However, these efforts are done by Dr. Gopinath and Dr. Professor Surya, as well as the direct energy deposition is also actively pursued by the both of them. You may visit some of their labs at a later point of time. So now let us understand a simple direct energy deposition, which is nothing but using a wire arc additive manufacturing. This wire is a consumable. It just looks like a welding, and you deposit this one over and over again, solidify it to form your component by slicing the layers in a designed manner. But let us look at a simple arc for a cold metal transfer. If you look at cold metal transfer or wire arc additive manufacturing, it depends upon your both current and voltage. So you try to take this welding wire and bring it to the base plate. It creates a resistive heating, and a droplet would be formed, an arc would generate, and based on arc boosting, the metal will kind of melt and a droplet will form. Once the droplet is formed, here you do it in a pulse manner. Once the droplet is formed, you would kind of retrieve back it's in a pulse form, you retrieve back, and that drop of metal would get deposited. And once the drop of metal is getting deposited, your manipulator will forward the wire to a next thing, like a stitching machine. The wire will be moved forward. Since the wire is moving, when there is at a cold state, it is also called as cold metal transfer. Even though there is a hot component, the droplet is hot, it's like from the bobbin, the wire would only move when the drop has been left the tip. So this is the current voltage waveform that will control the things. This is obtained using high speed camera, and also to remove the kind of a bright field from the arc, people have used some kind of a polarizer to capture it. So this is very difficult to capture. If you can see that this entire process happens in 7 to 10 milliseconds. So over a second, several times of it would deposit these small droplets. And it may seem to you as if like the wire is continuously putting the deposition, but it is still a pulse attack, right? Drop, 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 drop. It will do it in terms of milliseconds. So once that drop is being done, in fact, since these are based on the electricity, electric and voltage forms, the melt pool also influences your electromagnetic behavior. So that in itself, the arc stability itself is a different thing, which most of you might have learned it in your welding procedures. This is all controlled using PID controllers now. So let us assume that the arc stability is proper and you are depositing at a given rate, and you would move your welding arc with a velocity, and you would control your power with respect to the current and voltage. The other thing with this kind of a form is your melt pool. See, additive manufacturing, especially in the metal, is nothing but, currently I will say something which I will correct it at later part, at the half of part, is nothing but a thermomechanical process. how well you control your melt pool and how well you kind of know about your melt pool, your final deposition will be based on that. Because this hot metal melt pool try to solidify. In casting, you do have a solidification as a global phenomena, whereas here the solidification is happening at a micro to meso scale, layer by, droplet by droplet, layer by layer with an overlap, that kind of a stuff. So that makes this process, this is what we are like trying to look at it in a closer sense. Now, since we have looked at into this closer sense, I just want to ask you one question. When we make these kind of additive manufacturing kind of a component, I told such a great thing that 6:1, whatnot, every grand thing. Can you directly use this one to your component? What is your exposure to it? What do you think would be an issue? Because it's solidifying, there would be warpages, there would be defects, solidification defects. That would result in deviation from your near net shape, right? In manufacturing, especially in aerospace sector, your precision is such a quite most important stuff. So the biggest problem in additive manufacturing is how to control your near net shape deviations. That is quite visible. But the things that are not visible in nature is the solidification defects that are present inside. So that you can get it after doing the destructive testing at later point. So both will result in deviation from what you desired, and also it comes with free residual stresses. Any residual stresses in service condition is like will kill the life. It's like you want to buy a new brand car and the showroom guy already ran 2 lakhs kilometers. Will you accept it as a brand new car? Because its life is over to a larger extent because of the residual state. You want a brand new means brand new. The same thing, the material you want brand new means in a virgin state. Virgin state means you want in a stress relieved state with less defects and other kinds of stuff. So that's the target, right? But yeah, target is always good. What we dream is good. But can we achieve it? It's the point of research for us, right? That's where we have to go and sit down and understand. So let us understand in a fundamental manner, right? So what is that it is causing residual stresses? I will tell you now this residual stresses not in terms of metallurgical aspects, but in terms of mechanical aspects. So if I look at that black spot here, this is nothing but your fusion zone coming from the melt pool. And you are traversing your weld torch in this direction. As you move along, this fusion zone will be moving forward. As it moves forward, you have a contraction due to the cooling as you go along, and there would be this forward things is getting thermally expanded. This expansion causes a compressive stresses, and these things causes tensile because it is kind of contracting, and it is while it is contracting it is pulling, and what circles what you are seeing here is nothing but isothermal contours. That means the temperature is same all along in this kind of stuff. Now let us take 2 points. I will run over things little bit quickly once we understand the basic concepts. So let us take a point X which is very close to the fusion zone, and let us take a point which is little bit farther from the fusion zone. So 2 points are there which is tensile, which is X and Y, closer point and also the farther point. When I try to heat it up because of the things, it's like I can keep this point constant and move the fusion zone, which is actually what is happening. Or I can do a relative motion. I can keep the heat source and move my point X all along. It is also equivalent kind of a stuff. Now I'll try to move along in this direction from A, B, C, D in that direction. So when I traverse along for the equivalent relative motion, this guy would go into this transverse region, the traverse of this, whereas the other guy will go into this. This outside black color line, it's the yield component. Once you touch the yield, it will give permanent deformation and residual state. Whereas the farther point did not reach the yield, so it will not give much of a, it will not at all give you the things. Whereas the other point which are closer has bigger part. So if you look at any welding kind of stuff, you have melt pool, you have heat affected zone, and you have unaffected. It's still heated up, but it is, you call it as unaffected base plate. So melt pool goes through severe kind of these kind of effects, partially HAZ, and farther parts would get recovered as much as possible. Even though slight deformations would be there, but it's more or less can be recovered. So that is the genesis of the residual stresses when it comes to in terms of mechanical engineers. So this stress is so simple to understand. However, in the additive manufacturing, it is not one single spot. It is one spot, you put it little overlap, another spot, little bit, another spot, and then you put it another layer, you do zigzag, whatever it is. One single point is giving this thing. Multiple things will give heating, reheating. Sometimes it may go here, or sometimes it go, but in the subsequent cycle it may go up. So cumulative accumulation of thermoplasticity is going on. And if you can predict it, then you are the one who could do a digital modeling of additive manufacturing even before it is done in the lab. Right? That is what is the modeling aspects of additive manufacturing we will be looking into today's class. Right? Now, how many of you know finite element methods or are aware of it? Right? So we'll use finite element methods. What's the big deal? As I said, in this process there are two things. There is no physical load. There is no physical load, but the material is going under plasticity. Plasticity happens under shear loading. But how come this is happening? Here it is happening because you are melting the material. You are giving the temperature. Temperature causes differential expansion. That itself is a force. And also thermal softening will also happening. Thermal softening can also cause flow, which is also plasticity. Plasticity is nothing but permanent flow of materials. Either by differential softening or softening, you would introduce, you give thermal load, but you get a mechanical effects. So that is what we are trying to do in this finite element process. So first thing is we will do a thermal analysis and then we will do structural analysis. It's quite difficult to understand, but I will walk you through it. You can form your geometry just like a base plate, backing plate, and then your base plate. Over that you can decide whichever form you want, zigzag or a raster scan or inside out, outside in, whichever form you want you can decide, and you can mesh it appropriately, and you have to activate them as and when the torch comes under it. So you use something called as, you mesh everything, you deactivate entire deposition, you activate the elements underneath whenever the torch is depositing it. So what happens in any welding or additive manufacturing is, there's an amount of mass addition, amount of heat addition to it. The mass addition is done by activating the element whenever the torch is depositing those elements. They give birth, but you mesh it a priori and activate it whenever is torch passing through it. And the heat addition is given through, all of you know, a standard method called, sorry for that, heat source model, right? Now in this additive manufacturing of metals, you need to look at both heat sources and heat sinks. If you go back and metallurgy people, right, when you talk about solidification, solidification is dictated by the thermal gradients. Thermal gradients are your nemesis or enemies. At the same time, thermal things are also good to anneal and make stress relieving every damn thing. So thermal is boon and bane. So that means heat sources and sinks both are responsible to get a good amount of deposition, right? So the heat addition is done through the heat flux, through the torch. Now if you look back, I showed a isothermal contours. The isothermal contours shape look like this, isn't it? So the Goldak was, this is a famous Goldak model which you might have used in your welding. He was much aware of this fact and developed a double ellipsoidal model with an isothermal kind of a contouring. The rear half is a parabola, front half is also a parabola, and those he connected with the fractography. In that way, why the Goldak model is much popular than the Rosenthal or line disc or whatever kind of a model is, he connected the process parameter dictate your weld bead, and the weld bead dimensions are the feeders for this parameters. In that way, your heat source model is connected to the process. It is not damn whatever I want. Modeling people, for us, we do many things, but others people keep saying that junk in, junk out. I don't want it to be a junk in. I want it to be process driven. So the process dictates the bead dimension dictates my dimensions. So I am honoring the process, how it is being deposited. And once that is there, you get your Goldak heat source model. And then what are the sinks? It is done under ambience. If it is done under the ambience, the free convection is also one of the heat loss that goes to the environment. And the torch is at high temperatures. Some torches are as high as 2,000 to 3,000 degrees centigrade. Those are like radiators, right? So you need to also take heat loss through radiation. So the radiation and convection are heat loss, heat addition is through Goldak. Once you use this, kind of a model and you use your inconel or whatever it is, thermally dependent properties, because thermal softening would happen, and you decide your mesh, whatever is your mesh, and this is your deposition, and that deposition is carried out using something around 6 to 12 beads. 12 beads in this fashion. Track 1, it is done in a zigzag manner. Track 1, track 2, track 3, track 4, like that. Track 12 are being done. Now, if you kind of see, and I do this thermomechanical simulation, when I am running the structural simulations, I have not given any load. If you go back and look at that flow chart, the thermal history is fed into the structural thing, and that creates an equivalent structural load. And based on that, I solve for your temperatures as well as for the stresses, and then I get something. But we have to validate, we cannot tell whatever we want. So what we do is we keep certain thermocouples and measure that one. We cannot keep thermocouples inside because they get burned as we deposit, because we are fusioning the material. So you have to keep it outside, and it has come pretty nicely with our simulations. But we are finite element people. We can always track our temperatures anywhere and everywhere because we have nodal points. So let us look at all these P12 points at the center, this along the center. Let us look at your temperature history. Temperature history looks something like this. This doesn't really convey any damn thing. So what I would do is I will just focus on these things. This gives something, but let me just focus on P6. What is P6? P6 is this point. I want to focus on the thermal history of this P6. When I am trying to deposit on this first track or second temperature increase, it's very far off. But as you come onto the P4 and P5 and very near to the P5 here, you will see a small blip here. Because I am at this thing, P4 and P5, it is the weld track is going from here, I get heated up a little bit. So preheating is happening. And when exactly starts on the P6, you see a boom. Sudden increase in the highest temperature. Then it goes through P7, P8, small blips will happen as it goes back. But since heat is put into it, the heat capacity will be remained into it. So the temperature will remain for longer time unless it gets completely cooled off. Now, what's the big deal of this one? So far, in a material science, I told I'm very close to the material science people. I didn't even honor them so far, right? But this is what is quite most important. If you have a TTT diagram, and if you have exact amount of temperature that is there, you can insert the phase fractions based on that, and those will introduce much more residual stresses that brings it to the things. But this simulation, when we are trying to do, we just gave this insight and moved forward. In the next part, second part, I'll try to give more emphasis to that. And then we took our transient temperatures, measured the deflections using experiments and validated it. It went very nicely. So, well and good. We learned about the simple welding process. This is a warm-up. We have not yet entered into the regime of real additive manufacturing. Please, madam.
So, which tool you are using for simulation?
You can, I use Abacus, you can use ANSYS as well, COMSOL as well, but we use Abacus.
And the question is, where are you placing the thermocouples for validation purposes?
For the validation, you keep it outside your deposition, madam. At multiple locations you can keep. So,
means after the process is over, or
before the process, before you put the thermocouples, put it under the CNC or belt torch. That itself you have to keep it. Before nothing is deposited, you have to keep. You keep on depositing it. As it keeps along deposition, it will read the temperatures that is being fed to the outside peripheries.
Can we see this experimental setup in your lab?
Experimental setup is similar setup is there. I can show it.
Yeah, tomorrow, because
sure.
We need to see like where you are putting, because that
I will ask my student. This setup is removed, but we have two welding VAM devices are there. We'll show the base plates and where the thermocouples are being inserted. That can be done. Sure. Now, this is a warm up because it's a welding. It's almost like a welding. But VAM is not preferred much for two different reasons. VAM is still preferred if you want to make thick components, because the weld torch will give you thicker beads, right? If you are working on intricate components, aerospace components are intricate. So you use another process called as powder-based DED. I am not a powder-based DED guy. Dr. Gopinath is there. We have powder-based DED. We will also show the same things when you come to the AM lab. But there is another best method with the powder is called as powder bed fusion. So from last 7 years we are working on powder bed, and I'll show you some amount of powder bed for you. Now let us get back to the SLM or DMLS, direct metal laser sintering. Right? You can call it as different name. You can call it as SLM or laser powder bed fusion or DMLS. All are equivalent forms of it. Now, so far in the previous simulation, I only warmed you up for thermomechanical part. I only hinted you that the temperatures can connect you with metallurgy, but we never did it. But in actual, any additive manufacturing is thermal, mechanical and metallurgical in nature. Right? So, if you take care of all these three things only, you will predict the things as closely as possible. See, we can say that we can always do the deposition. I have great respect for that. But the resources are quite humongous. I work on C103. 1 kg of powder, when I purchased, is 3 lakhs. Now I think because of all the wars, it is 5 lakhs. Right? You need at least 20 kgs of it. So simply it is 1 crore. right? 1 crore you will get a powder. What you will do with the powder? You have to go have a machine, which is 7 crores. You don't need a machine, you can borrow steel from your colleagues, right? But still they will charge you a couple of lakhs, right? So take them, and once you take them, you print and you have to validate. Always I have huge respect for the fabrication and experimental characterization people, because even small thing goes down, the process stops. However, for simulation guys like us, we can still do something. But in the outside world, you do only simulations, they would not care about us. You need to always talk to them. You need to be in sync with them. So, of late we have started working on our collaborators with who does the deposition and help us in the characterization. We replicate things with the modeling aspects and correlate the things, right? So, simulation alone cannot get you papers, cannot give you insights, because you can always go into a wrong insight. You have to validate it with the experiment. Once you do that, you can go forward in the future for the digital twin. So in our group, we are going for a digital twin for the additive manufacturing. But those research slides, I will only tell after I give you what is the things that goes inside it. Those are only few slides, but that I cannot allow recording because some of them are quite the things. So that's the reason I made a different PPT for it. So let's get back to this. So far what we have done is we took care of this mechanical model and a thermal model. We never did a thermomechanical process. Now we are saying that your volumetric chain strain, your eigenstrains or whatever it is are connected with your metallurgical aspects. So it is three-way connected. So currently in our things, we are doing this three-way connected stuff to predict the eigenstrains or the residual stresses even in the single track. We are trying to address this single track residual stresses. Single track residual stresses are almost meaningless or quite uncertain. But I think with some of UH, they are trying to help us, but it is still rudimentary. Maybe next year if you come, maybe I'll show some residual stress on a single track. But people are interested in bulk. But bulk is actually, it's like almost like reaching the end of the universe. It's so difficult for us. For modeling people, single tracks are much more meaningful. So, in our group, what we are trying to do is, if I want to model single tracks, every single track, and want to build a component which has 10,000 things, even after my retirement, I would not deliver, 100% sure. Because my single track, each experiment runs for 10 days in a supercomputing machine. Then why are we working, right? We are coming up with AML models, we are coming up with scale reduced models, so that we will give bulk properties, and bulk properties will be used to build the component. That is what our aim in the modeling plus things. But those slides I will only show you after I finish these slides, and that I will not allow for the recording. Okay, great. Because they are not published yet. Now let us look at this powder bed fusion method. You have a heat source. Now this heat source is much more complicated than your arc. You can have an electron beam or a laser beam. So we work in electron beam for C103 and tungsten. For Ti64 and IN7 and 8 we use laser methods. Even for C103 we use laser methods. But when you come to this, you start with the powder. The powder packing is important. Powder distribution is important. That is first thing. And the gravity forces are important. Then as this gets into the melt pool, this is a fluid, it starts wetting it. Capillary actions are there. Those are important. And sintering. What is sintering? Sintering is not complete fusion. You partially use thermal effects and lateral compactions to solidify it. So that's the reason earlier we wrote DMLS, right? Metal laser sintering. So that means we don't want to completely fuse the balls, all the grains. That is one part of it, right? Now when this heat source is there, the modeling of a laser beam is different from modeling of an electron beam versus a torch. What I showed torch is only using gold lacquer. Then once it is there, in this, the melt pool has If you look at it like any movies like Harry Potter or whatever it is, in the last he will go and drop the ring inside, you will see it keeps on bubbling, right? You can see even this in here, gas entrapment would happen and it would kind of bubble. That is nothing but your melt pool dynamics because of the Marangoni effects. All this will dictate how the microstructure is formed inside. Currently we are not targeting microstructure. Microstructure is much more, maybe I need to take another berth with this computing. But for us is to predict the melt pool and predict the residual stresses coming from it. And this gets evaporated and then the recoil effects will be there. It's like a steam. When you put it in a tea kettle, you put the lid on it, the water bubbles, recoil pressure will again make the things. So all things keeps happening into it. And as things are happening, some are mechanical, some are fluid, some are metallurgical. Phase transition happens as the thermal gradients are different. Slow cooling will give you something, fast cooling will give you something. All these things are the physics of water bed fusion. If you incorporate all these things, then you can successfully model it, right? So that's what we are trying to do, right? We are trying to do two things. Initially we started doing DED. The first part is DED. I'll quickly show DED is much easier, but the second part is not that easier. The second one is powder bed fusion, right? These two aspects we'll try to do. Now if you want to do a discrete element method, if you want to do DED, again you have to start dealing with the powder. So in powder you need to use not finite element. They are discrete elements. They are like molecular dynamics. But the only thing is these molecules are as big as these grains of micrometers kind of stuff. And they interact, they collide, right? These are pretty weak forces compared to the things. So use mostly collision forces for the exchange of momentum and other kind of stuff. So use DED to model it and update the contacts at everything, and then you try to, let's say if I have to pass it through 4 kind of tunnels, I would do that at different velocities, and then I'll interact with the coaxial laser and melt it with laser melt kind of an interactions, and then you would able to do it. This is one part of it. So we have used for biparticulate and try to come up with different densities and Poisson's ratio to show how things are there. It is just I'm showing basic simulations. These are not publication grade. And then this is first part of it. And then as it gets into it, as it gets into the molten pool, right? The things become so murkier in additive manufacturing. That's the reason I started with the much more simple thing as one arm of it. You start with the discrete element, you get into mold pool, which is fluid dynamics. Once the fluid loses the heat, it solidifies, so get into solidification. So you are in multi-physics because of several things, multi-framework, Lagrangian framework, Eulerian framework, and discrete framework, which is classical framework. All 3 frameworks are required. So modeling is not as easy as you thought of. That's the reason for every 10 people who do complete fabrication and deposition, you rarely find one person doing the modeling, because you have to scratch your head too much to do these things. It's not that quite easy, but it's not quite hard also. It's hard because we don't have good computing resources. It's not hard because we cannot do it. So we do this, we try to get over the melt pool dynamics for that using laser powder interaction, using open foam, and we deposit it. This is what we have shown it here in a continuum framework. As it gets melted and it gets deposited into it. That's what is the DED results. But we don't work much on DED, so I just kept a couple of slides. I want to give a flavor of all 3 methods. The next method, first I have already given VAM, next is the DED. Third one is powder bed fusion. In the powder bed fusion, what happens is, generally we showed this powder falling from it. Generally powder doesn't fall into it. Powder is being recoated into the place. The kind of move force with the powder tank goes up, your stage goes down for some layer thickness. You bring a powder layer onto it and then you sinter over it. So you need to work on the powder layer, and then give physical properties of it and solve for the melt pool for a given heat source, which is a kind of a Gaussian heat source I'm trying to use to model the laser or an electron beam. And then I wanted to capture Marangoni flow. What is the drawback of Goldak heat source is it doesn't capture the Marangoni flow. Why it is important? Because this mixing of molten pool changes the thermal history inside the molecule very significantly, and that is not captured by the Goldak heat source. So you need a source that can be as close as possible to capture that thermal effects within the molecule. So which we solved using the open form fluid dynamics kind of a stuff. And once the fluid dynamics things is done, we know how much mixing is happening, how much Marangoni flow is happening, and how the thermal contours are there. This is much more accurate. Here I have used two different frameworks. Once the powder is there, we started using the overall open form kind of a network. And this is how it is not laminar kind of flow. You can see a lot of turbulence that are there into it, and these dictates the actual footprint of the thermal history. The thermal history inside the melt pool is the most important stuff to have a closer predictions. So that is what we have done it using a simple continuum framework to understand the Marangoni flow inside the melt pool. Now we use this kind of an effects to do a simple powder bed fusion. So this is your powder bed fusion, a particle bed which has been recoated. So first if you want to see the flow chart of this, you put your DM particles, pack it, calculate the forces, that will give the centering forces into it, reach into the equilibrium, and then activate your laser or electron beam heating, do the heating, and as it moves, it will heat subsequent parts, calculate the heat transfer, whatever is happening, and solve for the new particle positions and the nodal temperature and update it. As you keep doing it, you will still get into the molten heat form. The third part, we didn't solve it yet, that is sintering process, but still I will show you what we have achieved. It is not playing up. So it's a solid particle bed and we are heating it. As you heat it, you can see that it is getting into the molten pool. And now it has two frameworks. One, the fluid framework using CFD, one discrete element framework. Depending upon the traverse, you will see the type of, but this is still partially melted, it's not completely melted. So the same thing can be tracked with respect to your, if I'm only seeing the liquid spot, all other things are closed, how the temperatures are there and other things are there, you can keep track of it. So the next part what we are trying to do is, we are working on the sintering part. The sintering part is, now you have molten state, you have lateral forces. For that requires, we have to monitor this one inside an isolated two particles. We need to do it maybe under a FIP or something like that, and see what are the bonding forces when we keep lateral things. Once we only do that experiments, as I said, our AM is not just simply doing whatever we want. It again goes back to the little bit of the characterization side and the fabrication side. We need to fetch the data, put that one. The last part, solidification, is not activated. We are still working on it. Maybe next time I'll show you these kind of things. Once you do that, you will get all three parts of it, which will help you to do the simulations. But what happens is, this simulation will take almost a month. So I cannot rely on this. So we don't use this thing for our ongoing research. We use something else. So I will stop here, and this is the modeling aspect, which is very rich. People coming from mechanical and metallurgy can use it. If you're okay, if you have any questions, I'll interact. Otherwise, I'll show another 5 slides only about our current research. So, questions? don't have questions, I have a small PPT to show. Can you switch off for a while? Because these are not published and some are defense values. Okay. Since you don't have questions, I'll show you here. Laser DAD, which are important process parameters, and some process parameters have covariance between that. Remove that one and looked at which regime they are important to optimize the relative density. The relative density is the first prime. Having less porosity is the first basic aspect of a deposition. This itself is quite extensive work. This has been published in the International Journal of AMD, and now we are looking at the melt pool. After it gets solidifies, you have this weld nugget. Depending upon it, you may have a keyhole mode or a good conduction mode or a balling mode. And currently what we are trying to do is we assume the solidification through thermal gradients, and we are not tracking the microstructures. If you are doing the microstructure single, directional solidification would be very good to make a single crystal kind of stuff. So in modeling, we don't do that one. At this point of time, even in a phenomenological sense, we are only differentiating between a HAZ, well nugget, and unaffected zone. That is what I am trying to do. If I have to have more fidelity, I need to spend more time. For tungsten, my each simulation would run for 10 days in a supercomputer, right? And I will get only one data point, which is of no use for many people, but for us it is of good use, right? But I need that one along with the actual electron beam melting that we have done. We could not actually do it with tungsten. I initially got a coarse powder, non-spherical powder. We got polygonal powder. The material was not flowing. Then we did a dry run, and the dry run itself we could put it in the ACTA. So we got some quite good results from that, and currently we are addressing certain aspects of it. And now we got a spherical powder. The spherical powder, just 25 kgs, costed us only 15 lakhs. You can imagine. And one plate of base plate costs 70,000. So my student goes there, comes back in the evening, says that 70,000 is done, sir. Right? So that's about it. And my computer clusters, each one is, at least a cluster what I have is almost a crore of a cluster over a period of time which I have built. So all these things are high end, and they also give very high performing results if you do it carefully. As I said, modeling alone cannot work. You need to work with the actual people who fabricate, who characterize. Metallurgists plus mechanics can only solve AM problem. Only metallurgists cannot solve, only mechanical people cannot solve. You need hand in hand within both to solve this purpose. But we have our role to play as a mechanical engineers. I hope that's the way I wanted to give. I try to give very simple stuff so that you can grab with the lab to the higher levels. But if you visit our lab, maybe my students will show some more things. Yeah, I'm sorry if I have exceeded. I know my next colleague is waiting for his turn. I'm sorry if I have exceeded.
Sir, can we use this high entropy materials?
You have to qualify. That's what we are doing for simple elemental. See, I had a choice of tungsten alloy and pure tungsten. I thought pure tungsten is better, right? But pure tungsten requires much more high temperatures. Alloying brings down the TM down. So even if an alloy has so much complicated kind of things, high entropy has its own share. I haven't done my homework to comment more on it, but I learned is material science is a magic box. The more you study, the more wonderful things will come out of it.
He's not calling it as a black box.
No. We want to solve the black box. It's a magic box.
That's nice. Nice one. Thank you. So,
thank you. If I exceeded, I'm sorry for my next colleague.
I think, so we have a tea break now, or we have a direct okay, we can have a quick tea break.
Thank you guys for a wonderful opportunity. Thanks to Shaurya.
Going to print functional materials that can be including the semiconductors, dielectric materials, and conducting materials in order to fabricate the electronic devices, sensors, and memory devices. So the field is actually very new, and it has a lot of potential applications. So that includes the sensors, RFID tags, then digital applications, and also smart packaging devices, and for Internet of Things as well. So the advantages here is that it is actually very cheap technique, or in other words, inexpensive technique compared to ultra high vacuum techniques. So you might know about silicon-based electronic devices, so which are actually used for, let's say, high-end applications. So we have silicon, which is high cost and high-end applications, and it has, let's say, very high integration density and very short switching times. So in the sense that very fast switching time we have, and it's actually for very smaller areas, and the substrates are actually very rigid. Whereas the printed electronics actually for low cost and low end applications. This is a complementary technique which is actually having, let's say, lower using printing techniques which are having lower resolution compared to lithography and other techniques, and the switching times are actually not so good compared to the conventional electronic devices. They are actually long in terms of, let's say, microseconds and so on. Then we have the areas which are actually very large areas. So here the advantage is that we can print these devices on very large areas that can be kilometers of, let's say, printing roll to roll technique, and then you can have very wide variety of substrates that can be rigid substrate, flexible substrate, paper quality substrate, right? So the fabrication costs are very low. So if you just overall look at the compatibility, this one, it is compatible on any surface. You can talk about, let's say, printing on a wall, right? You can make solar cell devices on a wall, right? And you can make it on a roof, or you can make it on a paper, on a plastic substrate, which is not possible if you take about, let's say, conventional silicon-based electronics techniques. There you need ultra-high clean room lab, right? And then you need ultra-high vacuum techniques. So it's a complementary technology which is for low cost and low end applications. So there are different preparation methods. So in this case, what you need is a functional ink that needs to be prepared. So the inks can be prepared by using a precursor route. So that means you can actually dissolve the precursor in a suitable solvent, and that will act as a ink. And you can also have something called nanoparticle dispersions. So you can actually prepare the nanoparticles by sol gel or precipitation or hydrothermal route, and these nanoparticles you can disperse them in a solvent using a surfactant. And the stable surfactant will be used, for example, is called electrosteric stabilization and also electrostatic stabilization. So there is a surface charge around the charged particle which will prevent the agglomeration, or there is a surfactant which will prevent the agglomeration between the particles. Then the third one is a combination of both, that is electrostatic and electrosteric combination. So that includes the both the techniques, and that gives a very stable ink. So the main goal here is to prepare the ink which is stable, very long shelf life, that can be, let's say, months of time, and then the ink has to be stable and you can print electronic devices. So now I will talk about the electronic devices that we have made. So what is electronic device? For example, I don't know, people are having different backgrounds, so I will just introduce the electronic device like transistor. So this is called the field effect transistor. So where we have three terminals, for example, source, drain and gate electrode. Then we have a channel which is also called the semiconducting materials, which is actually supplied with the dielectric material. So there is a current that is actually flowing between the source and drain. Here the semiconductor is actually acting the tuning materials, and then you have the dielectric followed by the gate. So you will form a capacitor between the channel, dielectric and the gate, right? So it will actually have a charge accumulation from the gate and from the semiconductor side. Now if you apply the potential difference between the source and drain, the charge carriers will flow, right? So we are actually tuning the charge carrier flow by applying the voltage at the gate electrode. So that is called transistor. It's like, imagine there is a bridge where you can actually have a gate, and whenever you can want to, let's say, open the gate, you can see there is a water flow, right? So depending on how much amount you can open, that amount of water flow will. So similarly here we can actually control by applying the field at the gate electrode. So that will control the charge carrier flow. So these transistors are actually the building block for all the electronic devices like computers, smartphones, displays, and all the electronic devices that you can imagine. And on the other hand, so we are using oxides. Oxides are nothing but this indium oxide, zinc oxide, indium gallium zinc oxide, and so on. So you may wonder how oxides are semiconducting in nature, right? So there is something called defect. So the defect is in this case oxygen vacancy. So oxygen vacancy, each oxygen vacancy will donate 2 extra charge carriers. So that leads to the semiconducting behavior of oxides, and they also have the band gap. So because of this, let's say intermediate band gap, which is around 3 electron volt, and because of oxygen vacancies, you have the charge carriers. So these charge carriers are mobile when you apply the field. So that's why we are using the oxides, and they're actually transparent to the visible light. So you might have seen that there is a transparent solar cell or transparent electrochromic windows. So I don't know whether you traveled in a flight, most of you might have. So there's something called smart windows, right? Depending on the light on the outside, the window color will change. If the extremely sunlight is there, it will actually become dark. So these are called smart windows or electrochromic windows, right? So again, they use tungsten oxide as the material. Again, because of the oxygen vacancy defects, this will act as an electrochromic material. So oxides has this beautiful property of semiconducting nature, which we can also use and then print. And they are also non-toxic and very easy to fabricate. So then comes the dielectric material. So that's the dielectric that I'm talking about. Is very important. So normally people use silicon dioxide as a dielectric material, but you cannot print them at room temperature. You have to actually make either particles or you have to do high temperature processing. On the other hand, we can use something called electrolyte, which has both cation and anion. And when you apply a field, let's say the yellow bar is the metallic electrode and you have the anion cation in the electrolyte. When you apply the field, there is a Helmholtz double layer which is formed, right? So this Helmholtz double layer actually having very short distance around 1 nanometer. So that means you are having a parallel plate capacitor with very short distance. So that gives very high capacitance and that leads to low operating voltages as well. And it also leads to very high charge accumulation in the semiconductor. So because of these reasons, we are using electrolyte as the dielectric material. So the important ones are in this case, source drain gate are the metallic electrodes, but the important ones are the semiconductor and the dielectric. So semiconductor is the oxide semiconductor and the dielectric is the electrolyte material. So these two we can actually print. So then we can actually make two different types of semiconducting devices. So one, as I told, you can take the precursor, which is let's say indium chloride dissolved in a solvent, and then you can print and heat it. So the indium chloride will convert to indium oxide, and this will give a very high dense film quality with less porosity. On the other hand, you can actually use the nanoparticle approach. So you can prepare the nanoparticles, you can actually use the surfactant to get a stable ink, and then you can print. So you can print the nanoparticles. But the problem here is that there is a surfactant between the particles that will prevent the charge carrier flow. So that means we have to remove the surfactant by applying some, let's say, external treatment like temperatures or by photonic curing techniques. So in this case, we are using a novel photonic curing technique, and we are curing this particle, and then we are actually densifying the films and improving the charge carrier transport. That also improves the performance. So both the methods I have discussed in my fabrication route. So the fabrication steps involves the precursor, which is for example indium chloride with the solvents, or the particle approach, which is indium oxide nanoparticles, which we have prepared by solder route and dispersed in water with a sodium polyacrylate as a surfactant. So we can take the glass for the precursor route and PEN, which is a plastic substrate for the nanoparticle route. Then we do lithography. After doing lithography, we get the pattern structure like that. Then we print the precursor or the nanoparticles, followed by annealing of the precursor. In another step is that we are actually curing the nanoparticles. So I am showing you both the techniques in parallel here. So followed by printing the electrolyte, so which actually forms the final transistor. So these are the steps involved. One, you take the substrate, then you do the lithography and deposit the the electrode materials, followed by the deposition of the precursor or nanoparticles. The precursors are treated in a high temperature, and then the nanoparticles are treated at room temperature, but using a photonic curing technique, followed by printing the electrolyte. So that makes the completion of the transistor. So before I go for the electrical characterization, we have done the structural characterization. So the indium oxide precursor, we heat at let's say 300 and 400 degrees centigrade. What we observed is that at 300 degrees centigrade, we are forming the indium oxide, but there is also secondary phase, which is indium oxychloride as the secondary phase which is present. On the other hand, 400 degrees centigrade, we don't have any secondary phase, it is purely crystalline indium oxide. That means we need around 400 degrees centigrade to convert the indium chloride to indium oxide semiconductor. Then we have done the SEM and AFM imaging. So SEM shows that the particles, the films are actually very large, having a grain size, and also they have roughness which is around 8 nanometer, which we confirmed with AFM. So this roughness is actually very, very important. You should have actually very low roughness. In fact, people are talking about 1 nanometer roughness. The reason is that the interface between the semiconductor and dielectric, okay, has to be very smooth. If it is not smooth, it will actually act as a trap charge center. So if it is charges are trapped, then the performance will be affected. But however, we are using the electrolyte. So in this case, the roughness doesn't matter, which will show in the TM imaging also. So we have done the TM imaging for the interface. So this is the indium oxide at the bottom. Then we have the composite solid polymer electrolyte. So you can see that irrespective of the roughness, the electrolyte is actually flowing, right? That means we can actually have a very smooth interface that leads to efficient charge transport, which we confirm with the TM and followed by the electrical characterization. So in the electrical characterization, what we observe is that this is nothing but the gate voltage between the source and the gate, and then we have the drain current, which is actually the source drain current. So the square root of that will give you the threshold voltage. So the green one is actually showing the change of drain current with respect to the gate voltage. So initially you have this off state, and then once the channel is formed, then you can see that the current is actually rising. And if you take the on-off ratio between these two, you will get something called the on-off ratio, which is around 10 power 5. And then the red current is actually showing the leakage current, also in this case displacement current, which is actually few nanoamps to 10 nanoampere. And then we can see the output characteristics, which is nothing but the ID versus VD. ID is the drain current and VD is the drain voltage. Okay, so normally what you see is that there is a ohmic behavior followed by there should be saturation. That's the ideal behavior of a transistor. But we are observing non-ideal. In fact, this is called a negative differential resistance. Although you are increasing the voltage, the current is actually dropping. So what is the reason for this? So then when we looked at the structural characterization, we found that there is a secondary phase which is indium oxychloride, which is acting as a charge trapping center. So that means the charges are trapped even when you apply the higher voltage. That leads to the decrease in the current. On the other hand, for 400 degrees centigrade, you can see that there is a nice ideal behavior having the linear behavior followed by the saturation. So this shows that we are getting very good transistor when the films are annealed at 400 degrees centigrade, and this also confirms that pure semiconductor is required to get a good performance of the transistor. And interestingly, the ANRF ratio is also significantly higher. If I compare both the performance in this table, what we can see is that ANRF ratio is higher for 400 degrees centigrade, around 10 power 7. And another important parameter is called sub-threshold swing. That means how quickly the device can be switched off. So that is actually 60 millivolts per decade is the theoretical limit, and we have reached very close to theoretical limit of 68. It's a very good value of the sub-threshold swing. Then the mobility is nothing but how quickly the electrons are transporting from source to drain, right? So this is actually significantly higher than, in fact, one of the polycrystalline silicon has 100 centimeters square per volt cycle. So we have reached to the polycrystalline silicon levels using oxide semiconductors and electrolyte gating concept. And we also made the logic circuit. So you might have heard about logic gates, and logic gate, not logic gate, or logic gate, and so on. These are the logic gates where you can have different transistors which are combined in a different way. So in this case, we are talking about something called CMOS inverter, complementary metal oxide semiconductor inverter. We have made them using the oxide precursor route, and where the precursor are annealed at 400 degrees centigrade. So the interesting circuit is that you can see that these are the NMOS transistor and this is a PMOS transistor. You can connect both of them, and where you can apply the input voltage, and you can connect the two drains where you can actually have the output voltage, and the NMOS is actually grounded, and the PMOS where you apply the drive voltage. So in this case, what happens? At any point of time, either NMOS or PMOS is off, except that during the transition. So that means what? The current will be, let's say, drawn very less, and you can have the inversion of the logic signal. So how we can do that? For example, if you have a lower input, the PMOS will be off, on, and the NMOS will be off. So that means the VD will be directly going to the V out. If the input is higher, then the PMOS will be off and the NMOS will be on, but it is grounded. So it will entirely pull it down to the ground. So we can see in terms of the output characteristics of that. So this is the geometry of the transistor. So we have used the copper oxide as the p-type semiconductor and indium oxide as the n-type semiconductor, and we have done the electrolyte gating, and then we have connected the input and output, and we measured it. So what we can see here is that so this is the output voltage, and this is the input voltage, and this is the drive voltage. When the drive voltage is 1 volt, you can see that this is the input voltage which is lower. We are talking about low input voltage, but your output is actually equal to the drive voltage. Okay, that means what? For a lower input, you are getting the higher output. Okay, and vice versa. And here you can see the input is higher. The input is, let's say, 0.5 to 1 volt, but your output is actually close to 0. Okay, for your higher input, you will get the lower output. Okay, that is called a NOT logic gate. So we can make the NOT logic gate using the oxide semiconductors. This was the first demonstrated one, and we have published this in a small journal, which is a very good journal of Wiley. So then we also made the flexible electronics using the nanoparticle route. So in this case, we have taken the flexible plastic substrate, and then we have done the lithography and then the deposited nanoparticles. But we have cured those nanoparticles which are present at the semiconductor here. We have cured those nanoparticles using the photonic light. And remember that we are using the plastic substrate. If the light intensity is very high or the energy is very high, then it will burn the plastic substrate. So you have to use the very, let's say, short laser pulses or the light which is having lower wavelength and for short time. So we have done that, and using two different techniques. For example, UV visible curing technique, and again we measure the transistor behavior. We are getting a good on-off ratio and also the output characteristics. Then we have used something called laser curing, UV laser curing, and we have measured the transistor behavior. And the comparison of these two is that in case of UV visible curing, we are getting 8 centimeters square per volt second, which is the performance parameter. Then the UV laser curing, which is actually 12 centimeters square per volt second. So that means UV laser curing is doing better than the UV visible light, because this is actually having the unique wavelength, that is actually having a very broad wavelength. And we have done the XPS, we can confirm that surfactant is efficiently removed, and we have done the UV laser curing. And if I compare without curing the mobility is actually 0.95. So it's a very low mobility. So we are getting higher mobility when we use the UV laser curing. So this also we have published. Then we have used so far oxides, but there is another material which is called organic material. So we know that organic materials are actually insulating in nature. Many of the organic materials are insulating in nature, right? These are actually used for insulating purposes. But there is something called a conjugated semiconductor. So there is something called pi-pi conjugation. You have alternated single and double bonds. That leads to delocalized electrons. Okay, so those are the organic semiconductors that are being used, and we have done for gas sensing applications. So what we can see here is that we measured, for example, ethanol with respect to the concentration, different concentration and the time. So these are percentage response, the change in the current by initial current, and this is the time. So initially when we apply 600 parts per million, there is a small response. As you increase the concentration, you can see that the response is actually increasing. So we have done with other analyte molecules also. So we have done with the octanol, and we can see that the concentration levels are significantly better now. We have 3 parts per million. That means we can detect very low concentrations of octanol compared to ethanol. So we have done for octanol, butanol, ethanol and methanol. And when we compare the sensitivity, we can see that octanol is having better sensitivity compared to methanol. So the reason is that the semiconductor is hydrophobic in nature, and when we compare the hydrophobicity, octanol is having higher hydrophobicity compared to methanol and ethanol. So the hydrophobic interactions are leading the better sensitivity in case of organic transistor. We have done similarly for ketones as well. So ketones, in this case 2 octanols having very a low concentration of detection, that is 35 parts per million. Then we have done acetone and butanon also, where the concentration level significantly higher. So the improvement in this, again we can see that there is a hydrophobic interaction between the organic semiconductor and molecules. So we have done the esters as well. So esters also butyl acetate, isoamyl acetate, and also ethyl acetate. So in all these cases, what we can see is that if you increase the alkyl chain length, the sensitivity is higher for the organic semiconductor. So that is because of the hydrophobic interactions. So the reason to do this alcohols, ketones and esters, you might know that there is a metabolic reaction happening in our body, right? Based on that, you will have emission of different volatile organic compounds from the person. So one of the famous example is, if a person has diabetes, the person will emit acetone in higher levels, right? If you put a sensor at the, let's say, nose, and if you can detect the concentration of that acetone selectively, then you can say that the person is at the critical limit, or has the diabetes, or he is going to get the diabetes. So you can have the preventive diagnostics. So when you detect the volatile organic compounds coming out from the human breath, okay. Not only that, there is a alcohol test that can be done for other things like fruits and vegetables also. Then another project we have done with, let's say, the Unilever and Pragmatic. So this is about making the organic transistor to treat the body odor compound. The main thing is this about IoT to recognize intelligent activities. So one of them, the request was, can we detect the body odor which is coming out from the human armpit? So this is done for several reasons. I am not able to disclose here, but we have done that, and we will show you the analyte molecules are not disclosed because of the confidential nature. But we can detect parts per billion. So we have got 3 analyte molecules which are related to the body odor, and we can detect, let's say, 290 parts per billion in analyte 1, and analyte 2 is 88 parts per billion, and analyte 3 also 88 parts per billion. So we are able to detect parts per billion of body odor compounds. So then we check the let's say selectivity using 2 different sensors, sensors A and sensors B. Analyte 1 is higher sensors, higher response for sensors B, and vice versa for analyte 3. So you are getting higher response for sensors A. And analyte 2 is almost same for both the sensors. So that means what? By varying the organic semiconductor, you can have selectivity, and by tuning the functional group, you can have the higher sensitivity also, like parts per billion of detection. Then we have tested with the real body odor sample, and we can actually detect the low body odor and as well as the higher body odor using 2 different types of sensors. So this can have some commercial applications later. the last topic in today's discussion is that we are also working on something called mimicking the human brain, or something called RAM devices, resistive random access memory device. So you might know that traditional computers have something called von Neumann architecture. So what is von Neumann architecture? There is a separation between the processor and the memory. So the data has to shuttle between these two. And the latest AI computers actually are limited by this data shuttling, because there is a large amount of data that needs to be handled. So people are looking for alternative electronic devices, and they are actually making on different devices. One of them is something called RAM device. So this is the human brain which has billions of neurons, and it actually does both processing and memory at the same time. We don't have the von Neumann architecture. We have something called parallel computing or in-memory computing. That's the beauty of our human brain. So people are trying to mimic this human brain, and what we have is the neurons. So presynaptic and postsynaptic neuron, there is a neurotransmitter which is actually going between these two. So that actually leads to the processing and the memory storage. So that you can actually mimic using something called top electrode and a bottom electrode, and in between the oxide layer where you can have the conducting filament. This conducting filament, you can imagine like a parallel plate capacitor, right? You have two plates and in between the dielectric. Now, if you have a simple capacitor, then the charge will be stored at the both plates. But in this case, what we are forming is that there is a conducting filament. That filament is either a metallic filament or oxygen vacancy filament. This filament you can form and break it, let's say 10,000 times. Very reversible filament formation. That leads to change of conductivity, and that also leads to the memory behavior. So I will show you how it can be done. So we have done using oxides. So again, we have taken a 6-inch silicon wafer. We have done in the clean room. We have deposited the bottom electrode followed by the oxide layer. Again, everything by lithography process. I am skipping the intermediate. So finally, we have done the top electrode. So you can see that the 6-inch wafer we can make. Let's say, I think I forgot the exact number. It's more than 1,000 devices. You can make such a large number of devices, and at every intersection you have a RAM device, which is a resistive random access memory device. So then we measured the characteristics. What we can see initially. You can see that the resistance is actually higher. As in this case, I am talking about current. So the current is actually very low, right? Once you go, let's say in this case of negative voltage, as you go higher of negative voltage, you can see that there is a sharp increase in the current. This current increase, you can see that there is a conducting filament formation, right? If the filament is formed, then you can see the current increase sharp. Then if you again sweep in the opposite direction, so it will, now the current is actually going in a different path. Why? Because initially you don't have any filament, but after that you form the filament at this position. Now you can see that it has a low resistance, or in other words, higher current. And if you sweep in the opposite polarity, the current will still be higher, and at some point the filament will break. Then it will come to the low resistance, or in this case, lower current path. So any hysteresis, you can imagine like magnetic hysteresis also. These are also electrical hysteresis. Any hysteresis means there is a memory behavior. Right? So how we can understand this? For example, if I want to hold, this you can call as logic 0, and this is you can call as logic 1. So if I want to hold in this state, I can hold it forever, or I can hold it forever in this state also. Okay? So in between, what you have is the memory behavior, and you can have different logic states also. So this one we have done for let's say several cycles, and we can see that more than 100 cycles also we have done, and the curve is actually very stable. So that stable performance is as required. Then we have measured the intermediate states also, just like humans have the long-term memory, short-term memory, right? So similarly, you can have different states in the devices also by varying the resistance, by varying the reset voltages. Then we have seen that each state we measured, and they are stable for more than 1,000 seconds. So not only that we got the multiple states, the other thing is that these states are also stable. So then we have measured with respect to different pulse width, how we can vary the, let's say, the on-off ratio. So in case of lower pulse width, the on-off ratio is lower, but as you increase the pulse width, the on-off ratio is also increasing. And then when we show, this is the important graph. So you can see that you vary the pulse width of 1 microsecond, 10 microsecond, and 100 microsecond. So for 1 microsecond, the on-off ratio is just 1.2 times. For 10, it is 7.4, and for 100, it is 12.7. So you can enlarge the memory window by changing the voltage pulse width. That is because the change in the energy, that is changes the, let's say, the filament dimensions. So that leads to change in the on-off ratio. So with this I conclude. We have done oxide transistors. So the oxide transistors can be used for different applications of transparent devices and also sensors and so on. Then we have made the logic circuit, followed by we also made the flexible electronic devices using oxide semiconductors. Then we have made the organic transistors. These organic transistors are useful for detection of the gases and volatile organic compounds and gas sensing applications. The final device is about the memory device. So this memory device is non-volatile memory device, which is used for neuromorphic computing application and also AI. So with this, I thank my previous group members and also funding agencies, and I thank you all for your attention.
Thank you.
Any questions? I can take.
Floor is open for discussion.
In lithographic process, you are one of the slide.
Yeah.
Which type of lithography? Ion beam or electron?
We have used the electron beam lithography. The first one is the electron beam, and for RM device we use the photolithography technique because the area is very large. So we have to use photolithography.
Okay, what instrument that you have used for a measurement of a stone like the telling gas?
So we have made a homemade gas sensing setup using mass flow controllers and volatile organic compounds are bubbled. So you actually flow the air into the, let's say there is a beaker, you put this resistor for example, then you flow the air into it. So you create the bubbles, right? So that vapor we will collect it and feed into the sensing chamber. So sensing chamber is also homemade, and MFC we connect it and dilute to get different concentrations. So we calculate using the saturated vapor pressure, the concentrations of these gases.
You use the resistance measure or the
Yeah.
resistance?
We measure the current and then we calculate what is change in the resistance. Yeah. So you have a base current and then after exposure, what is the change in the current.
So is in your lab only you have a lithographic technique for printing the material or other technique you have?
In our lab we have the, me and Chandra, we have the lithography technique, and our lab we have printing technique, and we have gas sensing setup, and also probe station and SMU to measure the electrical characterization. So in-house we can do all these devices, and we can do the measurements also. And then there is a department facility for characterization like XRD, SEM, TM and other things.
So material are you synthesized or somewhere?
Sorry madam?
Material, indium material. Your lab you said?
Yes, we made the material by ourselves.
Can we get detailed elaboration? I mean,
Sure. Okay, if no more questions, then thank you very much. Probably we can have early lunch.
Yeah, so we can have a early lunch. I think thanks to you, we could have.
I finished very early.
Lunch on time, not early lunch. Yeah, we will have lunch on time. Thank you, Professor Suresh. So we will be meeting. So we will now stop or depart for lunch, and after lunch, the next session will start at 2 p.m. here only. And there are 3 talks, okay, organized for you. First will be on microfluidic based synthesis of nanomaterials. Second will be by Shubhadeep Chatterjee on transmission electron microscopy. It's a characterization basically technique. And third one is another characterization technique, atom probe tomography. The talk will be given by Dr. Rama Srinivasa Varanasi. The first talk will be Dr. Sunanya on nanomaterial synthesis for microfluidic devices. Okay, so thank you. So you know where is the lunch, right? Lunch is organized in the place guest house where you are.
start the recording, but when it comes to speak it live, pointer. Sign it off. That's the pointer.
ఇప్పుడు లైవ్ రాదు మరి
Hello. Hello. So thank you very much. So I hope the morning session was useful and you had an interesting discussion. What I got as a feedback is there are too many different topics, right? And it might be a little disparate. So please bear with us, right? So we're trying to give you the whole gamut of what is possible. And at the end of the day, perhaps today I'll be back, right, around 5:15 after the session is done. And then we'll have a discussion on how, on one-on-one literally, as a group, to see how we can basically work together in a better fashion, okay? So the second post-lunch session, we have 3 talks. The first talk is by Professor Sohanya from Chemical Engineering Department. She's the expert of microfluidics. And she'll be talking about microfluidics for nanomaterial synthesis and assembly. Please feel free to ask questions. This is a workshop, not a lecture, so the more you interact, the better it is. Thank you. Sonia, the floor is yours.
Thank you, Shaurya. Good afternoon all. I'm Sohanya, Chemical Engineering Department, and my area of interest, as Prof. Shaurya pointed out, is microfluidics. I'm not sure how many of you are well versed or know about microfluidics, so I made a brief overview of microfluidics. So most of the lecture today will be about what developments in the area of microfluidics, and then because this workshop is about particles, I'll be talking about particle synthesis that we have done in our lab also. So is that okay? So that's what will be the overview. This is how I'll proceed. So this is kind of because I teach class on microfluidics, so many of the slides are from my class. So in case you have any questions, you can stop me in between and we can have a discussion. So I don't want to talk more about the application, which is particle synthesis. Rather, I would like to spend a lot more time on microfluidics as such, because understanding that will help. Application comes later. So with that, we just start off with the introduction to microfluidics. So as the term indicates, microfluidics, right? So it basically deals with fluids of very small volumes, and we manipulate these fluids in channels of very small dimension. As you can see here, these are some, you must be familiar with the term lab-on-chip devices. So lab-on-chip works on the principle of microfluidics. So these are some devices, lab-on-chip devices, where typically reaction or any assay, for example a biological assay, happens inside the channel. So these lines that you see here, they are the channels. So the lines here, they are the channels through which the fluid actually flows. So those small lines are of dimension, micron dimension. The width of these channels are 1 to 100 micrometers. They can go up to 600, 700 micrometers also. And nowadays we are also using millifluidic channels, channels of dimension 1 mm, 2 mm, 5 mm, cubings. So these also follow the principle of microfluidics, though we call them millifluidics. So the characteristic dimension, what I mean is the width of the channel and the depth of the channel. So the width and depth of the channel is in the micron and milli range, but the length can be as much as possible. As you can see here, the length of the channel is all the way, it can be centimeters, it can be meters, it can be characteristic dimension. What we are interested is the width and the depth. So if you take a cross section, the depth and the width of the channel, that is what we are talking about. So because of this small dimension, there are a lot of parameters that we can control in these channels, and that is why they have become very a lot of people are using them right now in several applications. So this microfluidic devices are a result of miniaturization. So if you remember, long time back we had huge TVs with a huge, the huge TV. In our grandma's house, if you remember, and the telephones were huge. So now miniaturization started basically because semiconductor industry had a lot of developments, and we started moving from, we started having transistors, we started having microprocessors. So we were able to put a lot of resistors and all these circuits inside a diode or whatever you call them inside one small device. So miniaturization has helped, and it has evolved over a period of time, and microfluidics is a consequence of this miniaturization. So we are able to make these devices, micron sized devices, as a consequence of miniaturization. So that is where we are going next. How do we make, what are all the devices available? So we can make metal devices. So you basically, you see the channels here, so it's an open channel, and then you bond it with another device on top. So you will have, let's say this is the bottom side, this metal side, and I will have channels that are inbuilt in them. So you will have depth inside, and then I close it with another device, another plate or a sheet on top, and that is how you have the 4 sides. So 3 sides will be on this lower surface, and the 4th side will be the closing, the top cover. So that is how you get this channel, and this has been used for methanol reforming. It's a metal polymer channel, and you'll have glass. You can make glass reactors also. You can make these by using etching techniques, KOH etching. So fabrication techniques are borrowed from silicon industry, and that is how we have been able to make these reactors. In our world, chemical engineers, we call them reactors, where chemistries can happen. For biologists, this is a vessel or a small assay unit where cell cultures can happen, or a small assay can happen. And you can have metal reactors for high temperature chemistries, or for chemistries that are very sensitive to surfaces. And you can also have silicon and Pyrex reactors. But then with the advent of photolithography, if you know, there are clean rooms that are now there where you can do lithography. So photolithography is one technique which was developed recently, if I may call that recently, around 1995s or so. And now we are able to use polymer microfluidic devices. These can be fabricated in the lab within a day or so. The previous slide where you saw glass-based reactors, metal-based reactors, you can fabricate them in a month. It takes a lot of time. But these reactors, you can fabricate them within a week. Polymer-based reactors. Polydimethyl siloxane, PDMS, it is the most often used material for such microfluidic reactors for research purposes, because it of a lot of its properties, and also it's a use and throw. We just make it, we test our experiments, and then we throw them. So these are some polymers that have evolved over time, and now there are also what are called paper microfluidic devices. All you have to do is a filter paper in the lab. You just put hydrophobic lines, and then your device is ready. A best example of this is pregnancy test kit. I'm sure many of you might know what a pregnancy test kit is. It's a paper microfluidic device basically. You just put a drop of urine, and you can see the flow of the urine through the paper channel, and then you can it will detect if the person is pregnant or not. Similarly, COVID-19 we had antigen test kit which works on the same principle. So paper devices are very commonly used, and these are also working on the principle of microfluidics. And we have now moved on to 3D printing. So from photolithography, where we need a huge clean room to actually fabricate our devices, we just need a day. We can do a design in the morning, give the design to our 3D printer, print the device, and start using them in the evening to test our devices. So fabrication has become very, very easy these days with the advent of 3D printing. So with that, we have done with the device, what are all the different kinds of devices we use for making microfluidic reactors. Any questions so far?
Can we have more examples from the microfluidics?
Sorry? More examples
of real life applications where we can use this?
I didn't put it there because more examples, when you say, it's more or less biology. So I'll have to go into a lot of biology because microfluidic devices, mainly because of their applications, they are typically used a lot in biological applications. Chemistry, yes, but not as much. It's not commercialized because we are still using it at lab scale level, and we haven't gone to, we are still doing flow chemistries, we are still looking at the possibility of taking it to a large scale production, but we are still not there yet. But biology, lots of devices are commercialized. So if I start giving you examples, we'll move into biology. So that's why I toned it down. Yes, everything. Fabrication, so biology, the advantage is more or less they use PDMS reactors. You want them to be transparent, you want them to be sensitive, allow them to grow cells, and also you transparent because you will have to image and see what is happening inside the chamber. Are the cells growing, are they dying? You want to image fluorescence and all that. So that is one. And you just want them to be use and throw. So one day you do the experiment, then you throw it off. And then you want to actually see the how the cells are responding to some input and output, some cues that you are giving. So PDMS satisfies most of the purposes that biologists look for. So PDMS is what is being used. But once you come to commercialization, PMMA, POs, PC, polycarbonate, polymethyl methacrylate, those are the materials that are being used. Chemistry, there are some that are coming up. Maybe I can give you a paper that has some commercial devices.
Initially, I thought of by looking at the pictures, it might be very much useful in semiconductor-related applications.
This is bought from semiconductor. Yes, sensors specifically, yes, it is used for sensor applications. Definitely yes, but we are not going into that. So yes.
In test that paper they have used, that is a filter paper or some plastic material?
It's a filter paper inside. It's called lateral flow assay. It works in the principle of lateral flow assay. It's a filter paper inside, but it is covered with plastic.
What filter paper? One or two?
That I wouldn't know. Depends on the quality of the test, right? Different companies use different kinds of papers, and also the strips that they use are also different.
And what about that we are using the paper for a pH measurement?
Yes,
so that is also
lateral flow assay. The capillary helps in pulling the fluid, so then microfluidic comes into picture. Basically you are manipulating fluid at a very small scale. That's all. That's microfluidics. So capillary action is microfluidics, the principle. Okay, so then can I move on? So some of the properties that I wanted to highlight for microfluidics is, do we all understand Reynolds number, Bond number and all that? Okay, so then you might understand that we are talking about very small scales, right? So Reynolds number, which is it's a non-dimensional number used to typically characterize fluid flow, and it's inertia versus viscous. Okay, and if you look at the calculation, and if you just give rough numbers just for plain water, Reynolds number will never be more than 10, however much high flow rates we use, because of this D here. The characteristic dimension is in microns, right? Microns 10 to the minus 6. So therefore, your Reynolds number is always less than 10. It can never go more than that, which means turbulence is just impossible in microfluidics. We cannot have turbulence. And always your flow is laminar, streamline motion. The second thing is Bond number. As you can see, the number is 0.01. Rough calculation, roughly. It is again very, very low, which means gravity plays nil role in microfluidics. There is no effect of gravity. The other number that we are interested in is Weber number and capillary number. So these come into picture when, specifically capillary number, they come into picture when we are using multiphase microfluidics. So as you can see, capillary is viscous over interface. Likewise, inertia versus interface. So both these are extremely low, which tells us that interface plays a very important role. Surface come into picture a lot more. Basically, surface area to volume ratio becomes high when you go down in dimension. Because of this, the surface becomes a lot more active, and so a lot of things that are possible in microfluidics is because of this surface activity. That is why it is very, very, so as you can see, I have written here capillary forces, as you said, paper microfluidics, capillary forces are really important, and surface play a very important role. So then other properties that we are looking at, why is microfluidics actually so famous and why everybody is going to microfluidics is because of the heat and mass transfer. If you look at the characteristic equations for heat and mass transfer, heat transfer, it is proportional to d square, right, length, and I am going down in length, so 10 to the minus 6 if I say microns, and it is of the order of 2 times 10 to the minus 6, so it is 10 to the power of minus 12. So heat transfer time, this is time for heat transfer, is reducing that much, which means your heat transfer is so fast. Time for heat transfer is going down by an order of 10 power minus 12, which means your time is rapid. Within a few seconds, heat is transferred. Likewise, diffusion also, it is directly proportional to L squared. So this is L squared over D, this is diffusive coefficient. Radial diffusion, again you have a component D squared over 4D, capital D is diffusion coefficient. So the D is the small d, or the L is the characteristic dimension that we are talking about, because it is in 10 power minus 6 of the order of 2, 10 power minus 12. Again, the time for diffusion is extremely fast, which means diffusion is very fast. So because of these, heat transfer, mass transfer is very, very fast. So therefore, we can do a lot of things in micro scale that are not practically possible in a huge reactor. So this is one advantage. And again, reduced reaction time, because your mass transfer is very fast. Reaction time also goes down. This is proven. A lot of papers in chemistry, flow chemistry applications, they show that reaction time has gone down. So kinetics actually change. If it is very fast reaction, we are not talking about a slow reaction. If it is a very fast reaction, kinetics actually changes in the micro scale. But the one disadvantage is pressure. The pressure drop in a very small channel, if you see, the pressure drop is directly, inversely proportional to R to the power 4, which means if I am going down in my dimension, R is minus 6, then R power 4, so 6 times 4, right? So it is extremely high pressure drop. So if I make the length of my device to be a few meters, my device will break, because of the high pressure that we are generating within the device. So this is one disadvantage that we'll have to play around within microfluidics when we are designing a reactor. We'll have to, but then this is overpowered by the other advantages, which is why we are, a lot of applications are there for microfluidics.
What about the effect of temperature?
Temperature is heat, right?
So both may shoot up or shoot up?
Yes. Heat is transferred very fast, provided the K is also good. Conductivity coefficient is good of the material. Like for example, if I use silicon, heat transfer is quite fast. But then if I use PDMS, it is comparatively slow. But because the reactor itself is small, it's still better than batch, better than a large scale system.
What is N and lambda?
Sir, that I'm just talking about order of magnitude, so we don't need to think about that as yet.
It is not Nusselt number.
This one, NU, yeah, it is Nusselt number.
Nusselt number.
Yeah. But I am interested in this one only. It is Nusselt number, heat transfer, right? Yeah. So,
one more thing.
Yes.
If there is any pressure and temperature drop suddenly happens, then that is kind of a throttling process, right? That means the enthalpy of the reaction will be constant or zero change. So that doesn't affect any kind of properties.
sir, it depends on what application we are using it for. So if you are using it for throttling, we are using a very small, usually throttle is through a very narrow channel. And if you are introducing a narrow channel, definitely there will be throttling happening, but then you need to see what temperature and pressure we are working.
That's why if there is a pressure drop, and you are also mentioned there is a high heat transfer.
Yes,
then you can
no pressure drop, increase in pressure, high pressure, extremely high pressures.
Okay.
The delta P is high, pressure between inlet and outlet.
So there is a pressure and temperature variation happens suddenly.
Yes.
Then you can have
of course, yeah. You can. That is why it is. So it is application based. You will have to decide what you want, what are the conditions, what are the parameters, and then design your reactor. We'll have to be aware of all that. Definitely. So then, just to give a few examples of these, all these papers, if you see, they were published in the early 2000s, and they were all highly cited. They're all Nature, JACS, Langmuir, Science. So I just wanted to pick a few examples here and there to see how some of these microfluidic experiments are really giving us some very good insights that were not possible before them. So for example, if I take this case, okay, this is a Drosophila egg. Drosophila melanogaster is a fruit fly. So they wanted to study how the temperature has an effect on the embryonic growth of the egg. Like if I supply hot temperature to the egg, will it affect the growth of the egg and how? And then if I supply cold, what will happen? So in a typical experiment, in a batch experiment, the egg can either be subjected to a hot or a cold temperature. It cannot be subjected to both the temperatures. However, in this case, microfluidic device, they designed a Y-shaped device, and then you have a hot fluid coming in from one side and a cold fluid coming in from the other side. Yes, heat transfer is fast, diffusion is fast, but then there is an interval before which the diffusion can penetrate through the entire channel. So there is a time frame. We'll come to diffusive mixing in a bit, in a few slides down the line. But for now, the temperature can actually be different at the interface, and you can actually maintain a high temperature on one side and low temperature on the other side. So this way they put an egg here, and they could actually subject the egg to both high temperature, low temperature, and a gradient of temperatures along the egg surface. And so the egg was exposed to a lot of different temperatures at the same time, which then helped them to understand the embryonic development and what is affecting, how the temperatures is affecting. This is something similar to our body. Our body goes through a lot of different temperatures at different times. So that is what this experiment was about. You cannot do this in a simple flask. It's just not possible to have both hot and cold fluids at the same, being exposed to a small egg, small fruit fly. The other experiment is this one here, which was done by John et al. And this is Whiteside's group. He's considered to be father of microfluidics. And in this group, they were the first one who introduced PDMS based microfluidics. They were the first one who introduced paper microfluidics. And this is one such very, very useful experiment that they have published. And what this says is you can actually generate concentration gradients. You can have 3 different fluids, and they can automatically generate different concentrations across a channel, across a single channel. So this is because of the diffusion, effect of diffusion, and because the flow is completely laminar. Streamline mixing is very slow. There's no turbulence, there are no eddies. So streamline mixing is slow. So therefore you can actually have gradients of concentration across a single channel. And this is useful in multiple applications, specifically in biology, when you are doing high throughput testing. For example, if you want to test a drug, if it is effective, and you want to test it on multiple concentrations, then all you have to do is give the one drug and one diluent. Then they will be mixing in different gradients, and you can test it with different samples. So this is another method in which they have generated concentration gradient. Another example is droplet microfluidics. I'll be talking about this in detail later, but to just give a glimpse. So in this, where you have drops that are formed in a continuous phase. The yellow one here is oil, and the drop is in aqueous phase. So here what they have done is they have oxygenated the continuous phase and deoxygenated the dispersed phase. And because of the oxygen partial pressure difference, there is a transfer of oxygen from one phase to other, and this helped them in identifying sickle cell anemia. So sickle cell anemia is a disease that is caused by oxygen gradient difference in the blood, and earlier they weren't able to figure out how sickling of RBCs happen, and at what time scales and at what pressures. It was really difficult, but this paper because of this droplet microfluidic system where the oxygen is exchanged between the continuous and the dispersed phase, you can actually measure small millisecond time scales exchange and variation in partial pressures. So these are some work that give us a lot of information that we were now not able to do previously where we had macro-sized reactors. The other advantages is you can actually automate. Like I said, you just have to put everything in, turn on the pump, and that's all. The experiment or the reaction will happen by itself if your design is perfect. And also you can do assemblies, multiple layers. For that is where we are right now. So you start from a starting point and you get the final product. For example, if you're doing API manufacturing in pharma, so you have multiple steps. It's not just a single step. So earlier in the 2000s, people were doing one chemistry at a time. Now we are in a stage where we can put multiple steps together and put them all in a single chip. So this is one example. I've taken a biology example. It's an algae growth that is happening on a single chip. But this is also relevant to chemical engineers because algae is useful for biofuels. And biofuels can be produced at high concentration at a certain condition only. So if we are actually doing and figuring out the condition at which the fuel is produced, then every experiment has to be done separately. You have to grow algae for a period of 2-3 months, give a certain condition, and then find out how much of the biofuel is generated. So that is one condition. Second condition, again another 2 months. Third condition, again another 2 months. That's how we do. And the problem with algae culture is it's light sensitive. You need to give it light so that it grows. So once the algae mass grows beyond a certain point, light is not penetrating to the center. So therefore you will have differences in growth kinetics between the center and the outer part. So because of the diffusion limitation. Media also will not be diffusing to the core, light also will not be penetrating to the core. So this is a problem that people face in a huge bioreactor. On the other hand, in this experiment what they've done is they have a bottommost channel in which they have multiple wells. So each green circle here is a culture well where algae is grown. It's a small well that can hold algae. And then on top of it, they have this concentration gradient generator where you put water and they've put dye. So you have multiple concentrations of black dye. So it's like light concentrations, multiple concentrations of light. And on top they have another pneumatic control valve where they vary you see they have put light and black, consecutive light and black. So the combination, these two together will give you different combinations of light and black. So basically they have tested 60 different light exposures in one experiment. So this is one set of experiment. They have been able to do 60 wells, 60 different exposure to light for this one well alone, for this one experiment alone. This would have taken like 6-7 years if we have done the whole thing on a batch reactor, on a bioreactor. On the other hand, the other problem that light exposure is not uniform after a certain stage of growth is also averted because this is a single small well. Okay, 1 mm by 1 mm, if you see, it's a very small well. Light is exposed throughout, however much the algae grows. There's only a limit to which the algae can grow. Once it fills up, then the experiment is already done. We are finished with this particular work. So this kind of experiments are, high throughput experiments are really useful. So it's like automating and you can perform multiple functions within a single chip. Another bio example, high throughput example. I'm just skipping this because I think we understand this. So this is on the microfluidics properties and some of the applications. Now the problem with microfluidics, small channels, throughput is very low, right? But as chemical engineers, we need tons of material. If we do petrochemistry, tons of diesel, tons of petrol every day. So microfluidics will not be applicable for such applications. We cannot think of doing because it's like 1 microliter per minute. So per day maximum you can do like 20-30 microliters per minute, which is like very small. So that is why it is mainly applicable for biology. because your sample volume is extremely low. If you are getting samples from patients, they have very small volume. You can use microfluidics.
Can't we take this information to scale up?
I'm coming to that. In right now, for API manufacturing, we can use it. For petrochemistry, it's rather a long shot, but still people are trying. There is a company called Velocis which is trying this, but it's still under consideration. But for API pharma, we can still use it. So high throughput, how do we do that? So if conditions are performed correctly, everything is done, one chip works, 1000 chip will also work. It's the same set of conditions. You don't have to do a pilot scale and then you don't have to go for commercialization. So that step is averted. One chip works, 1000 chip, 10,000 chip, a million chip. So you can stack up the chips like inside a refrigerator, one small refrigerator, the ones that we use at home, we can stack up to like 1000 such reactors. And so that is called scaling out. And not scaling up but scaling out. If one chip works, you can just put them together and figure out the flow. The only problem is how do we figure out the flow? So you can stack it up, you can scale out. So one chip, here you have 10 chips all putting side by side, or you can have the flow channel on top of each other. You can do both. Functional area alone you can multiplex, or the entire chip you can multiplex. So two ways of doing it. Here they have multiplexed the functional channel alone, while here they have multiplexed the entire chip. So whichever is applicable for this particular work that we are doing, we can follow that protocol, but this is possible theoretically. Commercialization and large scale production in microfluidics is not there yet. Theoretically, yes, it is possible. We can scale it up a bit. But if you are looking at water treatment, I want to clean the river, it's just impossible. So microfluidics is a niche application. We use it for very specific applications, that is all. So with that, I am finishing basic introduction. Any questions? Are we all okay with so far? Okay. So then the next thing that I wanted to talk about is mixing. Remember I said it's laminar. The Reynolds number is extremely low and it's completely laminar, which means there are no eddies, there is no turbulence at all. So mixing is zero in microfluidics, and that is the reason why we have temperature. The flows, you can do one egg mein both the sides temperatures. So all that is because there is not much axial mixing. There's not much radial mixing. It's like a plug flow reactor. Laminar, only flow is in the laminar direction. And the other condition is the Peclet number. If you calculate the rough, Peclet number is LB by D, so it's diffusion and in the denominator and translation in the numerator. So because your convection is very fast, because the fluid moves out very fast, by the time diffusion catches up, the fluid is out of the reactor. So you will have to play around with Peclet number is quite high. It is of the order of 100 in microfluidics, and Reynolds number is very low. So when Reynolds number is low, Peclet number is high, we have a problem with mixing. We'll have to depend on diffusive mixing, but before diffusion can catch up with convection, the fluid is out of the reactor. So mixing is one major problem in microfluidics, and people have come up with a lot of methods to improve mixing. We can use magnetic mixers, stirrers, so you can have channels outside, say you can pulse the electrical pulses. So these are all coming under active mixing category. You can also have passive mixing. So this is what I meant when I said diffusion is very slow. So this is an experiment that I did in my lab, where you can actually see this is water, blue dye, orange dye, and you can actually see it flowing extremely slow. There is no mixing at all, and it takes a lot of time. You can actually see it slowly dispersing, and over a period of time they diffuse and they mix. So this, just like a PFR, this is your time scale. The length is your time in this case, right? So over a period of time, it takes around maybe a minute or so, but compared to a macro scale unit, it's still faster. But as such, mixing in microfluidics is extremely low because it is diffusion limited. Diffusion is the main reason mixing happens in microfluidics, and it's extremely slow. So what we can do is we introduce either active mixers, pulsers and things like that, or we can fabricate at the bottom of the channel, we can fabricate such grooves, ridges, so that it introduces mixing inside the channels. So this is these kind of grooves that you can pattern on the channel, they are called herringbone mixers. And so they follow a very, so this is experimental, one of it is experimental and one of it is prediction, mathematical prediction. Both of them are extreme overlapping. So basically you can actually predict how mixing happens in microfluidics based on the channel geometry. So this is well known in the literature. There are lots of such fabrication protocols available, lots of such grooves and ridges, wells available that help in mixing. So it's also very well known. The other way to mix fluids is by using multiphase microfluidics. So the previous example, ridges, grooves and all, is when you have only single phase. You cannot introduce a second phase. But if you have the if you can actually introduce a second phase, then two-phase microfluidics is a very easy method to introduce mixing. This is one example. You can have gas-liquid flows, or we can have liquid-liquid flows. Liquid-liquid, then we need to have an oil and aqueous, immiscible phases. So this is a drop that is being formed in a T junction. So you can see this is a T junction. So this is the continuous phase, the color, the contrast, you can see the difference. And this is the aqueous phase and it is forming droplets. So this droplets is extremely well mixed because of the recirculatory motions that are established inside the drop or inside a plug. If you are having gas-liquid flow, we call it plug. If you are having liquid-liquid flow, we call it a drop. So this is a drop and this is a plug. So you see, because the channels are constant, they are not moving. Fluid is moving in between, inside the channel. So the relative motion introduces streamlines inside the fluid. And these streamlines, they are responsible for mixing the top and bottom half. But then, if we just have a straight channel, only the top half will get mixed there, bottom half will get mixed here. There won't be mixing across the two halves. To help or enable the mixing across the two halves, we introduce what are called these serpentines. That's why in most micro reactors you see these serpentines to help in mixing of the reactors. So if you see mixing within these microfluidic channels, these are the predictions, computationally evaluated, and you can see that mixing is complete within a few milliseconds, right? So because of this, multiphase microfluidics is most often a preferred method for doing experiments, unlike single phase microfluidics, because you can actually put your reagents inside a small drop, so it is confined, so it's like a small micro reactor within a micro reactor, right? So it's a very small picoliter reactor inside your micro reactor, so you can actually control it better. So as you can see, it is also extremely reproducible. So I have taken cuts of the mixing pattern. So I introduced dye here and I took cuts of the mixing pattern, and they are almost almost falling on top of each other. So they are extremely reproducible, the mixing patterns also, the streamlined mixings with mixing within the microfluidic reactor, and mixing happens within a few milliseconds. So therefore multiphase microfluidics is most often used, and now I will be moving on to some of the applications that we did in our work. So any questions so far? So with that, we have done with the lectures on microfluidics.
That liquid is flow just manually we are putting the liquid or by some machine?
We always use, in our lab at least, we use syringe pump. We can't, if we do manually, we won't be able to control the pressure. As I mentioned, pressure drop delta P is already 10 to the power 24, right? So if we use hand, yes, syringe pump. We always use pressure driven flows. There are syringe pumps, there are lots of other pumps that can be used to control the flow. We don't use hands, typically not.
And that channel is open or that is closed?
So if you remember in the first slide, 3 sides were metal and then we put a plate on top. So it is closed. But then you have inlet outlet. You have holes for inlet, holes for outlet.
Suppose if we will open open system it can work, or that atmospheric pressure will be...
No, it won't work in open system. You will have spilling and yeah.
And speed, can you measure the
Yeah.
speed of that?
Yeah, of course. Velocity, so you are controlling the flow using a syringe pump. So you will, flow rate, you will, fix using the syringe pump. But velocity you can measure anyway. There are ways to measure the velocity.
Flow rate is important.
Of course. So flow rate controls your time. If it is faster, then it will come out faster. Right? So then diffusion won't happen. You are not giving enough time for reaction to happen. Right? Because Peckley number high, you should give enough time between diffusion and convection. That's a problem. You'll have to play around with the flow rate. And here again in droplet microfluidics, if it is too fast, mixing will be super fast. Because the faster it is, so your channel is stagnant. Then you have a liquid film, continuous film that is surrounding your drop, which is also moving. And then the drop is also recirculating. So therefore, if you increase the flow, you are increasing the flow of oil, increasing the flow of the drop also. So the mixing will be extremely fast, even faster.
Madam, initially you spoke about this dimension when you are telling about this microfluid 10 to the power of minus 9 to 10 to the power of minus 8. What is that?
That is volume.
Volume.
Dimension, if I...
Small amounts of that much volume that is being injected.
Yes.
That is what you say.
What I meant was, if you take a small pocket, in this case, just a droplet. In this case, if you assume this droplet, if you take the dimension of the droplet, the width, depth, length of the drop, the volume will be in picoliters. 10 power minus 12 to 10 power minus 9. It will be of the order of nanoliters, picoliters. The volume.
Now you are speaking about the channels through which this microfluid will pass. Now in our casting,
in your what? Casting?
Mechanical engineering casting process. So when we do this, we have one effect which we call it as aspiration effect.
Okay.
Yeah. So how are you taking care of that type of effect here?
Aspiration, if I understand correctly, it is formation of small bubbles, is it, or what?
It's not bubbles actually. When you pass the metal, liquid metal, the sand, mold, or whatever it is. So we don't see the flow throughout. Some decrease or some distortion will be there. So, and by the time it reaches that place also, that height difference will also be there. No? So there, that's what we speak about there. But here also, I see the similarity where you are introducing these bubbles, small bubbles. And when I think I'm getting a lot of questions like how much time will be using and
so
how
probably
so
if you look at this, right?
Yes.
This is a very controlled way of generating drops. Here nothing is open, everything is closed. And this is coming in at 10 microliters per minute. This is coming in at 20 microliters per minute.
And that too, that is being injected or whatever in one direction.
Yeah,
so
one direction.
This way it's going. It's
Yes.
not going the other way.
Yes.
So there are
pressure driven flow, right? You are pushing it in one direction. It can only flow in this direction.
In the dye preparation, we do incorporate all these things. Here also, the channel, are you putting anything? Because you said you're practically doing that. In
Yes, yes.
So how are you preparing that?
This channel, if you remember, I told you that it is made up of PDMS, polydimethyl siloxane, and the channel is very small. You will not have any other, it's controlled, everything is controlled. See, this is a channel. This is a channel. This is 70 mm. This is small channel.
Yeah.
And if you see, not the channel, this is a reactor. If you see the lines here, those are the channels. So everything is extremely controlled. You cannot have anything else happening there.
How are you directing it? Like particular direction is flowing.
You see these tubes? These tubes are connected to a pump. Okay, so this pump will pump the fluid. The fluid will come in through the tubes and they will reach your channel here, and they will be, it's pressure driven. You are pushing the fluid in one direction. It cannot flow in another direction because of the delta P. So there is inlet which is through which the fluid is being pushed. Outlet is open to the atmosphere.
So some pressure, I should understand.
Yes.
Pressure is applied and those droplets are within this size, and the fluid
Yes.
only.
Yeah. So probably if we see how it works, it'll be, I could have brought one reactor, my mistake.
Tomorrow, I think.
Maybe when we, yeah. Are they going to the lab?
This is not, we can get one of your reactors as well.
We can show. He has a syringe pump also, so we can see. I'm not really sure. He needs to.
So, today is possible today. No, are you today fabricating? We will have fabrication also.
Yeah. We are fabricating all reactors in our lab.
Using 3D.
Yeah. And photolithography. Yeah.
So, just how about cleaning of these reactors, because it is very small?
We use and throw. We don't reuse. Specifically for research purposes, we throw them. But if you are talking about commercial applications, we clean them with fluids only. You cannot take them, open them and clean them. It becomes difficult. Fluids, so you flow acetone. So if it is a chemistry, then you can flow other solvents and clean it. You were saying something, Sharon?
Yeah. So just in case people are interested in going and seeing the facility, you please let us know today evening. We will try to manage that tomorrow in the time. Okay. So this was not there in the experiment. We have other things planned, right? So we will see when we can schedule.
So can we move forward? Okay. So what I have thought was we use this microfluidics for synthesis of particles, nanoparticles. So I'll just quickly go through one example and then skip to another example. So 2 examples I'll try and finish today. So what we are trying to synthesis plasmonic gold nanoparticles. This is from my PhD times, which was like several years. Century back, not a century, like 2006, I started my PhD. So at that time, gold nanoparticle, specifically gold nano rods, was very difficult to synthesize. And every time you do a batch experiment, every time you do an experiment in the lab, you will get different size and shape, and you will get different spectral signatures of these particles. So this was a challenge that we took up. And this is also aqueous chemistry. Everything happens in water, in our liquid water cell, aqueous. So therefore, what typical protocol that was followed at that point. Right now, if anybody is doing nanomaterial synthesis, you might say, yes, this is a well established, there are a lot of methods we can do, yes, but at that point, it was difficult. So, there are two steps to this reaction. The first step is formation of small nanoparticle seeds, and then we use the seeds in the second step as a growth step. So we have isolated the seeds formation and the growth formation, typically nucleation and growth phase. We have isolated them. So we form 3 nanometer gold particles, and those are used in a growth solution to form anisotropic gold nanorods. So this is the chemistry that we are looking at. And okay, I'll skip this for now. If we have time, I will look at this. This is gold with silica coating on top. So this chemistry also we did using the same droplet microfluidic method. So the challenges that we were actually looking at is, so in a 10 ml solution, if you do a small vial, you get quite monodispersed gold nanorods dispersion. But then when you scale it up to 200 ml or even 1 liters, for applications you need a lot of material, right? So when you scale it up, we just end up with spheres. This was an experiment I myself did in my lab, so this is what I got. Probably now if you repeat it, it might get better, it might be better, but yeah, this is what I got. So I had issues with scale up, and also there are issues with monodispersity. While in the nano shell case, if you see, actually we want one silica particle to be coated with one gold shell. That was what our intent was, but actually we ended up with several different, so we had a bimodal distribution. This is our aim, but we might have ended up with several different things when we do it in a 10 ml solution, because we had a bimodal distribution. So this was also a challenge that we were trying to overcome using our droplet microfluidic method. So first thing is we thought, okay, let us try, why go to droplets straight? Let us try using a single phase system. Single phase is when you put your salt, reducing agent, everything through these different inlets, and then you wait for the reaction to happen. But actually what happened was, there was complete deposition on the channel wall. there was no control at all. So gold particles started, the small particles started depositing. Once you have a deposit, that will form a, act as a seed, and then you will have multiple reactions happening, leading to fouling, flow issues. You won't get anything in the end. So we had multiple rounds. We tried different combinations of the reagents, diluted them also, but still we ended up with all these deposits. So finally what we did, we moved on to multi-phase system, and we thought, okay, we'll use droplet microfluidics to figure out this system. Okay, so what we did was we combined the different reagents. We used seed, salt, and the reducing agent. So we are we made the seeds outside of the chip, and we used that in one inlet. The other inlet had the salt, and the other had the reducing agent. In this case, it's a slow reducing agent. It's a slow reaction typically. So then we had the continuous phase coming in here, and these three together, they mix and they form the droplets here. And as I mentioned, droplets, the mixing is quite fast. So therefore, they mixed at different, they mixed very fast, and there was no deposit on the wall because each droplet acts as a picoliter reactor itself. So the reagent is completely confined. There is a thin layer of oil around the drop. So it does not touch the wall at all. So therefore, your reaction is confined within these small picoliter reactors. So then we started with just one aspect ratio of gold nanorods. We were interested in just one aspect ratio, but then we ended up with multiple gold nanorod aspect ratios just by changing a few concentrations in the, or rather flow rates in our syringe pump. So we just pressed a few numbers and we got different aspect ratio rods. We also got spheres, the same chemistry, we got spheres, and we also got small elongated rods, and we also got dog bone shaped particles. So with just one experiment, a few sets of reagents, concentration of the reagents weren't changed at all. We were able to actually span a lot, the entire space of the combinations of reagents that we can get. So this would have been multiple experiments in a batch experiment, but in our microfluidics it was just 1 day's work of experiments, and you can get multiple such experiments. So this is one example. This is one example for gold nanorod synthesis. The other example that I was pointing out previously was the other example was this core shell particle. Like I said, we had in a batch experiment, we had multiple cores, single shell, or you can have several combinations, a very thick shell. So you had bimodal particle distribution. Now the same thing we wanted to try on a microfluidic, droplet microfluidic system, but again there were deposits. The problem here was I'm using a seed. In this case, I'm using, So if you see, the seed here is a silica particle and a very small gold nanoparticle. This silica particle, which is the core, so let me explain the chemistry here. So we make silica particles. The silica particles are 150 to 200 nanometers. They are quite huge. And then we try to coat them with gold nanomaterial. So the coating of gold nano shell, it's called, the coating of the shell needs to be of the order of 2 nanometers, 3 nanometers, etc. for applications, some of the applications that we are dealing with. So for this, the core that we take is 200 nanometers, while the seeds are 2 nanometers, and then we put them together, we add some more reagents, and finally we end up with a shell. So this is what our aim was. So we started with this, but because your silica particles are huge, they themselves deposit at this point. If you are using a simple drop, they themselves deposit huge silica particles. 200 nanometers are huge when compared to 5-10 nanometer particles. So they are depositing, and because they deposit, the reaction starts happening at the interface, and then there is some more fouling, and it slowly grows and builds, and the entire reactor is fouled. So in this case, what we did, we introduced a gas, one more inlet that came to rescue. This gas was an inert gas, but what it did was it just, this video, so it just so as you can see, it just cleans the interface. The gas is just an inert here, it just keeps on cleaning the interface, so that way there was no deposits of the particles at the interface. When there are no deposits, there is no fouling. So that's all. The gas bubbles helped in pushing the reagents from the interface. So this we did, and we just used the same protocol as previous, except that here we had an extra gas layer, and we had a very good nano shell particle formation. In addition to nanoshells, we were also able to get what are called nano islets. So we could stop growth at a certain stage, and we could grow them fully into nanoshells or stop them at a certain stage. So these are steated silica particles. They grow a little bit, they grow a little more, and then they fully cover the surface of the silica. So we could stop the growth at different stages, which was not possible at that time. I'm not sure if it is possible now, but it was not possible during my PhD time. So this was really a big thing at that time. And if you actually compare the batch with what we developed, it's a completely it's single, and as you can see, it's extremely pure monodisperse particles, while in batch we had bimodal. So this method is really very useful in synthesis of metal nanoparticles, and also in a lot of chemistries that are tricky, finicky, which are prone to small changes. It affects your results. Then we use such droplet microfluidic methods to get very good results. So this is one of the work, and apart from this, we have also done, currently one of my PhD students in the lab here, she is working on assembly of these gold nanorods. Now that we have figured out how to synthesize them in droplets, now the next thing is we thought how to get heterostructures, how to get assembled particles, can we get reconfigurable assemblies, and yes, we were able to do reconfigurable assemblies just by introducing different solvents inside a drop. Exactly the same setup, droplet microfluidics, oil as the continuous phase, T-junction. Instead of reagents, we had gold nanorods and different solvents like EDTA, THF, DMF coming in. So we were able to get side-by-side assemblies and structures assembled together, and also end-to-end assembled together, and we are also able to get superstructures like nanorods of this is a sphere of nanorods and such kind of structures, and these are actually very monodisperse, in the sense you can actually see multiple of these, many of these, and their size and shape are also extremely controllable in our reactors. So these are some overview of what we have done using microfluidic drops in my previous lab, in my PhD lab, as well as the current lab that I have set up here. So we've been doing a lot of work with just drops and combinations of drops. So we've got structures like this, and we've been doing different chemistries in these drops. So one area that we work on in microfluidics in our lab is droplet microfluidics. The other thing that we are also looking at is photocatalysis using microreactors. So here what we do is we don't use droplets, but we use single phase system. So we are depositing, we used, this is our first work, this work was recently published in Langner, and my PhD student is just working on this, and we just finished this work. What he has done is he in situ he synthesized zinc oxide particles on chip. So this is how the experiment goes. This is the reactor, and you have all the reagents going in, and this leads to such kind of zinc oxide particles that are grown on the surface of zinc PDMS. So basically we are introducing all the reagents through the inlets, and they react on the surface of PDMS, and they lead to this nanostructure formation on our PDMS channels itself. And then we characterized them. As you can see, you have got UV spectra, so all the characterization, and we use them for MB degradation as well as antibiotics, ciprofloxacin. We have done several different antibiotics. So we have done 4 different antibiotics along with MB-Di at different pHs. So this experiment was not done for water treatment, but we wanted to show that yes, we can do single phase studies for deposition of catalyst on the PDMS surface. Therefore, these kind of reactors can actually be used for photocatalytic chemistries, API synthesis and other such chemistries. So it is possible to do this, but zinc oxide typically is used for dye degradation. So we use this as an example, and we have also done high throughput. We have put 8 such reactors together and our production rate was improved a little bit. So can be used for API synthesis. So this is where we are in the chemistry part in my lab. So so this is my lab right now. My students who are working in the lab, and right now there is a complete area on healthcare applications that I am working on, as well as a little bit of chemistry and particle synthesis. So without my students, nothing will be possible. So I would like to thank my students, and also thank you all for your patience here and for listening. Thank you. Any questions?
I
That
see so many.
first application, madam, that
Yes.
gold deposition you said, no?
Yeah.
What is the application of that? The second one you said, but that
Gold application, the gold, it's not gold deposition, it's gold
Deposition.
synthesis.
Yeah, yeah. Why?
So
why
we
is that?
did not have any application in mind, but right now we are working with Prof. Shaurya. He has a lot of applications for these plasmonic structures.
We can use that in class.
Yeah, plasmonic structures, SIRS application, sensing application. So basically, in all these applications, you need a definite size and shape. And because we are not able to get a definite size and shape, we always go for downstream processing of these particles to get to that application.
Definite size and shape, especially gold one.
Not necessarily gold, any silver, metal nanoparticles,
You
silver,
were just
platinum.
using
We
gold
just took
to
one
assess.
example of gold. Copper, silver, gold.
Anything okay.
Yes, plasmonic particles. I'm assuming anything can be done. Our
Similar.
example is gold. Yeah.
Similarly, you can.
Definitely you will have to rework the chemistry, but yes, anything is possible. You were asking
Yeah.
something?
So I can also see potential applications in quantum dots also.
Yes.
You can do the same thing.
Quantum dots, there are lots of papers already listed in quantum dots. The advantage is it's not aqueous, it's organic. So because PDMS is hydrophobic material, it is easy to use organic reagents in PDMS to synthesize such material. So there are lots of publications on quantum dots and microfluidics.
Maybe the scale up is a real problem.
Yes. It is a real problem.
Reactors. But for example, in a small world like ants and all, I think these kind of reactors will help them a lot rather than us.
Okay then. Thank you all. Sorry.
What is the typical synthesized volume of nanoparticle?
So if I run my chip for like 1 hour, I will get approximately, if I need 1 ml, I will have to run it for 2-3 hours. 40 microliters per minute is what I'm using.
So, any more questions for Sonia? Okay. So, how many people would want to see her reactors and how they're making it in her lab? Right. So, please tell the people outside and near the registration desk. We will try to manage that tomorrow. So, we'll add that to the program. It's already hectic. We'll try to manage it. So the next talk, we have a slight change of track. So you heard about synthesis, additive manufacturing, all sorts of things since the morning. The last 2 talks of today are on characterization. The first talk will be on transmission electron microscopy, right? And Shubhradeep is an expert who mainly works on phase transformations, welding, solidification, additive manufacturing, and phase transformation that you have in those systems, right? And more recently, we have been looking at thin films and phase transformations in thin films. But his core expertise, which he developed at IIT Bangalore, was in TEM, both conventional and STEM-based methods, and that's what he'll be talking about. The second talk that we have at 4 o'clock after tea, which will be by Rama Srinivas, is on a technique called as atom probe tomography. Anyone has heard of atom probe tomography? Right? So, if you have not heard about it, it's an interesting technique
where we have 3 systems in India currently working, one in IISc, one in IIT Madras, the third one is here. And we have the latest generation one of that. That system is capable of looking at single atoms. Right? You ionize it and you can basically look at single atoms. If you look at want to look at composition, that is perhaps one of the best techniques that you can use. Right? Across all the other techniques that you have, right? And you get 3-dimensional information about the alloy that you have, alloy material, etc. Right? So with that, Shubhradeep, the floor is yours, and I think Shubhradeep will talk about the game.
I think I'm audible to all. Yes. Good afternoon. My name is Shubhradeep Chatterjee. I'm with the Material Science and Metallurgy Department. Since I was not very sure about the background of the participants, I thought I prepared a very general introductory kind of lecture rather than going into the research topic. So just as a curiosity, may I know if anybody from metallurgy or material science or physics background here? Okay. And people from chemistry? And engineering, electrical, mechanical, anybody? Okay, we have a mix. So it's okay for metallurgy and material science maybe?
I think madam is, you have a certification.
But I don't have any application specific. I have only one example from battery. But yeah, this is not a research thing, but it is more of a technique overview. But I'm not sure how the pointing thing works. Yes. Which one points?
Pointer.
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 Sensor over.
Pointer is not working.
No, it's working, sir. So,
She is also physics.
So I think you have to use a laptop.
Yeah, that I can use, then it is useless.
That is only for changing slides.
Yeah, then if I'm standing there, it doesn't make much sense. So I'll rather use my laptop and.
Sensor over.
Yeah, this is, I can throw it out. It's useless. Okay, so this is the TEM that probably you will see tomorrow. You have a visit there. And okay, let me, as I said, that this is a general introductory level lecture. You stop me at any time. Of course, we have to stop at 3:55, hard stop. You have tea and I have to go for another meeting. So, yeah. So, as microscopists, if there are microscopists among us, they always know, and photographers, that looks can be very deceiving. Okay? So, what you look an actual thing may be different. You see the rhino picture, it looks like a two-headed rhino, but it is really not. Two rhinos standing one after another. It's a 3D thing projected onto 2D. This becomes very relevant for TEM because what we will be seeing in the projection. So we have to be always aware of these artifacts. Unfortunately, I will not have much time to talk about artifacts, but that is the first cautionary note for TEM, that when you go for interpreting images or patterns that you get, you have to be very clear about what is an artifact and what is a real thing. And this one shows you have to know other things also. Just by looking at the image, I think the right one is a cauliflower and broccoli and something else, and the left one mud crack, and it's okay. It's okay, I can manage. So what you need, first of all, that scale bar is very important, but scale bar alone will not suffice. You have to know some other things about the specimen. So you do other experiments to get that data. Okay, so only by combining different kind of things you can know for sure what is happening. Okay, so now it's an overview. I will stay there for some time. What is the unique thing about TEM is that it combines many things, many phenomena and different experimental things together. That is the prime appeal of this technique, because individually you can do each of these things, but here you can do them together. Okay, and of course we know that electron microscope can go to very high magnification, so that is there. But on top of that you have this thing, and specifically these three things, different kinds of experiments. Diffraction, you are all I think familiar with X-ray diffraction. So yeah, you can do X-ray diffraction on bulk sample, but here you can do on very tiny crystals. You have done imaging, all of you have done imaging, optical microscope SCM. Here also you can do. And the third one is spectroscopy. You do different kinds of spectroscopy, Raman, UV and everything. We do two different specific kinds of spectroscopy here, not all spectroscopy, but you can, the advantage is that you can combine all three in one instrument. So that is where the appeal lies. And what kind of information you get? You get a variety of structural information. Starting from what we metallurgists call microstructure, which is nothing but a bulk material composed of billions or millions of crystallites, okay, with the boundaries in between. So that is what we call microstructure with some defects. So that is the microstructure, but that doesn't end there. You can go down, you can find out the crystal structure. That is another kind of structure. You can go one more level down, subatomic level. You can go to electronic structure or states of valency or electrical structure, band structure, magnetic structure. All those kinds of things can be done, especially these days with advancement of the technology. And not only do you know about the structure, you can couple structural information with property. For us, the one major focus is mechanical property like strength. Okay, so we can do combine different techniques. We can do a testing outside and then bring the sample to TEM, but we can also do inside the TEM. We can do deform a material and measure what is the response. So that is mechanical property. People do electrical property, magnetic property, ferroelectric or dielectric properties inside the TEM. So you can do direct correlation between the things.
Also the thermal properties.
Thermal properties, mechanical properties. So all those things can be combined. So I'll not talk about much about those things. We'll see that inside the TEM what kind of experiments you can do. But I will cover the basics and application areas. So you see that you start with metal, ceramics. These are our standard things for inorganic materials, metal, ceramic, composites. And then you have semiconductors, a big way. Semiconductors are being used in TEM or characterized by TEM. You also can do soft matter and biological matter. Are there any biologists or polymer people here? Not really. Okay. I don't need to worry too much then, but it also can be done with some modification. And what does it tell us? And it gives me the details with which I can design materials better. I can evaluate the properties, characterize everything. These are main things, but the bottommost thing is probably the most important when it comes to TEM. Specimen preparation. Specimen preparation is really a big issue because without a good specimen, we will not have any of these things or much of these things. Okay, so specimen preparation becomes a very important aspect of transmission electron microscopy. Okay, let us go to parts and working principles. Now, among parts, so you need a source like light microscope. You have a light source. Here you need an electron source. Then you need lenses, which will converge or diverge things. And something which we use in TEM extensively, apertures, some diaphragm, some openings through which the electron passes, and finally the detector, which will detect the signal that is coming from the sample. So these constitute the entire system. I will mostly focus on lenses and aperture. Sources and detectors are also important, but I will skip those here. Now, in terms of working principles and phenomena, these are the three things: diffraction, imaging, spectroscopy. So this is what we will keep in mind. Maybe I will keep track of time. Okay, so physics of image formation. We can see that a point object can be focused onto an image here by a convex lens. And we have a thin lens formula, and we can have an extended object, and you can see that a real image forms here when the rays which are converged by this convex lens to so different points get rays from different points get converged to different separate points in the image plane. So this is called the object plane, the top one, and the bottom one is image plane. And you have the lens formula, focal length and distance. So the point to consider is that is the magnification is nothing but simply the distance from the lens, image distance to object distance. So now in TEM or more complex microscopes, you will have a series of lenses. This is just one lens I am showing here. This is typically called an objective lens. But you will have a lot of lenses which will take this as a input and magnify this image. So you have those in intermediate lens, projector lens, we will see here. And what are the electron lenses? They are not glass lenses as we use in optical microscope, but they are just magnetic fields. Typically, we also have electrostatic lenses which are used for very niche and exciting applications, but mostly they are magnetic. Basically, you wrap a coil around a soft magnet, soft iron core, and produce a magnetic field that will deflect the electrons. And by deflecting, they will make them converge or go different ways. So this is the schematic, and this is a real lens, that electron lens, and you can see from the scale bar what is the typical scale of this lens. This is what we put inside a transmission electron microscope, which we call as a column. It's a long tower-like thing, which you saw in the first image. So it will be pushed. So we have different kinds of lenses. Two lenses are extremely important. So probably I will have, the first two are extremely important when it comes to image formation and diffraction. Condenser lens, which basically takes the electron source, image of the electron source, and condenses that onto the sample specimen. Now, condensers may give a slightly misleading idea. Condense doesn't mean that doesn't always mean that you converge it. You just put it. You just limit the electron beam onto the sample. Sometimes you do converge. So that's a different thing. And second thing is objective lens or image forming lens. So that is where you basically the schematic that we saw in the last image, that is what forms the image. And not just image, here it will also form the diffraction pattern. And this is a cut view schematic. On the left you see our objective lens is basically, it's a two-part lens. You have a top part and a bottom part, and your sample specimen goes inside this. Okay, you have a very tiny space. That itself tells you the specimen has to be extremely small. Okay, it's of the order of few millimeters. So we have to push it. So these days we also have so-called wide gap pole pieces. These are individual parts are called pole pieces. Even wide gap will not have more than a few, let's say, 5 or 10 mm, I guess. That is the maximum that we are talking about. But the space is very tiny. That is the message here. And you also have this newer lens design. This is a quadruple lens. These days they are having hexapole lens and then octapole lens. Now these lenses have an important role to play in modern microscopes like the ones you will see tomorrow. Because they do something, they make it better and removing defects of the lenses. So that is why they are important. So so basically we are playing with the magnetic field to deflect the electrons to certain paths. Okay. Now apertures. Aperture is something which limits the rays, electron beam that is coming from either the sample or from the source. So it is, you can see this is the physical aperture. Okay. These are like open positions, but what you have here, the small tiny holes through which this electron beam will pass through. That basically limits what is the spread of your beam. If it is a very tiny, your beam is spread is less. If you have large, now that spread, typically we describe spread in terms of angular spread. So that angular range will be reduced if you use a smaller aperture. So you may be familiar with the optical microscope numerical aperture formula, where it says that your resolution, the 2 points, nearest distance between the 2 points which you can see separately, improves if you use a higher numerical aperture, which will translate to this smaller holes, smaller apertures. Okay, so that collection angle is called beta, and this is the diaphragm or the aperture. So specimen, it's a rays coming from the specimen. You see that if rays coming from that side will be blocked by this aperture. So only the rays coming from certain divergence will be collected. Okay, now comes the main thing. So we have two basic modes in TEM. We have imaging mode and we have diffraction mode. Okay. In imaging mode, it is much like our optical microscope. So you have a parallel beam of illumination, and then from the sample, now you see different rays. So each point in the sample is acting as a source of electrons. Now why is that? Because electrons interact with the material and they get scattered. If you are thinking of electrons and particles, if you think of waves, they are getting diffracted because material has certain periodicity, is acting like a grating, and as a result, when the path difference between the two waves are multiples, integral multiples of the wavelength, you get diffraction. So this is what is happening. Different rays are different diffracted beams. And now if you take these two for example and coming and then they are forming, if you take this and then these two rays, all rays coming from that point are converging to this, and all rays coming from there converging here. Basically you are forming an extended image, real image of this sample here. And so this is the image plane of the objective lens, and this is called the back focal plane of the objective lens, which is the focal length. Now this is the key difference between other optical lenses and magnetic lenses here. Here we can change the focal length by changing the current through the coils. So that is why it is not a fixed value. So I can change what is the focal length of my lens. Now if you keep it this configuration, you see that rays which are parallel to each other, for example the ray coming from here to this orientation and ray which is parallel to that, diffracted by the same angle. Okay. Now this diffraction angle, if you recollect Bragg's law, so you have certain angle of incidence and angle of going out. So then these rays are diffracted by the same angle because the incoming beam was parallel, and they meet at this back focal plane of the objective lens. So that is what we call as a diffraction. It's a spot. You get different kinds of spot depending on what is the angle of diffraction for each. And you know that angle of diffraction depends on the planes for crystalline materials. So you have, depending on the periodicity, you get different angles of diffraction, and these spots represent those. Okay. Of course, this will be a 2D array. Here it is showing a slice. So you have a 2D array, and that is the diffraction pattern. Now this comes the thing. So this is the first image that you form by your objective lens. But you don't stop it there, you have intermediate lens which will make it bigger. Now if you change the focal length of this image to focus on this plane, image plane, you will get here an image. But if you make the focal length, change the focal length and focus here, the intermediate lens is focused here, what you are getting, a magnified view of the diffraction pattern. So by just changing the modes meaning here the focal lengths, you can go very quickly from image mode to the diffraction mode. That is the first and primarily most important role of this technique. So I can get the diffraction pattern, and just like we solved for X-ray diffraction, if we know the lattice parameter, we can identify which planes are diffracting. If you know which planes from the symmetry, you can get the lattice parameter. So these kind of things can be done. Key thing to notice here, unlike in X-ray where the angles vary from, let's say, 20 to 90, usually you go from 2 theta from 0 to or 20 to 90. Here the angles are of the order of maximum like 0.5, 0.6 degrees, 10 millirad. 10 millirad is like about 0.6 degree. So that kind of angle we are talking about. So that means the angle between the planes that are diffracting and the incoming electron beam is almost 0. So if the electron beam is coming, it is 0.5 degree. So that means almost vertical. So in X-ray diffractometer, where you have diffraction taking from planes parallel to the surface of the specimen, here the planes are parallel to the electron beam. So almost parallel, 0.5 degree. So that is another thing to keep in mind. Okay. Now, lenses have, or the optical systems have an inherent limit of resolution, which is called diffraction limit. Because if you pass a light wave through a small aperture hole, because of diffraction, it will be spread out, and this is how the spreading out looks like. Intensity will vary periodically like a sinc function, and so the condition for resolving a point is that this maximum, this shows if this is one wavefront coming from one kind point and this is another wavefront coming from another point. If the maxima of this is separated by the maxima by delta x, you can calculate what the delta x is. That is typically given by 0.61 lambda by alpha. Alpha is the angle. So this is a basic unit of optical system, absolute resolution. But typically we don't go there. We don't reach there because our lenses have additional constraints, which we call as defects, lens defects or aberrations. Okay. So I will talk about a few. So different. So this is spherical aberration is one. So you have rays, electrons. Suppose this is a sample and electrons are coming from there. If you have rays which are parallel to the or close to the optical axis, midpoint, central point, they will get focused at a different distance from the rays which are farther. So the farther away rays are called marginal rays, and nearby rays are called nearby to the central axis are called paraxial rays. Yeah.
So in like a few slides back, you one of the demonstration of the image plane and diffraction plane.
Right.
What are the advantages of having the diffraction plane? Like why are we calculating that?
So this diffraction, this enables us to seamlessly go from the diffraction experiment to the imaging experiment. I can combine that information. XRD gives you only diffraction. Optical microscope gives you only image, or SEM gives you only image. Now I can combine, I can go back and forth. From diffraction you can find the structure, for example crystal structure, and from the image you can see how the morphology is. So that is the reason, that is the main appeal of this technique, that you can combine these two very easily, just press of a button. Okay. So now I'm saying that these rays will be focused here, closer to the axis, whereas paraxial rays are focused at a larger, longer length. Now, as a result, you don't get a one spot from a spot, but rather a diffuse intensity between those 2 points. And you can make this thing plane go this way or that way, and you will see that there is some intermediate distance from here to here. If you are placing this here, this spot, marginal rays are focused exactly, but you have lot of variation in the paraxial rays. If you go the other extreme, marginal rays are focused, but paraxial rays are here. So you have a blurring. But in between, you will hit some point at which you have the least amount of distortion or diffuse intensity. So this is called the disk of least confusion. Okay, and that is the main thing that controls the resolution. If your points are spread apart away from this distance, then you should be able to separate them. That is one of the things. This is called spherical aberration. Okay, that because the off-axis rays and on-axis rays have different wavelengths. But you have similar disk of confusion due to other reasons. For example, I will come to this later. First, let me show the inherent electron beam itself may have a dispersion in the wavelength, slight, because it depends on the voltage, and voltage may have a slight amplitude oscillation. So that may have a very slight difference in wavelength. Typical wavelength in a 200 kV electron microscope is about 2.5 picometers. Okay, 0.0025 angstrom. But on top of that, you may have a like 1%, 2% variation in the wavelength. That itself will cause a difference in the focal length, because again, magnetic lenses, if you have different energy, different wavelength, they will be focused at different length. So you have a plane of least confusion even here. This is called chromatic aberration. Okay. Yeah.
Mostly you can get this kind of aberration in optical microscopy.
Yes.
Very, very small.
Yes. Yes. Higher. But because of the magnification that we are involved, typically 100,000 or higher, even the small ones can potentially, although this is not a big issue here, but if you go to the aberration corrected ones, because in aberration corrected microscopes, you remove spherical aberration, you kind of remove astigmatism. So then only thing that remains is this, which is difficult. We also have a solution for that. Probably towards the end we will come from that. But this is a chromatic aberration. Not only this electron source, but as electrons move through the specimen, they may suffer a change in wavelength, because they may hit some other electrons and lose energy. As a result, their wavelength may differ. So that is a real thing. So when it is objective lens focuses that, you will see different focal lengths.
Maybe inelastic scattering.
So that is what. So when they lose energy, their wavelengths is changing. So as a result, now this is not about the distance but about the plane. Suppose you have a plane like this. I think this is trying to show that this plane, XY plane and XZ plane, if you, the focal length may be different. So if you have a circular beam, because of this astigmatism, it may become elliptical. So your image will get distorted. So you will not get a true morphology, you may get a distorted, and your focusing will be difficult because of this. So this is astigmatism. Now in modern microscopes, astigmatism is pretty much controlled by changing magnetic fields. You vary the magnetic field so that your circle does not remain ellipse but it becomes a circle again by putting some additional fields. Chromatic thing, we have some techniques called energy filtering which can filter out other wavelengths, only choose one, monochromators, such kind of things are available. Spherical aberration, again, you have to design the lens, and that is what the past 20 years have seen a tremendous growth in this area. That how to reduce the spherical aberration, and that is what you will see tomorrow, that spherical aberration, if you remove, you will get an excellent resolution, subatomic resolution. I have, now you see the terms, the abbreviations, like plethora of terms, okay? You have starting from here. Now CTEM is basically, some people use conventional TEM, okay? And other things are non-conventional. So starting from HRTM, high resolution TEM, I'll just read out the abbreviation so that at least you can say that you have heard these things. Scanning transmission electron microscopy, atomic resolution STEM, then selected area electron diffraction, convergent beam electron diffraction. Then these are bright field, dark field, but you have annular bright field, annular dark field. You also have high angle annular dark field. You have EDS like SEM, EELS, electron energy loss spectroscopy, EFTM, energy filtered TEM. TKD, it's like EBSD, but in TEM, transmission Kikuchi diffraction. Precision, it's an alternative to TKD, is precision electron diffraction, which again you can do in TEM. 4D step, which is kind of similar and comparator to these two techniques, where you can combine some information, orientation information here. IDPC, integrated differential phase contrast, then tachography, 3D reconstruction, electron holography, correlative in situ, and inoperative. This is, so you have all these terms, some of them I will go through. Correlative means you use several microscopes. You use SEM, you use FIB, you use TEM, and then you use APT, which you will have a lecture following this one. So that is correlative. Okay, I think this is about the thing. So TEM, basically, TEM or STEM have two modes. So basically when you operate the so-called parallel beam, your electron beam falling on the specimen is parallel. So, and that you do by changing the power of this. On the other hand, you can switch off the objective lens and, this C2 lens, condenser. C2 is condenser lens, second condenser lens. You can switch that off and make the electrons converge on the specimen. This is called a probe forming schematic. When you form a probe, you will also realize that your object distance is much higher than image distance. Basically, you're now not magnifying but demagnifying. You have an extended thing. You are making it. Your goal is to make as fine a spot as possible. So ideally, you want angstrom level beam so that you can probe atomic dimensions. So each beam is like falling on an atomic column. So that is where we are today, that we can do such things, sub-nanometer beam size by this probe mode, convergent beam mode. Parallel beam mode has its own application. So in conventional thing, as I said, that you have diffraction and imaging modes by changing different things, and this is the aperture. What aperture? I think I had another visual here. This one. Where did I have that visual? Okay, somehow I missed it. Anyway, so basically, you can put an aperture here in the back focal plane, which will limit the which bit diffracted spots you select for further magnification. Now, basically, that means since you have a magnification, that means there is a virtual aperture. Virtually, you are selecting a very small region in the sample from which you are getting the diffraction information. Okay, so this is very useful because then you can select your area, tiny areas. Now, when I say in TEM, whole area that you observe is about 10 micron, maybe 10 micron by 10 micron. So that is small area that you are observing. But I'm saying even within that, you can select an area like 1 micron square. So that you can get put the SID aperture, selected area aperture, and get the diffraction spot information only from a tiny area, and then magnify it. Similarly, you can also have, so you remove the SID aperture, but you can put an aperture here, okay, on the image plane, and you can get, no, this is where, this is put in the, let me just point here, blue and green there. So this is the image plane. Image plane you are putting here. Here you put the aperture on the back focal plane, the diffraction plane. So then you choose only certain diffracted beams. Now if you form an image using only those diffracted beams and not other beams, okay, then you form a particular kind of image, okay, which we call as dark field image. Okay, so the image is formed not by direct beam that is coming directly from the column, but from a diffracted beam, and that image is typically called a dark field image. That you can do by placing an aperture in the back focal plane. So for getting a dark field, what you do is put an objective aperture in the back focal plane. Getting a selected area diffraction pattern, you put a SID aperture in the image plane of the objective planes. And this shows how different kinds of ray diagrams where you get diffracted beams and image. This is an example. If you have lots of crystals, your selected area has lots of crystals. For each orientation, you will get a spot. Okay, but there are so many crystals that you get for a given plane. Let us say 1, 1, 1. You get a ring because they have different orientation in space. So each is giving one ray, one spot into the detector. So you get different rings which you can index by noticing the spacing. Remember that DH scale, that Bragg's law still holds. Okay, so you can. Now, if you don't have so many crystals, you will get a spotty ring. Okay, not all orientations are present, or not too many crystals are there. So you get a spots rings which are not complete but spotty. So these are called ring patterns. In contrast, what you see here are patterns from a single crystal, which typically metallurgists will call grain. So a single crystal ring region will give you only certain spots. Okay, and by tilting the specimen, this is another advantage of TEM, that you can manually control the tilt and you can get different kinds of spot patterns. By analyzing these spot patterns combined with the angular relation, amount of tilt, you can say, okay, this must be coming from an FCC material or a BCC material. So from the symmetry of the pattern itself, you don't need other things. By looking at the symmetry, next slide has that, you can tell that which crystal structure it is. Yeah.
What is the approximate scale of previous images?
In the diffraction pattern, the scale is inverse of length scale, inverse of nanometer. Okay, so it will be like 1 by nanometer. Okay, like something this length, maybe 1 by nanometer, 1 by nanometer, because it is getting reciprocal. If you have a larger spacing, your diffraction spot will be closer. So these are the different kind of standard patterns, simulated patterns that you can get for different kinds of orientation of the crystal with respect to the electron beam. Now this is not a diffraction pattern. This many of you will be familiar. It's called a stereogram. This is to show what are the different kinds of orientation that crystal are related with each other. Suppose you are at certain orientation and you want to go to this orientation. In TEM, you need some guide how to go from one orientation to another orientation by tilting. This tells you that guide. So which path you should follow while tilting so that you go from one orientation to another. This is one of the applications. It has other applications also. this is a diffraction, this is a convergent beam. So instead of a parallel beam, if you converge the beam and take the diffraction pattern, you will get a lot more information inside the this disk. Spots become disk, and you will see lots of information there related to the symmetry. You can determine the symmetry, space group symmetry of the crystal by doing this kind of experiment. And this is Kikuchi diffraction, where inelastic, you have when the beam comes, they have a fixed Bragg angle for a certain plane. But even if it is not at that Bragg angle, this incoming beam will lose some energy and change its wavelength so that it will satisfy the Bragg angle for that plane. So this is inelastic electron scattering followed by Bragg diffraction, and that will lead to this kind of lines. These are called Kikuchi lines. They have one practical advantage and one very theoretical thing. Practically, it helps us to go from tilt from one orientation to another. But more importantly, it also shows you the map of the reciprocal space map of the crystal. So it gives you an idea, and it is extremely sensitive to the tilting. Unlike the diffraction pattern, which is less sensitive, this you can use for orientation determination, accurate, just like EBSD. You can get accurate orientation determination using this Kikuchi diffraction. This is the STEM mode, or scanning transmission electron microscopy. Here, what you have is not a solid detector, but you can detect, you have an annular detector. So if you detect the direct beam, electron beam, that is called a bright field detector. So you have a bright field solid detector. So here, the straight one. But electrons are undergoing inelastic collision, so that will lose energy. And you can put an annular dark field detector, so which will be here. So this is the bright field detector, this is the annular dark field. So you have an annular solid ring kind of thing where electrons are falling. That will select electrons which have lost a certain amount of energy. Now this energy loss is actually proportional to the atomic number. So this, by collecting these electrons, you can get what atomic elements are there in the material. That will give contrast in the image. So you have different, so this is the bright field, this is the dark field, annular dark field. If you increase the angle of the annular, you place the ADF detector on the other side, you get even better Z contrast or atomic number contrast. I think I have to go fast. It's almost 340. Okay. Now image contrast in conventional and STEM. Basically, you have different kinds of reason for image contrast in the image, and image is contrast for us. So without contrast, there is no image. So we need to rely on certain phenomena. The phenomena are diffraction and phase for both things. So diffraction contrast is what we use mostly these days, and Z contrast is used mostly in STEM mode. But each has all three. But here in conventional, you also have a mass thickness, not just mass, but thickness. Thickness of the material also matters. I will skip the other details. I just want to show the mass thickness, that if you have, so this is carbon on carbon. So usually the thickness the contrast that you are seeing there is due to thickness. Okay, the dark things means it is thicker. So you have particles, it is thick. But now you can put some coating angle at some angular deposition. That will show you the shadow. Okay, so that shows that this is really mass and thickness combined. It is not just mass. They put a mold coating on that, and then you get a contrast here. Same for polymer and biological specimens. This is a very important thing. For biological specimen, this is probably the most important contrast mechanism. You put some staining agents, and that will go to specific organelles, and that will give you the contrast. Okay, so that is the mass thickness contrast. But mostly we use diffraction contrast. So as I told, you can select some of the beams to form the image. And here it shows, for example, the contrast that you are seeing. This is bright field image. The dark things is coming from one particular phase or crystal, okay, which are diffracting, Bragg diffracting. And you see tiny dots, tiny dark dots, they are also there. So this is the grain boundary or crystal interface, and inside you have tiny dots. You have a columnar or lamellar structure at the boundary, and inside you have scale. Now when you go to dark field, they light up, the dark ones light up. Again, in a TEM, it's a matter of pressing the keys, buttons. You go from bright field to dark field in a well-aligned microscope. So this you can give you a lot of information. This is a defect. This is called a line defect in a material, crystal called dislocation. So you can image such defects in TEM, and you get the best contrast under certain condition. It's all showing that different condition will change the contrast here. So a dislocation line. Similarly, this is a stacking fault. So you have a stacking fault which is an alternating fringe pattern. Here you get antiphase boundary, and here there are particles in a matrix, very tiny particles. The scale is about 5 nanometers of this particles. You get a coffee bean like contrast. In these images, what you are actually using is not the particle or the defect, but the strain field that these defects create. As a result, this contrast comes up. And this is finally the high resolution TEM, where you can get atomic resolution, atomic columns. You can visualize interfaces, defects at the interfaces, orientations. This you can do in this. Now, in addition to imaging and diffraction, you can do spectroscopy here. And there are two that we use. Yeah.
Can we capture resolution of motion?
Yes, in principle, yes. If you do in situ experiment. So if you are doing some loading inside the material, you can see them move. So you have to collect pictures continuously, frames, and see them move. In principle.
Is there any specific technique, or we can do it?
It's an in situ straining. In situ straining.
We can do it in conventional TEM.
If you have the port, to insert that device chip basically, where you can put a load. So the dislocations will move and you can image. Of course, it is better done in a high-end microscope, like ours we have. Now, you can do spectroscopy. Spectroscopy primarily gives you here the chemical identity of the specimen. So you can view at the simplest level, it can tell you what composition you have. Now, you will tell me that you can do the same thing in EDS, in SCM. Okay, what advantage? Magnification, yes. Resolution, yes. You can get a much better resolution here. But moreover, SCM, EDS, if you are familiar with EDS, let me just, what happened? Yeah, I will skip this. So EDS is nothing but when electrons come and hit the specimen, some electrons are excited, then other outer cell electrons fall into that and they emit that excess energy as an X-ray. So you do X-ray and you collect using a detector, and detector separates them into energy channels. These energy channels, because they are characteristic of elements, you can identify the elements. Now this you can do in SCM also. Here the advantage is that SCM, the specimen is thick. So as a result, the X-rays that come out of specimen, they undergo fluorescence and absorption, which makes results bit unreliable or less, let us say less accurate. You have to do corrections, and there are corrections, people do that. But this you can get here, because it's a thin specimen, you get better results. And spatial resolution, of course, is much better than SCM. And it shows, for example, you can map, you can also do line scan. This shows that, for example, at a grain boundary or interface, you can have segregation. It clearly shows this. This is that bright yellow line shows that this yellow scale is for nickel. So there is some enrichment of nickel at the boundary. So it shows such segregation. And here you can see a multi-layer and how it is back. And EDS spectrum looks like this. You have when you have separated it. It's like SCM. So, but yeah, you have better resolution here. One thing is that here you can use primarily two methods. One is a clip fluorimer for quantification. How much percentage is there? Then you can use a clip fluorimer or a ratio method, or you can use a zeta method. Clip fluorimer is typically used, but you have to be careful. This I am grateful to my student who convinced me that this is a real thing. When you use a zeta factor method, you sometimes, depending on the settings, depending on the values that you use, you may get a better result, more reliable results. How do I know that these are more reliable? Because I know the composition of the material that I took it. So when I deposited these thin samples, they have a specific composition. So this shows that you have to be a bit careful what to use, and always cross check. Don't believe everything, especially in TEM. You can go completely wrong if you're not careful. Okay, this is energy loss spectroscopy, where electrons undergo various energy loss. I started a bit late, Varanasi.
No,
so
I get more time to go through slides.
Yeah, but I still have to finish by 4. Oh, it's already finished. Okay. So this is yet another technique where electrons undergo small inelastic collisions and form energy loss, which you can use again for quantification. But this is where things go even further. You can not only get composition, but you can get subelectronic, means transitions, valence state. So you can get electronic properties, electrical properties using this band structure. All these things are possible by this spectroscopic technique. And you can go extremely high resolution if you have a probe corrected microscope like what you will see tomorrow.
Can I spot conduction band minimum and valence band maximum here?
I'm not the correct person to, maybe you can answer this. Okay, I am not really working in that. So I can just tell you that this is what people do. I'm not really familiar, I'm sorry. Okay, so I will, this is energy filtered. You can filter those things using yields, put a filter and then use this for imaging, mapping. Specimen preparation, I said that this is an important thing. So you are observing an area. This is a 3 millimeter grid. Your specimen is placed on that. That itself tells you it's a small thing. So if you have to prepare from bulk material, you have to cut a thin section because electron transport region is about 100, below 100 nanometer region. So you have to thin it down. And you cannot do it in one step. You have to go by step by step. You cut, polish, and then do dimpling, something called dimpling, then do something called electropolishing or iron milling to further thin it down and produce a hole. Now what's the point of a hole? Electron will just pass through. No, around the hole you have very thin regions. That is what you observe. So the area that I say that it's of the order of very few, it's like a couple of microns or a few microns square. That is the area. And for biological specimens you can have these microtones. You have for certain special kind of specimens you have this embedding method, powders or fibers or thin film cross sections, you can have that method. And this is a site specific, this one is called FIB, focused ion beam, where you can make a sample from a specific region that you have identified in the sample. It's like SEM, you are seeing the region 1 micron square, you are lifting that sample, thin sample from there. Again, we have that machine there. Tomorrow you will hopefully see this, how to lift out a specimen. This is just one image to show you one application thing, to show you the kind of things people are doing these days. So you can see that you can combine different kinds of things, chemical map at nanoscale with structure using STEM, and then you use a valence state. Okay, took all three information together by slicing and different kinds of yields, combining yields, EDS and STEM detectors to get those information together. And this shows you different phase transformations are taking place in a battery material as it degrades through cycling. So different cycles will lead to different structures, starting from layered structure to spinel structure to this one I'm not sure what structure, so another structure. So different phase transformations are happening and also chemical changes, and it shows from surface to inside there is a degradation. That identifies, this was not known, that okay, from surface to inside there is a gradient in the valence state itself. So your design of the cathode materials or anode materials, these things can improve dramatically. This map show that this is not only chemical, this also have a valence gradient thing plotted here as a function from radial function from surface to inside. Okay, so this is a brief thing. So you can have references and I will stop here. If you have a quick question or two, I'll be happy to answer. If not, then I will hand it over to.
Can we get these slides?
Yeah, I think you asked the organizers. I will give it the, so you can call. I think they are giving it. Hopefully, right? I don't have any problem. You write to me, I will just send it. Otherwise, organizers will. Okay. Any other question? I'm sorry, I have to leave because of this is the paper that I was talking about. Okay, I will leave. All the best. Tomorrow you will have some lab visits. TEM, you have fantastic TEMs. Tell you about APT. No. Oh, there is a break.
స్తంభనే అనిపించమ్మా.
Okay, so the next session will be, that's okay, I can talk now. Prof. Ramesh Srinivas Varanasi here. He is faculty in the Materials and Metallurgical Engineering Department of our IIT. And he works on, he calls himself a physical metallurgist. He works on, in short, he told me that he can modify the properties of steel from micro to macro scale, and he uses atom probe to characterize, and the atom probe is his primary technique to characterize what he is working on. So, stage is all yours.
Thank you very much. So this was a bit of a challenging slides for me to put together for the very simple reason that I wanted to see what is it that would add value. At the end, I decided maybe the best way for me to talk about the technique is to show what it can do. And not just in, I'll show a bit of my slides in the topic where I did my PhD, which is steels, but then we will move on to different material systems to see what insights this technique can give and maybe how it could potentially be helpful. And also I'm consciously, every technique, there's no technique which is perfect. Every technique, if you look at microscopy, every technique has its own limitations. But in this particular talk, I am trying to stay away from the limitations because that would be a problem for us when we start using the technique. Then we can try to see what we should or we shouldn't do a little more deeply. But this is more for me to give a flavor of what this technique can deliver. So I kind of like this comic a bit when we look at multi-scale characterization. If we have a new material that we have to characterize, no single technique is going to give us all the information. So we have a different length scale, we have different techniques that we have to put together to make sense of what is happening. And this is something which I would say for atom probe. So we are looking at, we do look at a few million ions, about 10 to 200 million atoms. But I would always ask my students to remember that 1 mole is 6 into 10 to the power 23 atoms. So a few grams of material would generally be 1 mole. And in that context, when you say you're looking at a few million ions, it is literally nothing. So we get a lot of value out of atom probe, but again, it is important to realize and understand that it is very site-specific and very localized. So we have to be a bit strategic to be able to leverage the information that we get. And we also have always, it's a good idea to put it in perspective with other multi-scale techniques. Now, I'm a physical metallurgist where I mostly work on steels. So we know that we have features which range from a macro scale, which could be surface, cracking. You had a lecture on additive manufacturing today, so you know build direction can change, the way you pattern it, everything can change the properties. From there, we have something called grain boundaries, phases, and then we have grain boundaries are 2D defects, precipitates could be over 3D, and then we have dislocations which are more 1D defects, and then we also have voids. So we have this huge spectrum of our microstructure, and we also have a lot of techniques. For example, we just had a lecture on TEM, we had on EDS, EELS. So where is the value that atom probe is bringing in? So if we were to just look at the techniques which help us understand the chemistry, very broadly, this is by no means exhaustive. One way we could look at it is spectroscopy techniques. So we have an incident beam or radiation. In case, for example, if you look at TEM, let us say we incident an electron beam, then we can get multiple information from X-rays, for example, which is EDS, and then from Auger, or you can also have EELS. So there are a lot of spectroscopy techniques. On the other hand, there are also something which we call time-of-flight techniques. Time-of-flight techniques, the way they differ from spectroscopy techniques is we have an atom, and there is a time t which it is taken from origin to a detector. So this time of flight is going to be a signature of our element, and by measuring this time of flight, we'll be able to say what our element is. So even in time of flight, there are multiple time of flight techniques. For example, secondary ion mass spectroscopy is one of them. So even atom probe is a time of flight spectroscopy. But what is it that atom probe gives, which the other techniques have limitations? So, to begin with, firstly, we get a 3-dimensional composition mapping. This is extremely important. Second, on the XY plane, we get about 1 nanometer of resolution. On the Z axis, we can go up to sub-nanometer resolution. When you have secondary ion mass spectroscopy SIMS, a very advanced SIMS can even give 1 parts per billion resolution in terms of your chemistry. However, when we go in the Z direction, the depth resolution is poor. We have a resolution about 1 parts per million, 1 ppm, but our depth resolution is sub-nanometer. So that way we are getting very good resolution. In principle, we do not have any upper or lower limits of elemental mass. Like if you were to measure the composition using EDS, for example, even in TEM, people who work with boron and carbon know that it is very challenging to be able to quantify what is the chemistry. On the other hand, because it's a time-of-flight technique, we don't have such limitations, particularly when it comes to elements with lower atomic mass, which could be challenging with some other techniques. Then, one of the biggest advantages that we have is we know that most elements also have isotopes, with the naturally occurring isotopes. For example, I work with iron. Iron has 4 isotopes. So there will be a particular ratio of all these 4 atomic masses in terms of what is the ratio in which they exist. So when we have a pure iron, we will get 4 peaks. Each peak would correspond to 1 isotope. And the intensities of these peaks would also be the same as what it should be in natural abundance. So because we are getting information even of the isotopes, even if there is some peak overlap with some other element, we will be able to deconvolute them a lot more effectively. And not to mention, it also allows us to do some tracer studies. For example, oxygen has both 16 and 18 atomic mass. Now if we want to look at oxide formation, and then if you want to say, okay, I have already an oxide, I want to know what is the growth of my next layer of oxide. Instead of doing an O16, we can oxidize in O18. Because we are able to make this differentiation in atom probe, we can use this as a tracer. So, for atom probe, the predecessor technique is something which we call field ion microscopy. So this is one of the first papers in 1955 from the group of Erwin Muller. And you can also see there's someone called Kanwar Bahadur. So that is, as the field was introduced, we had a signature or contribution from an Indian researcher. So he was the PhD student with Professor Muller at that time. And the way this technique works, I'll just come to it in a minute. We'll see these atoms, but we don't get chemical information. I'll just explain a couple of slides down the line. And then, a few years, maybe about 20 years down the line, they develop what they call it the first atom probe. And these are the origins of the way we see, which is the local electroatom probe tomography. Now, how does field ion microscopy work? The first step which we always do is we make a sample into like a needle. So now we have focused ion beam, which is FIB, where we can actually take a sample and make into whatever shape we want, which I'll show in the next slide. But classically, the way they used to do is they used to take a small wire and then they used to electropolish it. By changing the current, changing the solutions, you can change the tip of this electropolished needle. They make it into a needle. Then the question arises, why do we have to make it into a needle? So the answer is, when our radius at the top is about 50 to 100 nanometers, we have a very high surface area. And for the first thing which we do is, we first put the sample down to low temperatures. We apply a voltage. Now, let us say we apply a voltage of 1 kV to 10 kV. Because the radius is so small, the electric field at the tip is going to be in the order of 10 to the power 10 electron per meter, electron volt. This high electric field is what we need. Why? In field ion microscopy, we have something which we call an imaging gas. It could be neon, for example. What happens is, now we have a positive charge, there is the gaseous atom, and electron from gaseous atom is transferred onto the sample. Now then, the gas is charged positively, and then suddenly the gas impinges onto a phosphor screen. So with this, because we get information from each atom that way which are there on the surface, we will be able to map 1:1 what are the atoms that are there on my surface. So if you see, each of these dots which you see is atomic arrangement on this tip. This is coming because a gas which is ionized because of the voltage that we apply to the sample impinges onto our detector, so we know exactly what is the position of our atom. But now we have a limitation. We are able to find the exact position, but we don't know what the atom is. So this is where atom probe tomography comes in. In atom probe tomography, we do not have an imaging gas. Rather, we have it in very high vacuum. Typical conditions are 10 to the power minus 10 to minus 11 torr, in addition to having about 40 Kelvin of temperature. Then when we apply a localized electric field, if there is a static electric field, and then we give pulsing. By pulsing, let us say if my standing voltage is about 2000 volts, I give a small pulse. So with this pulse, locally the electric field increases. That can cause the atom to ionize now. Previously, we had an imaging gas that was ionizing, but now we have the atom itself from the tip that is ionizing. When we make a pulse, we know exactly the time at which we are pulsing. We have a detector, we can measure the time of flight. So this time of flight is dependent on the mass of each atom. Also the charge of each atom. So we have something called now charge to mass ratio. And by measuring this, we are able to now exactly say what is the signature, or what is the time of flight, and what it corresponds to which element. Then this, here we have now a position sensitive detector, where we have, like it can exactly identify where the sample is on the X and Y plane, and we can project it. So we field evaporate one layer, and then layer by layer, as we keep running the sample, we keep going in the Z direction. So we have positions in X and Y, and we are removing layer by layer. We also have positions in Z. We put them all together. Now you can make a 3D reconstruction. Historically, when I said they had this first atom probe in the 1970s, what they did was something simple. They said in the phosphorus screen, they put a small hole at the center. So now instead, then they had another detector on the back with which they can measure the time of flight. So there was an inception of this whole idea of atom probe, which culminated in what we see today. So how do we make the samples? As I mentioned, classically we used to take a small wire and electropolish it to make it into a needle. But now we want to understand chemistry of a very specific region. For that, we do something called site-specific lift-out, where we know which area we want chemical information from. We go to our focused ion beam, which you will be seeing tomorrow, and as Professor Shubhadeep was talking, the way you can make TM samples, the instrument can also be used to make atom probe samples. We first go to a region of interest, and we just cut it and lift out whatever area which we want. So this is what we call a micromanipulator. So we bring the micromanipulator, we weld it to a sample, and we lift it out. And then this is something which we call a silicon posts, because if we want to put the sample into the atom probe, we have to put them on a specific grid. So this is the silicon post, as we call it. But it's not too critical at this point. But what is important is the moment you put it, it is still thick. We use the FIB to make it thin and sharp. This is one video from Michigan Center, which I think explains this process very cleanly. Now, the first thing is there is a platinum layer as a protective coating. Then we start milling in all the 3 dimensions. As you can see, all the 3 dimensions are being cut. This literally we are milling layer. And then we keep one side hanging so that it is still in contact. Then when we look at the cross section, we know all the 3 sides are free. We have this needle, we weld it and we cut it. And then, as I was mentioning, we put it on the silicon post, and then we again weld it with the post. And then we keep sharpening it until we reach the radius, which is less than about 50 to 100 nanometers. Now, what is the benefit is, let us say if you want to know the chemistry of the grain boundary, we can go to the grain boundary and make a lift out so that we exactly see what is happening at our grain boundary. And it can be, I'll be showing a few examples. So this whole technique of site-specific lift out can be used in multiple ways.
How are you going to sharpen? How are you going to sharpen the 50 to 100 nanometers system?
So what we do is we have the gallium. So here in IIT Hyderabad, we have a gallium film. So this gallium ions remove the material. So we say we are removing the material from outside to inside. We kind of give a pattern. So this is what you see, an annular pattern. So we have an inner radius and outer radius. So inner radius, not anything inside, nothing happens. But we keep removing the material from inner to outer radius. So we first do it at higher currents, which is very coarse. And then we keep reducing this step by step. We start with larger radius, we keep reducing step by step. And then we finally...
Means you pass the gallium.
Yes, yes, yes.
Okay. How is it like? Means this specimen will be stationary and the gas will be passed.
Yes. So this is something, gallium is actually, typically tomorrow when you will see the machine, you will realize that there's an electron column. Just like you're able to control the electrons to image, we also have an ion column from where we'll be able to use gallium to both mill the sample as well as image it. So this is again which I was talking about. We have a sharp needle. Now I was mentioning that we can do a laser pulse, we can do a voltage pulsing. What happens to materials which do not respond to voltage? Which means metals which perfectly fine, but there could be some oxides, semiconductors where if we try to apply voltage, we still might not achieve ionization of an atom. In such cases, we try to have thermally assisted ionization, which means we want to increase the temperature locally so that we can help the atom to be ionized. So for that, instead of doing a voltage pulsing, we have a laser and we do a laser pulsing. So the 3000 generation and 4000 generation had something called a green laser. In the 5000 there was a deep UV, there was a UV laser, and in the 6000 which we have at IIT Hyderabad there was a deep UV laser. So essentially the energy of the laser is increasing. The advantage of the atom probe that we have in IIT Hyderabad is in the previous generations we can either do a voltage pulsing or a laser pulsing. But here, in this model, we can do both at the same time, which is what we call a synchronous pulsing. And as I mentioned, we'll be able to identify X and Y because these are lines which we call delay line detectors. The moment there's something called a microchannel plate, you don't need to go into the technicalities, but I just wanted to explain. The moment your ion hits it, you'll have an electron cascade, and then it will hit the delay line detectors. So let us say there is this delay line detector of Ty. There will be two signals that will be sent. One that will reach Y1 and another which will reach Y2. So we'll know the time. So therefore we exactly will be able to identify at which location we have our hit. So when we apply some laser, we can understand that the laser is not going to exactly give energy to one atom very locally. It can give energy to the surface. And when we have such a phenomena, then we cannot control the initial energy of the atom that is being ionized. So we can have two atoms that are being ionized, one with a little higher energy and one with a little lower energy. So why is this a problem? Because as I mentioned, we are looking at time of flight. So when the initial energies are different, the time of flight will be different. So we have something to correct it, which we call a reflectron. So if the initial energy is higher and which influences the velocity, then to get reflected, it will take a little longer. But if the initial energy, so this way we can actually correct the initial energies. And this is the small difference where I was talking. We can play with both electric field and temperature. So one is the voltage pulsing and another is the laser pulsing. So is laser pulsing perfect? As I mentioned, we give initial energy to the surface. The time of flight can slightly vary, which in turn means when we have our mass to charge ratio or the mass spectrum, they can be a little broader. So it comes at a bit of a cost. Atom probe is a characterization tool. You can do it for steels, which is what I work on, superalloys for turbine blades, like any aerospace applications, magnetic materials, electronic materials, thermoelectric materials, lithium-ion batteries, materials for solar applications, even for geological applications. In Curtin University particularly, they work with geological applications, and we also are working currently on some samples here which are meteorites, and we try to see how the local chemistry is and what information we can get. And there is also an attempt to push this to look at things like proteins, but that would need a very specialized sample preparation, which is called cryo sample preparation. Everything happens at liquid nitrogen. We'll not go into the detail. At this point, there are only very few groups in the world who are moving in this direction. So from this point, what I would try to do is give you a few examples to hopefully show that the information that you can gather from atom probe is interesting, but at the same time, how we can see it in perspective with other techniques. So this is a part of my PhD, where defects such as grain boundaries or dislocations, they can influence phase transformations. So how are these defects doing it? So, like in our material, we had something called martensite, and when we heat it, we form a different phase. So, for people familiar with grain boundaries, we have high angle grain boundaries and low angle grain boundaries. When we started annealing, this green is the one which is forming later, and red is the parent phase. We realized that this green is forming in a very specific regions, which is the nucleation is happening at the high angle grain boundaries. Now, what happens when we anneal 100 degrees higher? We start realizing it is not just forming at high angle, but even low angle boundaries. This is perfect. This is quite important because where it happens, how much phase forms influences all our mechanical properties. And why this is important? So this was on about 10 manganese steel. And when we look at chromium nickel steels, the same material, initial parent is martensite. At lower temperature, they start forming inside, not on the boundaries. And it is only at higher temperatures that they start forming on the boundaries. So whatever we observed was actually counterintuitive of what was reported in the literature. The question was to understand why such a thing happens, and we want to know what is happening in the grain boundary that promotes this phase transformation. So until now, whenever I talked about atom probe, I mentioned that it is a technique with which we'll know the chemistry. But what about structure? In some exceptional cases, we can extract structural information of atom probe data, but as a thumb rule, as a technique itself, we might not have structural information. So it always makes sense to complement this chemical information with some other structural information. So here what I do is something called transmission kick-sheet diffraction. I'll come to it in one slide down the line. But essentially the idea is we have the sharp needles that we are making, we have the tips, and with this tip, we get the orientation information. So then I know this is my tip. I have one grain boundary, which is a high angle grain boundary. In the same grain, on the other side, I have a low angle grain boundary. So I can look what is the chemical information across this grain boundary. Now, when we look at a low angle grain boundary, so this is manganese in my material, we realize the manganese at a low angle grain boundary is much smaller compared to at a high angle grain boundary. And same applies for carbon. Why is this information very important for us? Because when we are forming parent to product phase, when we have this manganese and carbon, they promote or have increased the driving force of the product phase. So when we have these grain boundaries, especially at high angle grain boundaries, we have this nice decoration or segregation at a grain boundary of these elements. What would they do? Locally, they would promote the formation of a phase. So that is why, because in our grain boundaries, we have some elements which are segregating that promote the local driving force, we're able to see nucleation high angle grain boundaries, which was counterintuitive when we looked at literature. So as I said, I'll explain very briefly what is transmission kick-sheet diffraction, but this would make sense for people who are familiar with electron backscatter diffraction. So in EBSD, essentially what we do is we do it in the SE. We tilt the sample to 70 degrees, and we have an electron beam, and it interacts. We get backscattered electrons. With that, we also get information, which is the Kikuchi bands. From this, we are able to say what is our grain orientation. Now, what is transmission kick-sheet diffraction? As the name suggests, we are in a transmission mode. So just like in TEM, you need very thin samples to be able to have the sample has to be electron transparent. So essentially, we need samples which are less than 100 nanometers in thickness. So we can do it to, what we do is, let us say we assume there is a TM lamella. So we have two kinds of geometries, but the principle is the same, that in an SEM, we don't need to go for a TEM for this. Just in an SEM, we have an incident beam, and the electron beam, instead of being backscattered like what it does in the EBSD, because this is electron transparent, it passes through your electron transparent lamella. And that gives us Kikuchi bands, and we get structural information out of it. Now, why is this so beneficial? We only get information from the bottom 10 nanometers of our sample. The resolution of EBSD would be about effectively 30 to 40 nanometers. Now, if I have a sample feature which is 100 nanometers by 100 nanometers square, if I'm doing an EBSD, maybe in the X I get 2 points, on the Y I get 2 points. I can at best get only 4 points. Now, if I do something I call the transmission Kikuchi diffraction, we get information 10 by 10, we get 100 points. So the confidence is much higher. What we can do with the data is much better. And the same thing, just like I explained with TEM, because our atom probe needles are about 50 to 100 nanometers in radius, so the tip, at least on the top part, is also electron transparent. We leverage it to essentially do the same thing, but to our atom probe tip, and we get the structural information. And we have the structural information, we have the chemical information, we put together. Sometimes in materials, we know that all the high angle grain boundaries or all the low angle grain boundaries do not behave in the same manner. So we also do statistical analysis, we say we do 4 to 5 grain boundaries, depending on case to case. Wherever needed, it always, because as I was mentioning, we are just looking at very few small set of region, and whether that is a representative effect of a material or not, we have to be a little careful in trying to extrapolate that. So this is one other example where I was talking. Yeah.
One comment.
Yes.
Is Kikuchi line depends on the thicker and thinner regions of the transplantation?
No, the Kikuchi bands come from structural information. So whether it is thick or thin, as long as the structure is the same, the band, as long as it is the same grain, the band will be the same. The Kikuchi pattern will be the same. However, if we are going in very thick regions, then our electron beam that will not transmit. So we will not be able to effectively get a pattern. But if the question is, I have an electron transparent region, one area is maybe 80 nanometers, another area is 60 nanometers, it is the same. So this is, until now, I was talking about nucleation of a phase, but what about growth? Are these grain boundaries influencing anything of our growth? So in this case, it is not atom probe. This is just to illustrate what transmission Kikuchi diffraction can do. We make a TM kind of a lamella, and we do transmission Kikuchi diffraction. You see the resolution is much finer compared to an EBSD. So these are like low angle grain boundaries, where the product phase, which is green, is forming along the boundaries, which means there is nucleation and the growth is happening along the boundaries. The moment we come to high angle boundaries, you can see that the size of the product phase is much bigger, which means it is growing a lot more easier at a high angle grain boundary compared to a low angle grain boundary. So this is an information we can say very confidently because we have a lot of points with which we can say with great conviction that this is my product phase. And then, because this is a TM lamella, we can do transmission Kikuchi diffraction and SEM. And now I know what is the area that I have to focus. Then I take the same sample to a TEM and try to do some TEM studies. So the next slide will show this rectangle. So this is a TEM micrograph, and we have EDS. This is from Keniston. One thing we notice is wherever you have the austenite which was forming here, you see the austenite is along the boundaries. So the growth, so this is the product phase, and the product phase is manganese enriched. We see it is growing along the boundaries. Now, so which means the boundaries are helping the sample or helping the manganese to be transported from a pairing phase to the product phase. So in our manuscript, we quantify why and how it is happening. But for now, we can just take that we are able to exactly identify how these boundaries, which are 2D defects, are helping the growth. The next thing is, one other thing you notice here, there are a lot of dislocations which are terminating at this interface. So now what is the role of these dislocations? The same dislocations, when I look at an atom probe, we see that this dislocation, this is manganese, this dislocation, if you go from outside to inside, in the micrograph, so in this graph, distance -6 is away from the interface, and about -1/2 to inside is the core of our dislocation. We see that this particular manganese, which is a solute element in this case, is nicely going to our dislocations and segregating. I think the first question which people will ask me is, how do you know that there are dislocations? Until now, you've been telling us that there's only a chemical technique. How do you know there are dislocations? That is thanks to 2 people of my group who dedicated their PhDs, where, as I was mentioning, we can correlate atom probe with another technique. In this case, we first perform transmission electron microscopy on this tip, because atom probe, if you remember, we are ionizing atom by atom. So after we are done with the atom probe measurement, it's a destructive technique. We don't have anything left anymore. So we first do TEM, we image. Now we know the structure of grain boundaries, dislocations, we know the complete structure. And then we run the same sample in an atom probe, and we know the chemistry. So even for a defect, like a dislocation, screw dislocation versus edge dislocation, we are now able to quantify both the structure as well as the chemistry. So this is also the biggest advantage of correlative microscopy, because if we were to try to understand the chemistry of this dislocation from a TEM, we'll not get any reliable data. On the other hand, atom probe is able to provide that, but then we don't have reliable structural data, which the TEM is able to provide as well. Now, the other thing also, I'll give you a small example where we, the resolution which you can see is about 50 nanometers, and just focus on this particular small area. We have 3 alpha grains, alpha 1, alpha 2, alpha 3. All these are parent grains, and gamma is a product grain. Now, until now, I have been showing that manganese nicely segregates to the grain boundaries. So in this material also, if we were to look at the chemistry between alpha 1 and alpha 2, or alpha 1 and alpha 3, we should see that manganese should segregate. However, like when we look at alpha 1, alpha 2, we see on one side, this is how we start, 10%. On the other side, there's a great depletion. Fine. What happens next from alpha 1 to alpha 3? Rather than segregation, we see there's a depletion of manganese. Why and how is it happening? The reason is pretty simple, that this particular grain boundary which we see here, the manganese is using this grain boundary as a short circuit diffusion path. Because if we go back and look in the literature, we look at the diffusivity of solute elements in the grain boundary versus bulk, it is a couple of orders of magnitude faster. Now we have a product phase which likes manganese. So at the grain boundaries, because the diffusivity is faster, they act as very fast diffusion channels, and then they promote the growth. So this is a very local snippet which we would not be able to get it with any other technique with such high fidelity, that my boundaries are helping diffuse a solute element. In the interest of time, maybe I'll just quickly go through it. So we also know, on, for example, the product, this side is growing. On the other hand, this is not growing. So people familiar with physical metals, we can identify this is a coherent boundary and incoherent boundary. The way they grow would be different. We also get chemical information. That is why we have a compositional gradient on one side and we don't have it on the other side. And one last example from my work is we added a bit of niobium. What we added is 0.03 weight percent niobium, which is extremely small. And then it changed our mechanical properties, and we wanted to understand why. And we did all the other scale testing, and then we had to come down to atom probe. I mentioned that this is a dislocation, and we have manganese enriching it. So we are able to identify what is a dislocation by looking at manganese enrichment. Now, we have this niobium, which nicely comes and sits and forms at these dislocations. And the dislocation density of the parent material is about 10 to the power 16 per meter square, which is extremely high. So which means we have a lot of these places where my carbide which is this niobium carbide, can form. And it is not necessary that when we think of niobium carbide, we think it is 50-50 carbide. However, when we look at this chemistry closely, we realize this is not even a 50-50 carbide, which is what we call a transient carbide. And this completely changes a lot of things. One, it changes how the product phase nucleates, but also how it grows. For example, you can see these are two ferrite grains, which is the parent, and we have austenite, which is a product. And you can see there is a carbide which is sitting right at this junction. So in a three-dimensional way, if you just look at these interfaces and the carbide, you can see it is exactly sitting at this triple junction. Because it is sitting at the triple junction, it will hinder the movement of any of these boundaries because they're being blocked. So let us say if my product phase wants to grow, this particular carbide is going to prevent it from growing. So in this way, such small-scale nanoscale chemical information, which are very important for bulk properties, APT is a very good technique for us to understand. So I'll just skip this summary in the interest of time. We'll switch the gears to look at some other materials. I'll talk about a couple of cases which I worked with, and then I give some information from literature. So one of the things which were working was chromium oxide coatings on steel. So this is packaging steel, and there is about 4.6 million tons of production, and they have these oxide coatings to prevent corrosion. Traditionally, they were using hexavalent chromium coatings, which is chromium 6+. However, that is not good for health, and the whole industry had to move towards a new kind of coatings, which were based on 3+ or trivalent coatings. So this was a project in conjunction with Tata Steel. So they came to a colleague of mine who was in the other department, Manoj, where they said, look, we are getting nice properties, but we don't understand why. And then so in this paper, we also correlate with some XPS. But then when we looked at atom probe, so this is the steel, which is the iron which you see, and then this is the layer. When we realized and we looked at the chemistry, we realized that on the top part, which is the oxide, it is CRO. It is about close to 50-50. Typically, when we think of chromium oxide, we think it is Cr2O3. So CRO is not a composition that is expected. And then there is some carbon, which is a bit of a carbide, but let us just focus on the CROC. So when we first got this information, and they were skeptical. They're like, maybe there is some artifact in the data, it can't happen. And we said, even it is interesting for us why it is CRO and what does it mean for its structure. And then we did TEM, and then we were able to clearly show that the CRO layer is actually not even crystalline, it is amorphous. And then we have the CROC layer, which is a bit crystalline, and then we have the substrate, which is, of course, it is crystalline. So with this, we are able to show that one, the chemistry is off-stoichiometric, and then there is a very close relation with this chemistry and the structure, and this in turn we were able to explain the properties it was showing. So this again, we are looking at something about 10 nanometers, and we can still give the chemical information with very high fidelity. Another project which I worked with is design of batteries. So normally we have about graphite anode materials for our batteries. The capacity is around 400 milliamp per gram. If we were to use silicon as an anode material instead of graphite, we'll get 10 times the capacity, which is 4000 milliamp per gram. What is it that is preventing us? When this silicon is lithiated, it forms something called SiLi 4.4. But the take-home message is, when this happens, the volume change happens by 4 times. So then, when I have a material during lithiation, there is a huge volume change. There's also something called solid electrolyte interface formation. It becomes thick. But also what happens is, because we are making the same material change volume by 4 times, it induces cracking. So after many cycles, we'll have small particles and with a lot of electrolyte interface, which is not good. And when there's such a volume change, structurally it is not feasible in daily components. So this is one such silicon particle after multiple cycling. You can see numerous cracks at a very small scale. And this is after multiple cycles. This is a sample which our collaborator from Belgium, they gave us. And then this is after few cycles, we see the cracking is not extensive. We take a sample and lift out. And here, what we see is this is a material with silicon, and it is a composite. We have a silicon, and it is as a composite. And we showed that wherever we had high silicon concentration, the lithium is only going there. In the matrix, not really. So silicon is the material into which the lithium is intercalating during charging. Now, we wanted to extend this and see, can we reduce the size of the silicon so that we have small silicon precipitates, very large matrix, and it will confine it. For that, we did some magnetron sputtering deposition. We had all amorphous. Again, with APT, we can confidently say it is homogeneously distributed. And then we start annealing this. By changing the temperature and time, we can actually control the silicon precipitation. Here we see the onset of the silicon precipitation, and it is very few nanometers. So the whole idea is, can we control the silicon size, and in this way, can we enhance the properties? I would say we were not completely successful, but that was the first attempt. So this was sputtering on a copper substrate. You can see after charging, there's still some volume expansion, and we see some delamination, but at least on the cross section, there was no cracks. And it gave very high capacity. So this is one example where in battery materials you can use. So I'll show some examples from literature. So one is with thermoelectric materials.
But that is only for some number of cycles. But did you do the same thing for all around?
Yeah, so we had some challenges experimentally. So we had to drop it because we deposited this on a copper substrate, and we wanted to precipitate. But the moment we annealed it, copper started diffusing into our coating. So it did not make a lot of sense to go for electrochemical measurements later, because now we are no longer looking at the same chemistry. We had copper coming in. So that was a bit of a challenge where we could not see through the project.
Even this kind of technique can't be applied in next round of cycling, right? So even if you, whatever the result.
So we also did something, but for the same material made through a different synthesis route, where we looked at number of cycles and how much lithium goes in, where it goes in as a function of cycling. So this is an example from thermoelectric materials, where this was ball milled and then spark plasma sintered. So on one hand, we have non-annealed material. On the other hand, there is an annealed material. So this is small and large. The reason you don't see that intuitively is the scale bar is different. But what was very interesting is when you look at the conductivity, the annealed one shows better performance. And if you look at this local electric measurements, you can see that they can do the conductivity measurements within one grain across a grain boundary. So this is one example where this is smartly putting together what is the property that you're measuring with looking at the chemistry. So then they had two materials, one with a smaller grain size and the annealed where they had larger grain size. So this is in the grain interior. Compared to the grain interior, the grain boundary is about order of magnitude lower. However, the moment they annealed, the grain boundary performance improved. The question was to see why, and they attributed it to the segregation of platinum, which increases the grain boundaries with annealing. So the idea is we have grain boundaries, and we are able to change the chemistry of the grain boundaries, and that changes the thermoelectric behavior. Another example also in half-use level alloys, where they had two different materials, where they are able to change the segregation, and that changes the electrical conductivity. One other recent example, which is very interesting, where they have, this is EBSD, and they have a very specific region, and they go down, pick it up, and do, so this is the grain boundary of interest. Let us say if they want to look at across this grain boundary, they do the conductivity measurements of this grain boundary of the lifted out region. And then from the same grain boundary, because there's a huge grains, they pick up the sample and make an APT needle from a different region. It is exactly the same grain boundary. So now they can say, I have my property of one grain boundary, and I also have, I'm showing the structure and chemistry of the same grain boundary. And so this is the transmission Kikuchi diffraction I was talking about, and you can clearly see this is the same misorientation. What did they observe? That this is a lead tellurium with some silver doping material, the segregation that happens to low angle grain boundaries. For people familiar with the structure of low angle grain boundaries, you can also think of it as stack of some edge dislocations or screw dislocations put together. And the core of a dislocation will have high stress fields that would be one of the driving forces for segregation. You can see that the segregation at low angle grain boundaries compared to high angle grain boundaries. What they explain in detail, I'm by no means an expert in thermoelectric materials, but what they explained is due to the segregation, the local bonding behavior changes, and because of that, the properties change. So this is one other example of thermoelectric materials where we are able to show that the chemistry of a boundary is very important. And when we do our experiments very carefully across one grain boundary, we are able to go down and identify how the chemistry affects the properties. Then we can use this information to smartly tailor the chemistries of these boundaries to get better performance. This is one small snippet where the applications of atom probe in electronic devices. So electronic devices could be LEDs, HEMT, field effect transistors, FinFETs, memory devices, and also solar applications. So this is one case where they're looking at a doping profile across a FinFET, and this is also very relevant for industry when they have some failure analysis. They go to a very specific region and they look at the chemistry and try to understand what is the cause of this failure. So this is by Global Foundries. That is why if you look on the y-axis, you don't see any chemistry because they don't want to disclose it. But clearly you can see when they're trying to see the local doping concentrations across these interfaces. Another example is multi-layer ceramic capacitors. This is from Samsung, where they're trying to see trace elements in these barium titanate. And when you have a material with a lot of elements, you will get a mass spectrum which is fairly complicated. And they're trying to see what are the trace elements, where are they, how are they affecting your material properties. And I'll just try to conclude this. So when I mentioned about correlative microscopy, I said, okay, we can correlate atom probe with transmission K-Q diffraction. We can correlate atom probe with TM. Is it the only things that we can correlate with? No. We can do it with multiple other testing methods as well. For people who are familiar with micromechanical testing, so there is something called micropillar compression, where they go make a small pillar. It could be of a single crystal. In this case, it is of a bicrystal. So there is orientation 1, orientation 2. They try to apply a load, and you can see these are the slip bands, and try to see what is the strength. So this is one kind of micromechanical testing where we get a lot of information of how the material behaves at a very local scale. This is another example where they had two cases. One, they had a bicrystal, and the same bicrystal, they had a small silver deposition and they annealed. The reason is so that the silver can go into the boundaries. So there's one without silver, and then there's another with silver. And clearly, when you look at the yield stress, the segregation which you see silver, which is nicely sitting at this boundary of this bicrystal, is able to clearly enhance the strength of the boundaries. So this is another example where you're having a micromechanical testing method. You do EBSD, you're getting information about the local strength, and then again you're performing atom probe on that grain boundary so that you can identify the effect of chemistry very clearly. And we talked a lot about site specificness. Two more examples before I conclude before my concluding remarks, where such site-specific chemical insights are very precious. For example, this is one case where this paper talks about hydrogen embrittlement. For people who are not familiar with hydrogen embrittlement, you can simply think that there is a structural material. When there is hydrogen inside, it can assist in premature fracture. Now, they observe there is a crack. So there is a small crack, and they're making the site-specific field club just beside the crack. So whatever chemical information that we are getting, so if you look at this crack is not sharp, rather blunt. So what is it that is helping this crack to be blunt? And then since the atom probe lift out is being done in a very localized manner, we are able to, in this case, the heat treatment or the material design was done in such a way that you can get a gradient of your solution. So if you can see manganese, this is a 2D plot. Higher red color is higher intensity and blue is lower intensity. You can see that on the left side you have manganese rich, on the right side it is manganese poor. So this is the chemical gradient. And this chemical gradient is what exactly assisting in these crack arrest. Another example is from Surendra when he was a postdoc, where you can see this is a nickel-based superalloy and there are these stacking faults. So this is something which we call electron channel contrast imaging, where we can look at dislocations or faults but in an SE. So first you can identify the area of interest and then make a sample lift out, but also do TEM before. And then when you realize there is a stacking fault and there is a chemical segregation at these stacking faults. And for researchers familiar with nickel-based superalloys, three properties are extremely important. And there is segregation at such defects, they have a huge implication on the three properties. Now, we said correlative microscopy. I promise this is this last section. Now, until now we said TKDE, micromechanical testing, but it's not just limited. So this is one very nice example from Kevin, where they do scanning photoemission electron spectroscopy. I said there are silicon posts, they have the iridium IR-RU deposition, then they oxidize it, you have an oxide forming, then they perform the scanning photoemission electron microscopy on this, which is not destructive, and then they put it in atom probe, which is a spectroscopy technique. Another example is with XPS, X-ray photoelectron spectroscopy, where we are able to see on the same tip, we get information from XPS, and then after that we put it in an atom probe, which is a destructive technique. So the possibilities are limitless. The question is, what is the information that we want? Atom probe can give us chemical information. It does not give us what is the bond energies, all these which probably a lot of spectroscopic techniques help us better. Or it doesn't give us structural information. It doesn't give us what is the structure of a defect. How we take a technique which has very high chemical resolution, chemical fidelity, and complement it with others so that we can understand what is happening at a nanoscale, so that we can design materials at a nanoscale which gives better properties. With that, I will look forward to any questions.
Sir, how much you charge if our students come and...
So it is on the website. We have, if it is a partner institute, it is about 30,000 end-to-end from FIP sample preparation, then atom probe, and also the data analysis. So this is the current charge if it is a partner institute. So Sathi website, we have charges for all the microscopes that we have here.
Sathi website, your IIT.
So this is a sophisticated analytical instrument. So this is a national facility which we have established where you will be going to a workshop tomorrow. So it is a consortium of different microscopes, and we got money from DST as well as some other partner institute who helped us set the facility. So on that website, there will be charges for all the instrument usage.
So for partners, it will be less or?
Little, of course. Yeah, partners we charge same as IIT Hyderabad. There's no difference.
Means after 6 months, till the time is over.
No, we are not partners.
So partner
Spoke partner institute.
No, sorry. Spoke. So Sathi partners are different. So this is ANRF Spoke, but when the institute was being set up, we had contributions from industries as well as some academic institutions who helped us set up the facility. So for them, the costs would be same as that of what we charge internally.
Thanks for showing your work on HPT. I have a technical question. Should you please comment on it? For example, I am working on FERUMNSI, that is an alloy.
Okay.
So it is having FCC structure.
Okay.
I am observing some anti-side effects. That means RU and MN can change position, but within the same FCC position.
Okay.
So, would you suggest me to go for neutron diffraction to reveal the atomic structure, or can I go to the APT to do the same?
So in APT, let us say if we have some short range ordering. So because we get a good amount of data, we'll be able to extract. We have a few million ions that might be. We'll be able to do data analysis. They have been worked in the direction where they're able to look at short range ordering. If there are two cases, like maybe case 1 and case 2, and you want to see the difference and see how the short range ordering changed, atom probe would be helpful. But if you want to look at more from the structural point of view, then I think neutron diffraction would always be helpful. I mean, I think the whole point of my talk was that use two techniques together. That would be like a foolproof method. But in your case, I'm not very specifically familiar with your alloy, and I'm also not sure if the short range ordering exists, and if we can find it from APT, maybe you can go through
We can
the
still
literature.
do this kind of analysis to add some more good evidence along with neutron diffraction.
Yes, yes, yes.
Yeah, generally I'm working on metal matrix composites. Generally we'll be going with EDS or XID. So if I go with APT, how it would be, or how it's going to help me?
So let us say if there is, when I have a matrix and there's an interface. The question is there any change in the interface chemistry? Like when I've worked on some Laves phase-based composites, and we saw that there is a matrix and there is a precipitate and there's an interface, hard phase, soft phase, but there is a change in the interface chemistry. Now, whether the interface can behave in a very brittle manner, which causes decohesion, or there can be some local deformation, all these can be a function of the local chemistry in addition with the local structure. So this is an insight which will only be able to get from APT and TEM. Then if you can make your, again I'm not an expert in composites by any means, but if you can now have a means with which we can tailor, like in steels for example, we have a phase boundary, phase A, phase B. We can add certain elements which will particularly go and sit at these boundaries, which will increase the cohesivity. So in your case, for example, if there is any such element which can increase the cohesivity, now you can make a new alloy where you can strengthen the interface.
Why do you think they move towards the boundaries? Maybe because of the weight, or why do they go?
So when we look at a grain boundary, we know that we have in two grains there are two different orientations, and the coordination number at the grain boundary is not perfect. So that leaves there is it acts like a surface, and by going to the boundary, essentially there will be an energy reduction. Gibbs free energy would reduce locally. So this would be the driving force for the atom to go and segregate there. That is why as a consequence, the segregated boundaries would have lower energy compared to the unsegregated counterparts.
Can you throw some light on AFM?
AFM. So again, AFM with APT or in general AFM?
In general AFM, and how it is?
So in general, okay, again, I know my limitations, so I'm not an AFM expert, but typically I have used AFM in terms of nano indentation. So where we use it is, let us say we have a grain boundary and we want to look on grain 1 and grain 2, what is the local hardness, and then what happens at the grain boundary. Now again, segregation can change things, so that is where we try to look at a boundary with segregation, without segregation. So you looked at micropillar compression, but the same kind of things you can do a lot more statistically with nano indentation. Let us say you have large grains, you have a large boundary network, and we can try to do multiple indents across this boundary, and then we can have two boundaries. And also it's important to always remember that the structure has an implication on the chemistry as well. So whenever we are comparing two different materials with different segregations, it is always ideal to look at boundary with similar misorientation, a high-angle boundary with a high-angle grain boundary.
So for these studies, I can use AFM?
Yes. So if you have a very huge boundary, what I would recommend is you make multiple indents and then look at the local and just leave a certain portion which can be taken out for atom probe. So then you will be able to show that, look, I have a huge boundary. Maybe if you have a 100 micron boundary, you can do about 80 microns indentations, and you can get a very statistical measure of how the hardness is varying in a sample A with segregation, sample B without segregation, and then you can leave a bit of 20 microns, and then you do atom probe on these two samples, and then you can very confidently say, look, I have one boundary with very similar misorientations. On one boundary I have this hardness, on another boundary I have this hardness. So the misorientation is similar. I'm picking up the atom probe sample also from the same boundary. Now whatever is happening because of the chemistry. So this is where I said we are looking at very small areas, but when we design our experiments in a very robust way, we can very confidently say that this is happening because of my segregation.
Any other questions? No? So, thanks very much.
Thank you very much. It was a pleasure.
So, you might, so I think recording we can stop. Recording is done.
Stop the recording.
Thanks.